Generative AI is changing the world as we know it. Till the time to create out of the box images, people were using softwares like Photoshop and Illustrator, and it is used to take hours of hard work. Now, this task can be done just within few seconds. If you feel like your photo is too serious, you can do one click and make yourself laugh. If you feel like changing the hairstyle, let's say short hairs, you can do so within one more click. And you know the crazy part? All these things look too real to be considered fake. It doesn't stop here. Today, film producers are saying that they are going to try generating movie scenes with tools like Sora, Heijin, Runway, and so on. From image, video, text to audio, AI can now understand and interpret everything, and that's why the world is going crazy over it.
Should we automate away all the jobs?
Every technological revolution leads to job change, and this will be no exception.
Concerns over the rapidly expanding use of artificial intelligence.
The danger of AI is much greater than the danger of nuclear warheads by a lot.
The machines taking over is a threat for everybody. It's a threat for the Chinese and for the Americans and for the Europeans, just like a global nuclear war was.
AI is going to change education, it's going to change politics, it's going to change the entire job market. I mean, there are already predictions that AI is going to change and reshape the entire job market by restructuring 85 million jobs and by creating new 90 million jobs by 2026. And believe me, that's not far. There is no point in debating about AI is threat or not. It has already arrived, and it's high time to adapt it to thrive in the near future. This is something we are not trying to frighten you about. Rather, we want you to be aware of the technology and learn it to be more successful in your careers ahead. And to exactly support what I just said, we at Intellipaat have created this generative AI course. Within this course, we have covered the programming, deep learning, and artificial intelligence practices that are being used to create the new age tools of generative AI. This course is not about the demo of how to use particular Gen AI tool, but rather it's about generating how to create these tools and the logical intuition behind writing their programs. So if you're already well versed with data science, machine learning and deep learning, continue further and master the art of artificial intelligence to get yourself ready to become an AI engineer. Having said that, let me walk you through the agenda that we have at hand for this particular course. We will start off by understanding what is generative AI. Then we will discuss about LSTM and transformers, which are very important deep learning algorithms you need to understand before we jump into the advanced generative AI concepts. Next up, we will talk about BERT model, which is an open source development by Google. We will understand how BERT works, and we will also do the hands-on for the same. After we are clear with this, we will talk about transformers, the concept of encoder and decoder, what are embeddings, as well as hands-on exploration of transformers. Once done with these concepts, we will jump into the discussion about Hugging Face, what it is, what's the core of Hugging Face, different models, open source libraries, and documents available, etc. Moving forward, we will discuss how to create LLMs, LangChain for generative AI, what is prompting and retrieval-augmented generative, alongside best prompting practices. I hope you're clear with the agenda. So without wasting any time, let's get started with the first topic of this generative AI course.
What is an explainable AI? Before I answer this question, let us go back and understand why exactly it exists first. Let's say I have gone ahead and built a model which helps recognize if the patient has a disease based on their X-ray records and MRIs. I have done this by using a deep learning model to recognize the pattern out of the images. Now I gave this particular model to the doctors. They went ahead and put out some patient samples through the model, and the model provided almost the right decisions. But this fact scared the heck out of doctors. They asked how exactly is this model coming to these particular deductions? What things or computations are happening behind the scenes to reach these particular decisions? And how can I trust the results generated by a machine to treat my patients? Basically, doctors or you viewers don't know anything about my model. It's kind of a black box for you or everyone. I mean, you can just provide an input, some magic will happen within the black box and you'll receive the output. But you'll not be able to interpret what's exactly going inside this black box. Well, the irony is even me, the developer who has developed this particular model, will not be able to explain how it came to a particular decision. You see, it's not just about me. Any data scientist or machine learning engineer or an AI engineer will not be able to explain the computational details behind predicted output. they'll not be able to explain how a model reached a certain decision for a peculiar instance in a testing sample. And this is a problem, right? Well, if there is a problem, there is going to be a solution as well. And that solution in our case is Explainable AI, briefly abbreviated as XAI. Well, it do help us humans worried about black box situations understand how an AI model comes up with results and how much we can trust those particular results. Let us explore the different components of Explainable AI to better understand how exactly it works. In a basic sense, it comprises three different components. Number one is prediction accuracy, then there is interpretability and justifiability. The prediction accuracy and interpretability are two technical aspects, whereas justifiability is something that's going to solve our problem. That is, understanding how a model reached a certain decision. Let's start by understanding the prediction accuracy. Prediction accuracy is a highly important metric for any machine learning engineer or data science professional, right? Because the success of your machine learning model is going to be judged by comprehending how accurate results your model provides. Generally, when we compute the accuracy, we try to learn the pattern in data and then check how accurate results the learned model is making for the testing set, right? Well, in case of Explainable AI, it is not going to change. It will remain the pretty much same, but it's just that you'll comprehend the performance by using models like LIME and running multiple simulations to match results and understand the performance. LIME is a technique that helps to explain the prediction of an AI model at the local level. Next one is interpretability. Interpretability, or in other words, what we call as traceability, is yet another important factor. Generally, when we try to work and build a model, we actually happen to have a problem and data set at our disposal, right? We try to visualize the attributes present in the data to figure out their correlation. We even dispose of certain columns that don't feel much relevant, right? By doing all these things, we are actually trying to interpret the question and how a solution can be framed. In a similar manner, in the case of machine learning or AI model, interpretability resembles how the learning of a model can be broken down into chunks. If it is a decision tree model, what are the rules the model is setting, what are the important features the learning process is revolving around, etc. Figuring out answers to these factors is basically what known as interpretability. To achieve this, we have a framework called as deep left, which explains predictions by analyzing input feature changes. Finally, we have something called as justifiability. Well, as we already mentioned, this component is all about solving the human mistrust in AI or ML model. If I were to explain justifiability with a simple decision tree that predicts whether a student can get into BTech program based on the marks he got, if he got more than 85% marks in computer science, he can easily get CSE, or even if he got 80% mark but carries excellent extracurricular skills, then too he can get into the BTech program. So we arrive at the conclusion that certain factors within my dataset would lead to alteration of results. Figuring out these exact rules, figuring out these exact attributes that have more say in the decision, etc. are the main components that we try to break down. Not only that, we try and understand if there is a slight change in the input provided, and if there is a change, what kind of output will turn out to be. Now let me put all these three components into a practical use case by taking the same example that I took in the beginning of the video. Say, if a person has cancer, our model should be able to take X-ray images and detect the cancer cells accurately. It should not interpret it with any other disease. This highlights how much the outcome of this model can be trusted, which is known as prediction accuracy. To understand the nature of disease, the AI model has to break it down into smaller chunks, which would narrow down the scope of the data. The amount of data we humans are able to understand from these smaller chunks of data is defined as interpretability of the AI model. Why the cells in the X-ray were termed as cancer cells and why not any other disease underlines the justifiability of an AI model. So you see, overall the explainable AI is not just about building trust or understanding how a decision was made, but it is about troubleshooting the misprediction and improving models' performance.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
So what exactly is an LSTM? So we saw that in, if you look at the RNN equation, let me pull that again here. Where is the equation? Yeah, here it is. So this equation of RNN, right? This is exactly where we are having the previous state. So this is the state, and this is the previous state. And this is again unfolded to t minus 1, t minus 2, t minus 3, and so on and so forth, right? And that's what exactly was causing the vanishing gradient problem for us. So now this can expand till infinity, right? Logically, it can have like infinite number of, or maybe infinite number of previous sequences. So that is exactly what is causing us the vanishing gradient problem. So if it means like if you increase the context length, right? Remember that we took some context. So if you increase this context size, you have to go a lot back in previous time steps. Okay. So then there came a new architecture, which is called an LSTM, which is called long short-term memory. So the key idea behind this long short-term memory cells, long short-term memory, I think that's what we will focus more. That if you take, so this is the same RNN equation that we know. Instead of HT, I'm writing this as S of T. And if we can make this gradient h of t minus 1 equals to 1, then we can actually avoid the gradient vanishing gradient problem. Okay, because moment you if you start dividing this with the previous time step, this will become 1 for you, and you don't have to, it means like you don't have to go back in time to actually compute for certain values. Okay. So what this exactly means in terms of context? So it means like when you are trying to predict the word, let's say I love ice cream, and let's say this is the next word that you're trying to predict. Now this becomes the h of t for you, and this becomes the h of t minus 1 for you, and this becomes h of t plus 2 minus 2, h of t minus 3, and h of t minus 4. And you will also have h of t minus 5, which we initialize with some zeros. Okay. So we say that sometimes it's not required to go very long in time. We can skip certain parts. So we can skip this one. So we can go here and rest we can skip. So if I scream a lot, so based on these very important words that you can actually, the less important words you can skip, and the important words you can remember, right? This can actually help us predict the next word. Again, like this is not a very good strategy, but in the longer run, we can actually avoid this vanishing gradient problem and can run with longer sequences. Okay, that's the value add that LSTM cells are actually doing. So that's the overall intuition of LSTM. Now, what exactly is LSTM? To understand LSTM, there are certain components that we first need to know. An LSTM will have one input gate, and when I say gate, it's nothing but it's a different equation altogether. So it will be an equation, input equation. This will also be in equation. Output gate is also going to be an equation for us. And this is what, if you look at the paper, LSTM paper, this actually looks like. Okay. Now let's try to decode this line by line. Yes, the data is inputted from the left direction. Okay. So your input actually starts from here. So actually input xt starts from here. So this is the input xt, and this is the previous state ht minus 1. Okay. And we are talking about the first, which is this is the forget gate that we are talking about. This is the forget gate. This is the forget gate equation. So for the forget gate, we get the previous input, we get the input, and we take the sigmoid function. So this is the sigmoid activation function. So here in this equation, this xt, which is this, gets multiplied by some weight matrix. We call this as weight matrix for forget gate. That's why we take a subscript for f. This means this is the weight matrix corresponding to the forget gate. Then we have ht minus 1, and we multiply this with the u of f. This is another weight matrix which is corresponds to the forget gate. So you multiply them together, you add them, and you then take some activation function which is sigmoid. So that's why this is the ht multiplied by uf, xt multiplied by the weight matrix wf, and then we have taken the sigmoid, and that actually corresponds to the forget gate t. Pretty simple. For now, remember, like, this is a equation. Remember, this forget gate is a equation. U of f is again a weight matrix. It's a weight matrix. It's just denoted differently because it corresponds to the weight matrix of your previous state ht minus 1. Okay, let me do it again. So I'm saying just trace to these paths. This is one path. Okay, so this path actually gets one input xt, and this gets ht minus 1. We multiply with this weight matrix. We call this w of f. We multiply with u of f. We add them together, and we take the sigmoid, and this becomes the forget gate ft. So just park it for now. I'll explain you what is the importance of this ft in a moment. Then look at the input gate it. This is the input gate. So this is the forget gate. We call this as forget gate. And this is the input gate. Now input gate is, again, if you clearly observe, is a combination coming from ht minus 1 and xt, and getting multiplied by or getting activated by again another sigmoid function. So we multiply this x of t with w of I. This is the third weight matrix, and I want everyone to keep track of how many weight matrices, different weight matrices are we using. So this is number 1, this is number 2, and this is number 3. This is the third weight matrix, which we call as wi. We multiply this with u of I, which is again the fourth weight matrix that gets multiplied with ht minus 1 and the sigmoid function I. Okay, so this is the input it, input gate. So till here, till this point, this is the input gate. Now the C tilde, this is what is called as an intermediate state, which we call as an intermediate state. Intermediate state. Then this intermediate state CT says that it's a combination of, again, ht minus 1. This is the ht minus 1 going inside, then the xt going inside, and we coin this with another weight matrix, which is the fifth weight matrix, u of c, and the sixth weight matrix, w of c. And this time, instead of taking a sigmoid, we're taking the tan h function. Okay, so the outcome here is the c of t, okay, which is the intermediate state, or the new cell state. Okay, and the cell state this is what is called the cell state, this equation. So this equation is also clear how it is being derived. And this is also done. So now we are looking at CT. Now this CT is actually the dot product between the forget gate, this forget gate FT dot with the CT minus 1. So this outcome is actually your CT tilde R. And you're taking, and this was your forget gate FT, and we are taking the dot product here, this. And we also take the input, which is the input gate, which is nothing but this one, this input, and we dot product it with the current time step CT. Okay, so what it says now look, like the magic is actually happening here in this equation, which is the cell state equation. This says that your cell state, the memory, this is the memory actually. This memory will only store something when your FT is 1. Okay, let's say the FT value comes out to be 1. Then I am going to remember what has happened previously. Plus, I will also remember the current input and the current cell state. But if this FT is becoming 0, right, then I will forget what has happened previously. I will only remember what is happening at the current time step. That's why it is called as a forget gate. Okay, because the forget gate value, actually it's like a on-off switch. Okay, remember this CT is not, so this FT is like an on-off switch. This is on and off switch for us. So this will dictate whether you want to remember something. Yeah, you can say it's like a Gajni model, exactly. So it's like an on-off switch, whether you want to remember something in the past or you don't want to remember something in the past. And that's the addition that you do in terms of the RNN, right? So now when you selectively choosing which information to pass and which information not to pass, then you are increasing your long-term dependency. Making sense? So let's say now, previously, let's say when you have the capability to remember, let's say 10 words or 100 words, but now if I give you that the choice that, okay, you can selectively choose whatever 100 words you want, then probably your recall memory will increase, right? So you will say that, okay, I will not remember is, am, and this unnecessary word. I will only remember important words. Okay, so when you do selective, let's say memory, then you are increasing the long-term dependencies, and that's the value add LSTMs are actually adding on top of RNNs. Make sense? And once you have the cell state, right? Once you have the cell state, the CT, then you can get the outcome from the HT minus 1 and the XT. And this HT is actually getting from the output and the cell state CT. So this is, I think, the same equation as RNN. So this is the same equation as RNN equation. This is also like same as RNN, and this is same as RNN. The only value add that we are adding here is these two. This is what we call as the cell state, like this is the memory. And in order to control this memory, we have a switch, which is called as the forget gate. Intermediate state, because see, in calculating the cell memory, you need CT minus 1 also, right? So that's why you need to store the previous time step also, right? So that's why it's called an intermediate state of the previous value. Okay, so we don't have to actually code this from scratch, because similar to RNN, we also have an LSTM representation in PyTorch. So everyone, please open up your Jupyter Notebook instances. So we'll do the same next word prediction, but this time we'll do this with LSTM instead of RNN to see if you still see some improvement in the next word prediction. Yeah, open your collapse. And does anyone remembers the text that we have used? Well, let's create a new one. I'll just copy paste here. Yeah, the Virat Kohli one, right? Can somebody paste the text here? Or let's use the same. We'll just be changing few values there. So then that should be simple. Okay. So I'll probably use the same RNN example. Yeah, this is it. So here, the only change that we will probably make is that instead of using an RNN, we'll probably use an LSTM. So here, instead of RNN, we'll just simply change this to an LSTM layer and run it again. Or just the learning rate, train it. Okay, now, so there is some change that we need to require in order to do that. It's not very straightforward because in an LSTM, so this needs to be converted to an LSTM cell. This LSTM actually contains one more output, which is the cell state. So we have the H state, right? We also need the cell state. So I'll call this as HN, and we also need the CN, which is the cell state. So this is will be the outcome of your LSTM. And here also you will be requiring C0. And here also you will be requiring C0, which is nothing but the cell state for the very beginning of the sentence. So that's the only modification that you need to do. And you need one more modification here because you need HC0 also. Call this as C0 and we'll pass this as an input C0. Let's do the training. LSTM forward takes 2 positioning input, 2 were given. Okay. Because I think I have also need to do the return statement here. Sorry, my bad. So this will be HCN and CNN, and we can make this as a tuple. Okay, again. What's wrong? What's wrong? Out. And this should also be combined together. Okay, now it's good. So next, then we will do the next word prediction, which is we also need C0 here. I need to pass C0 also here. Zeros. One sec. What is the hidden size that we have used here? Hidden size 256. No. Okay, so I'll give you some time. So I think no need to change anything from top. We'll keep it as is. Make the changes directly in the vanilla RNN, right? Or we should call this as LSTM also. LSTM, LSTM, and LSTM. Okay, make these changes. Just duplicate the RNN collab that you have and make the change directly there. The changes here will be in the LSTM. In this LSTM, then while defining the forward layer, we also add the cell state C0. And here are the cell state which are given to the LSTM model. They output the next cell state. Okay, has everyone made the changes to the LSTM and they are able to run the training? Okay, let me just check if everything is working good. Just answer this class is okay. Text splitting is okay. LSTM model okay. We have embed size. Let's keep it to 128. Just making some minor changes. LSTM model not defined because we have not run this. We'll run the model. Okay, we'll define the loss function. And we'll also define, let's time it to see how much time does it take to run. Okay, so running in 34 milliseconds, which is awesome. And the next word predictions will be this. Okay, so here the next word getting predicted from this is from the match 3, the, right? It says the next word should be the, and then you can retrain it again to see what's the next statement will be. Rerunning this again to find the next word in the story. Okay, something wrong. Let me comment this. Okay, let's increase the sequence size to 20 and see if we can see any improvement in the next word model. Okay, and we can still see like the next word which is getting predicted, the, is not fitting the context very well, because LSTMs need like more data and more training time to actually train this. So again, like LSTMs might not be a good choice to do long-term dependencies. And that's why we need to migrate the model from LSTM to a transformer-based architecture. Executed the code, able to run the code. +1 if you're done. Anyone who is not able to run or execute. Okay, so to recap, what we saw that both RNN and LSTM are prone to vanishing gradient problem and might not behave very good for long-term sequences. But there is one more pressing problem here. One pressing problem here is that the training that we see in both the examples, both in RNN and LSTM, how that training is happening is that, let's say if I say good morning, and we send it to either the RNN or an LSTM block to convert that into, let's say, a French word called bonjour. Okay, for example. So when you do a sequence to sequence classification, right? You first need to give this input to RNN, and then you wait for the output HT. Then you give this morning to the RNN alongside with the HT, and then it will start predicting bon and then for jour, right? So here, while training time, the data is going sequentially. So at the input side here, when you read, so it's just time bound, right? It is time bound. You won't be able to predict the outcome until unless you have actually got the state from all the inputs. And that sometimes can become a bottleneck for GPU processing, right? So currently you will say that, okay, sir, this model is training on GPU, but exactly the data is not getting parallelized, right? So you also need data parallelization. Apart from your model, you also need data parallelization, which is kind of a bottleneck for both LSTMs and RNN. And that's why it becomes really hard for RNN and LSTMs to run on bigger data sets. Okay. I can share one experience that in one of my previous firm, that was a French company. So we had a lot of documents in French. So we thought of creating a French to English translator. Okay. So we trained the model because we had both the French text as well as the English text, and we got some open sourced data set also to do that, and we ran the training. And you won't believe that at that particular time we were using Azure like servers to do the training, and took almost like 2 weeks, 24/7 running to train a model, and that too with an advanced score of 0.712, right? If yeah, that was the advanced score. So not a very great model, but still it was very long time, long training time that we have to wait for. And it had almost like 7 million parameters in that particular model, right? So again, in terms of weights, as we saw, like RNN equations has too many weight matrices, right? So all these got combined to a 9 million parameter model running straight for 2 weeks. And then we did that again, like also, like we were not able to translate uh, any sentence which were more than 20 words. That was a problem again. So we need to chunk it to 20 words and then translate it. So again, like certain limitations. At that time, like transformers were not there. So, but then later on in sometimes it's being asked in the interviews a lot. So why LSTM and RNN are not good? Because of two reasons. First, so this is, I think, one of the biggest concern. Second, both the LSTM and RNN models have too many parameters, so it makes them very hard to train, right? You end up spending like a lot of training time to train it on bigger data sets because of these two reasons, right? So like because of these two problems, like these are not, LSTMs are not a good choice for sequence to sequence task. Then comes the transformer architecture that was introduced in 2017, like very recent. So at a very high level, so one thing that what transformers has done good is that each input, each input, let's say this is the words, goes into the transformer block at once, and the outcome also comes at once, right? So this is where we are overcoming the uh, data parallelization issue. Okay, now because each data can go at one go, right? So we do not need to wait for the outcome or the cell state from this word, which should go inside this, and then cell state from this, which should go inside this, to wait for start doing the next word prediction. Rather, we can give all the inputs at one go, and that can solve for the data parallelization. So this transformer block here might look like a black box. So let's see what is exactly inside this transformer block. So a typical transformer is basically made of an encoder and decoder. So sometimes you will often see in literature that transformers are also called Encoder-Decoder Architecture, ENC Tech Architecture. Yeah, autoencoders. I hope like you guys have done autoencoders in image. No? Okay, some people saying yes, some people no. Really confusing. But yeah, okay. For people like who know autoencoder, it's like both encoder-decoder architecture kind of a thing. So we'll break like these encoders and decoders. What exactly it is, right? When we say encoder and a decoder, what exactly this encoder-decoder is. So if you look at the attention all you need paper, they say that you pay an attention on the word, and it is a plural word, not a singular word. It's a plural word. It means it is not a single block, rather it's a bunch of same encoder layers, right? So we have total 6 encoder blocks at the input and the 6 decoder blocks at the output. So if I expand this further, so this might look something like this, right? So we have 6 encoder blocks, and then we have 6 decoder blocks. Again, now the question is like, what is this encoder block then? So this encoder block is actually this. I don't know if you are able to see this. Let me zoom this. Okay. So an encoder block is actually made up of 2 layers. One is called self-attention layer, and another one is called the feed-forward neural network. So I think this is, we already know, this is the multi-layer perceptron model only. But before this multi-layer perceptron model, we are adding one self-attention layer. So we'll focus our energy now to understand what is self-attention, because this is the key. If you understand self-attention, combine it with the feed-forward neural network, you will get an encoder. You just repeat these encoders 6 times, right? And that will become the encoder block for you. And the decoder block is nothing but it's the reverse of this. So you have a self-attention layer first, and then you have a feed-forward neural network later. So I think now let's focus on self-attention. What is self-attention? So self-attention from the paper is coined as a non-linear function, first of all. So attention is nothing but it's a non-linear function. Linear function. Approximation, right? And the logical intuition of self-attention is that imagine you are sitting in a class, right? You're sitting in a class here, and then the teacher is actually distributing marks to all the people in the class. Let's say there are 62 students, and let's say you receive 75% marks, right? So you got one score for yourself, and then your neighboring people are also getting individual scores. Let's say this person 90. And now you want to make friends with these people. But you say that, okay, I have received a score which is 75. I will only make friends which are important to me, which have a higher score than me. Let's say a person with 90% marks or an 81% marks, right? This generally happens with you, right? You do a self-attention. Not only you just look at yourself, but you also look at what others are also doing. So in the linguistic context, when you look at any word, you also need to look at other words. So the authors actually introduced a concept called attention score. Okay, so each word will get an attention score, which is actually calculated using this formula, right? So the word "the" will also have its own attention score. Animal will also have an attention score. Didn't, right? Cross, all of them. And then any word will look at all the attention scores and get a unique self-attention score. Like it tries to map like which words are important for me and which word are not important for me. And I think this is where the difference is happening between the RNNs, LSTM versus transformers, right? In transformers, in order to look back in time, you were using this equation h of t, but here we discard in transformer and say that, okay, will not require the hidden state, rather will focus on the attention scores in order to compute whether things are important for us or not. Let's see like how we actually compute this, like how the actual transformer architecture is doing that. So we'll break this self-attention into 7 steps. So the step number 1 is to calculate the self-attention. So in order to do this, that's where the attention score comes into the picture, right? So you give score to each word. So if it is important, then I will give like higher attention score to this, higher attention score to this, higher attention score to this, and rest I cannot, and I can ignore. Okay, that's how it is actually remembering which things are important and which things are not. So to calculate self-attention, we need 3 vectors for each word. Okay, so for each word, so let's take one example. At the input, I want to translate thinking as a word and a machine as a word. Yes, it's like it's like a probability score only, correct? But this probability score is getting calculated for each word, right? So how do we do that? We take the word, let's say thinking is the word, we convert that into an embedding, and then we maintain 3 vectors. Like these are the 3 vectors that you need to maintain for each vocabulary. For each vocabulary word thinking, you will have your own unique query vector, key vector, and a value vector. Okay. Then what we will do, we will actually take the in the step number 2. In step number 2, what we'll do, we'll take the dot product of these query vector and the key vector. So at the very beginning, what will happen? This will be initialized randomly. They will have certain like random weights, and you will take the dot product, which we call as score. So it's a dot product between Q1 and K1, right? But for the next word, like if now thinking wants to know how important machine is for me, then what we have to do, we have to multiply the query vector of thinking with the key vector of machine. So here you will see it is Q1 multiplied by Q2. So again, let's say I have hypothetically assumed some number. So it has, let's say 112 and it has come out like 196. So this is the next step, step number 2. Then step number 3 is to divide this score by 8, right? So what we'll do, we'll divide this by 8. And some people will say why 8? Because it is basically the under root of the length of the query vector. So in attention, all you need paper, the length of this query vector was 64. So if you take the under root of 64, this comes out to be 8, right? And then you divide this by under root 8, sorry, 64, which is 8. And let's say this is the one. And then you take the softmax of this value. Okay, so you'll get one particular word. If you go back to the equation, this is exactly what we are doing. So this is step number 1. Okay, this is the query vector. Query vector, getting dot product, getting a dot product with the key vector, right? Then we divide it by the value, and then we take the softmax of this. Softmax is a activation function, basically. Softmax function equation will be something like this. If you know, it is called E x to the power I divided by summation j equals to 1 to k E x j, right? This is the softmax function. Basically, it's like probability only. So let's say if you want to get the softmax, let's say these are the numbers 1, 2, 3, 4, right? And you want to convert to the softmax value. So you will take e raised to power 1, and then you will add e raised to power 1 plus e raised to power 2 plus e raised to power 3 plus e raised to power 4, then comma e raised to power 2, and this denominator will be common, and this will be the softmax output. Okay, so this is the softmax activation. Yeah, so step number 3 was this. We take the softmax, and after that, what we do, so we multiply, we again take the dot product between this and the value vector v1. So let's say if your v1 is 1, 1, 1, and if you multiply this with 0.8, the resultant value will be 0.8, 0.8, and 0.8, 0.8, and so on and so forth, right? So this is the score. This is what we call it as a score. So if you take the next step, right? So this is the complete picture of the calculation of your attention score. So we take the word, get the embedding, generate its 3 vectors with what is called query vector, key vector, value vector. Take the dot product between Q1, K1, get the score divided by the length of the query vector. Take the softmax, multiply the softmax value with the value vector v1, and then this is what will be the output, and we call this as the attention score. This is the attention score for this particular word, thinking, right? So this value actually contains now, if you see it very clearly, so the intuition of doing like the softmax is to keep intact the values of the word that we want to focus on, and the irrelevant words will be drawn out, right? So if the value of the softmax comes out to be 0.0001, then that particular word will automatically shrink out from the value. These will be initialized randomly, right? So similarly, imagine like how the multi-layer perceptron weights are getting adjusted itself for the task. So when you will use transformer and you will do a supervised training or an unsupervised training, then these query vector Q1 and K1 will take its desired value accordingly. So the actual values will be random. Initially, it will be initialized as a random vector for us. How many this Q1, Q2, Q3? As I said, that each word in your vocabulary. So let's say we take the same example like this, the Virat Kohli one. Okay. Here, each individual word which you see in the data will have its own individual query vector, key vector, and a value vector. Okay. So if you have 1000 words, then you will have total how many vectors? 3000 vectors. And since these are vectors, what we can say is we can write this in the matrix notation, and each row is one word for us. So let's say this is word 1, and word 1's query vector Q1, word 2 query vector Q2, word 3 query vector Q3, and so on and so forth. So you can write it in a matrix notation. Then we have word 1's key vector, word 2's key vector, word 3's key vector, and so on and so forth. Then this is the value vector for word, again, for all the words, right? So it will going to be a very big matrix. And then we take the dot product between the query matrix and the key matrix divided by the length of this query vector. So this length, whatever length you choose, take the softmax, and after that you multiply it with the value vector, and the resultant value is what you get as the attention scores. Attention scores are getting created. Now, there was one more concept in the paper which we talked about, is called self multi-head attention. So this is called self attention, right? The vector that you are actually getting is for one word, like for all the words, but there is another concept which is called as multi-head attention. So it means like as you have got one attention vector, you will create multiple attention layers for this, right? So the intuition to understand this is, let's say you have a picture, okay? You have a picture, a colorful picture. Then you put, let's say, a red glasses, which are red. And now all the areas in the color in this image where it is red, it will actually pop out, right? It will become much more visible to you. Or let's say the other colors will become much more visible to you, right? The red ones will hide away. Okay. So imagine like this, putting a red color sunglass is one attention matrix. Then you put a green one, let's say. So now what is happening is that the attention layer is able to get the bigger picture also. So far you were actually looking at the one word here, but now your attention will have few more layers looked at from different perspective. Okay. So maybe if you use 3 attention layers, then you will have, let's say, 3 different ways to look at the same scenario. Okay. That's how, like, linguistically we can think of. To use only for finding the attention score, let me think. What could be the drawback? One drawback of using this would be that though you have got the attention score from this perspective, like it, right? We are not combining how it will behave with other words kept together with multi-head attention. So multi-head attention is nothing but you maintain more, let's say, query vector. Instead of having a query vector, now you will maintain. Yeah, so this is how your multi-head attention look like. So for each query vector, for each word, will maintain, let's say, one. So as we know, like this kind of a situation will create one kind of an attention score. For the same X will create another set of attention score. Okay. And now you can attach like multiple heads to this. And each, so the question will be like, why we are actually calculating the attention score again and again? Wouldn't it be like same? So the answer to this would be, will spacey word vectors will be no. It depends like what kind of word model they are using, right? So the word embedding that spacey uses is word2vec. It's not transformer based. Different attention score. So the idea of having multiple head or multi-head attention was to look at the same data with a different perspective. Okay, as I said, imagine like this, calculating this attention score is visualizing a picture with the red color sunglasses. Then the same data, the same picture is then you view with the green color sunglasses. Then same picture you then view with the, let's say, a blue color sunglasses. Now, when you look at from the red specs or the red glasses, red regions will get hide out, right? And other colors will pop out, right? So you will get like more information. Okay, so that's why multi-head attentions are used within the transformer blocks. And then how does this is works is complete multi-head attention block. And this looks something like this. So for each word, this is what we already know till this point. Like for this word, this was the self-attention layer that we were actually calculating. Self-attention for the same word, thinking. Then we calculated the another self-attention layer, and then we stacked them together. Right? We stack them together to form what is called as a multi-head attention. So again, this is going to be give you a same similar Z-score, but now you have different attention blocks getting stacked together for same word. RNN might not be, or LSTM might not be good for natural language tasks. Other than that, wherever you feel that the sequence is important for you, for example, in stock market prediction, then these are one of the best one, because you don't require like so much long-term dependencies there as compared to in natural language. So the I'll say the comparison that we are trying to draw here between LSTM and transformer is purely based on natural language tasks. So now I think we need to stitch the entire picture, which is, now we already know that for each encoder block, we have the self-attention layer and the feed-forward neural network. And this is what the illustration will look like. I had so how this the transformer blocks work. So you get the input, right? You create embeddings, and these embeddings go into the encoder block. Then the blue ones here, these blue ones are the attention scores that you're transferring. Okay. And this goes to the encoder block, and the final encoder block here, whatever will be the block, the outcome of this will, so each encoder block will output a different attention score. Okay. Because input to this is an attention score, and output of this encoder block is again going to be an attention score. And this output attention score will then get distributed to all the decoder layers in the transformer architecture. Goes to the next encoder block. Then we create the final, like the query vector and the value vector, which gets distributed to all the decoder blocks. And one by one, the decoder starts to convert that. And in the end, the decoder block. So these decoder blocks are also reverse of encoder, right? They are also generating the same attention values, similar attention values, not same attention values. So what is BERT? So BERT stands for bidirectional encoder representation from transformer. Eventually, it was developed by Google AI in 2018, and it serves like a Swiss Army knife, because for the very first time, we could use one single model that was capable of doing like most common language tasks, like for example, sentiment analysis, name entity recognition, question answering, language translation, text summarization, text classification, right? This all was possible because transformer model enabled us to have embeddings, right? Which sits between the encoder and the decoder, and it enabled transfer learning for the first time. Now you can actually extract knowledge about any language, or in other words, we can say features that are now encoded inside some representation. And then that knowledge can be used to do multiple tasks, right? For example, if you have known this in transfer learning in image recognition, then what we generally do is that we train a model, an image model, to extract features. Now, these features, once the model understands like how to recognize eyes, or how to recognize vertical lines, horizontal lines, or blur, or whatever complicated feature, then you can use that learning to perform other tasks. Similarly, in language, when we say NLP, uh, transformers actually enabled to extract those knowledge from the text, and then we can make use of that extracted knowledge to perform the tasks that we generally are aware of about in natural language processing, which are sentiment analysis, named entity recognition, and so on and so forth. A Swiss Army knife solution is means like one single model. Like, have you seen a Swiss Army knife? So what does a Swiss Army knife looks like? It's like this. So like a one single, knife has a saw. Yeah, it's a single man army kind of like a thing, right? So it has a nail cutter, it has a saw, it has a screwdriver, it has a knife, right? So one single thing can do multiple tasks. Similarly, like BERT enabled a single model enabled to have multiple tasks. So eventually, the BERT model was trained on a massive data set, which was 3.3 billion words. And the training corpus actually included the entire Wikipedia that we know today, which almost had 2.5 billion words, and Google's book corpus, right? So Google have also its Google Books, if you know, right? They have transpiled collection of various books. And if we combine that, that was around 800 million words. Total was roughly around 3.3 billion words. And then we trained this using a transformer architecture on a 64 TPUs for the course of 4 days. And the model that got trained is called BERT model. And we're looking at transformers. So a transformer architecture is a collection of encoder and encoder and a decoder, which has the attention block inside this encoder and the fully connected neuron. In BERT model, we only utilize the encoder part, right? We are not utilizing the decoder one. So BERT is just a collection of encoders only, right? Because you at the end of the encoder, you get some weight matrix, which is act as an embedding for us, right? And then this embedding, we can say, has learned everything about the language, and now we can do multiple tasks with this kind of embedding, right? So in another words, you can also understand this as we have extracted the features out of the language, and now we can use those features to do multiple tasks. Okay, but over period of time, like the BERT model was very popular. Why it was popular? Because it actually superseded on many of the benchmarks. Okay, so there is what is called as glue benchmark NLP. So if you look at that, so it's like a collection of various data sets that can do sentence classification, question answering, right? So this glue benchmark is quite popular. So any new model which comes into the domain has to have performed on the glue data sets, and then people are actually competing to perform better than the previous glue benchmarks. So BERT at that time was very better than what you see with Word2Vec or any other language encoding models. So BERT was outperforming them by a good margin. That's one, I'll say, misconception that people have, that encoders are LSTM. No, that's what the transformer architecture told us, that you really don't require an LSTM model or an RNN model to have long-term dependencies. Remember? Because to do so in RNN or an LSTM, you need the previous state equation, which was something like this, right? HT minus 1. And in the entire transformer paper, we didn't had anything which tells about the previous state. So we are not looking at the words as sequences of in time anymore. And that's what actually the transformer model actually talks about. Okay, so don't confuse encoder as an LSTM model. So encoder is basically the encoder block was self-attention layer. So we had the self-attention layer in the encoder block, and the outcome of this self-attention layer goes to a fully connected neuron, FCNN. Okay, and that complete actually corresponds to an encoder. This we call as an encoder. So it's not an LSTM. So coming back, so like BERT was very popular because it actually performed very well on the glue scores. So there was a high demand to have smaller versions of BERT because it was very difficult for people to actually have like 64 TPUs to do inferencing or do other tasks, right? So in 2020, a lighter version of BERT, which is called as distal BERT, was offered, and that was 60% faster while maintaining the 95% original BERT performances. Okay, so going forward, we will look mostly on the distal BERT, right? Because distal BERT is something you can actually infer on your local machines also, or maybe in Google Colab. So how does this BERT actually is trained? Let's look at that. So BERT uses a masked language modeling technique. So this is something very important. What is masked language modeling technique? It means that we will enforce the bidirectional learning from the text uh, by hiding certain words in the sentence, and it will force the model or the transformer architecture, because like how the attention blocks were, attention layer was looking at. So if you remember that example, okay, I think it will be good if we bring the transformer. So if you remember this slide, that each word actually has now the ability, because of this self-attention layer, to look at all other words and give it a score, right? Now, in the masked language modeling technique, what we do, we hide certain word, right? And we call this as like a mask, and then forces the model to actually predict this word. So can you guess the blank word here? What could be the blank word here? And why did you say learn here? Why not any other word? Because now your brain has actually looked at from left to right, and then also from this direction. Okay. So you're not only looking at the first context like this left to right, but you are also are actually scanning through this text. Like that's why it is called bidirectional. So the word bidirectional in BERT is this, right? So we force the model, because now since we are masking it, uh, the attention scores are not only just calculated for these words, but they are strongly calculated for the other words. Okay. So in BERT training, what we do, we hide 50% of the tokens randomly, and then we ask the model to actually predict. So a typical BERT or any large language models are not supervised models, because it will otherwise will require a lot of manual data. But imagine like you have very big book, right? And now you need to learn the information from that particular book. So in order to learn that context, or let's say the information which is captured inside the text, what we do, we make use of masked language modeling technique. So we actually sometimes 15% or we make 50% of the data masked, and then we ask the model to actually predict. Now you already have the true label. So let's say you're correct that it is actually learn. But when you have, let's say, the sentence like this, so you can hide like data from here, and you already know the data. So this is becomes your target variable while the training, and the output will be what model will predict, right? And you can then self-correct that using some loss function, and that's how the training is actually happening. Of course, like it not only uses this one, we'll talk about another scheme. So a BERT uses basically two schemes to do this training. So is the masked language model or this masking technique clear to everyone? Okay, so let's quickly also see that in action. So everyone, please open up your Google Colab. And going forward, please use Google Colab only, because we will be actually downloading a lot of models. And since Google Colab has better speed, so don't try to run this in your local. Otherwise, like you will be limited by uh, the downloading speed. Like, so it's the label creation is not supervised. Okay. So when you get the data, uh, or let's say when we are creating a general embedding, we generally do that in mass language format. Okay, so try changing the sequence length there, because I think by default we were only using like 10. Try changing the sequence length to 20 or 30 or 15 or something, and then see if the next words is different or not. Okay. So I just quickly wanted to show you like how this mass language model actually is working. So in Hugging Face, we have a pipeline that we can actually utilize to see that in action. We'll import pipeline from Hugging Face. And I'll call this as unmasker. We'll define the pipeline, and here we will use fill mask. Okay, Hugging Face. Okay. So Hugging Face is a startup that actually holds all these large language models. Be it be BERT, be it be GPT-2, GPT-3, I think, or Llama, or any other. So it is actually a repository that actually has all these pre-trained models. Okay. And it also offers an external API, a Python API, to actually connect to these models. Okay. So it's a very good library where you can actually download datasets. You can download models also. And you can also get some wrapper APIs to do certain tasks like image translation or image classification, object detection, image to text, image to video. Like all these are supported on Hugging Face. So the transformer, the package is actually maintained by Hugging Face itself. Yes, they are open to use. But see, when we say open to use, it means they are open source, but there is one slight catch. Open source also have two kind of licenses. One is called as MIT license, right? I don't know if you guys know it. So if you go to pypi.org, okay, and let's say search for transformers, or let's say NumPy, right? I think everyone is aware about NumPy. So if we click on NumPy, there is a license detail also about this, right? So what kind of license it holds? So it's a BSD license. So generally BSD licenses are approved for commercial purposes, or Apache 2.40 licenses, right? So anything that has a license Apache 2.40, it means you can use that model to actually generate income in your company. But if the license is MIT, okay, or any other license apart from Apache 2.0, then it means that you can use that particular package, piece of code, or the model for learning purpose, but you cannot generate income from that. Okay. For example, let's say if there is a model like BERT model, it's generally MIT license. So if you want to generate, let's say you create one, you fine tune that BERT model. Okay, again, like there is a debatable question: is the fine-tuned model is your IP, or it remains the owner, the original author's IP? So the fine-tuning actually removes that IP constraint. But if you use that model as is and start generating, let's say, income, you created, let's say, some software and people are paying for it, then the original authors who had claimed this to be an MIT license can sue you and say that, okay, uh, you have infringed our IP. So be very careful. I think as a data scientist, we really don't look at these things. But later on, when things become commercial, this can create very serious problems. Okay. So always work with, I'll say, open source, truly open source models. Right. So I think that's a very good debate also happening currently in LinkedIn. I don't know how many of you are following that, but people are seriously talking about that. Facebook releasing llama models, right? Or Google releasing the gamma models, right? All these are not truly open source, right? You can use them for academic purpose or learning purpose, but you cannot truly use them for commercial purpose. Okay, then what's the point of saying that they are open source? They're not open sourced. Right? And when we say open source, also like you are giving the entire code and the entire weights. Again, like it's a different I think a debate, but yeah, Hugging Face actually stores like all open source models, but again with different licenses. So be very mindful of those things. But if it was safe to use Hugging Face if we try to use this on confidential data, yes, okay, you can use this to build your or do some training on your data because nothing is going to the Hugging Face portal until unless the model is downloaded locally. Okay, so we'll import transformers. We will use so in transformers there is a very interesting sub package which is called pipeline, and using this pipeline you can do like wonders. One such pipeline is fill mask. So if you run this, I think for many of you this might be running. For me, it's running will be treated as a different IP or not, right? So still that debate is happening. Okay, fill mask is the same thing that I'm trying to show you, the masked language model. So here, what the model will do, it will try to predict the masked word. Okay, so if I try this, Indian masker, it will predict a few legitimate words for me, like learn here. So it says learn has a probability 0.69. Then use can also be fitted in here. And I think if you use the word use, then it also is making sense, which is like I'm trying to use Python. Teach is also something which is a legitimate word, which is I'm trying to teach Python language to get. And you can clearly see that this has a better performance, right? And in understanding the words, not only just here, right? So if you remember, like what we were doing in RNN, right? We were predicting the next word here, right? So if we now try to predict this using this unmasker, right? So it is performing way better because due to two things. One, that it is using like more data to predict because it's trained on entire Wikipedia. So it has like better context. And now you can think of how it has have learned the long-term dependencies. So Wikipedia pages are sometimes very long, right? It can even span to 5,000 word paragraphs, right? And still like it's able to hold such information, right? That's the beauty of was transformers was, right? And that's how you can clearly see the difference now with LSTMs and with transformers. So everything, because it is using self-attention mechanism, right? With LSTMs or RNN, you had to compute or you had the vanishing gradient problem. That's why you could not go very far beyond in the time. But now with self-attention block, you can actually, yes, but also at the same time, you are enabling uh, parallel data distribution also, right? So these two things actually accounted for better performances on transformer model. Okay. Masking for multiple words, you can give it a try. I think not possible because it will otherwise will get confused. Okay. So, but now you don't know which mask it is actually talking about. You can actually do that. It's not a problem. But then how will you distinguish uh, that which mask belongs to which prediction? Okay. It will surely work, but it will again create a confusion for you. So while doing training, we only mask one word at a time, not multiple words. But since the model, the moment it sees like this token, which is this mask token, it tries to predict that word. But then it will create some disambiguity for you if you have multiple masks here. No, mask 1, mask 2, it will say that this word is not found. Okay. So you need a mask token. So mask is a like a, you can say, a reserved word for the model to understand. Got it? Has everyone tried this? Okay. So here, when you did or executed this line of code, it actually downloaded the BERT model for you, right? And which BERT model actually it used? It actually used Roberta for masked LLM. Okay, this is Roberta is also one kind of, you can say, a transformer model. But let's say if you want to use uh, the original BERT model, so you can say BERT cased, BERT base, uncased. So now the BERT uncased model will be used here. And strangely, if you run this using the BERT model, right, this will not work because the word mask is used like this with a capital M, right? So since it's a cased model, so you need like this mask token, right? So the token is the differentiation here. So what I was saying that if you just use fill mask, the default model that gets downloaded is Roberta model, not, so it's again like a more refined version of BERT. Roberta was again like published later on when the BERT model. But if you want to work with the original BERT, so you need to provide the model. You can also say model equals, right? BERT base uncased, and this will actually download the original BERT model. Okay. Okay, let's go back. So this is one such scheme of training. The other scheme, pipeline, is nothing but it's an API layer on your Hugging Face models. We'll decode this later. Just wanted to show you like how the mask language model actually works, right? Score is the probability score, right? So here, uh, the probability of occurrence is 25 that this word is going to be A, right? I'm trying to learn a language to get a job, right? So the score is nothing but the probability score of the prediction. Okay, coming back. The second scheme in which the BERT models are being trained is predicting the next sentence itself. Okay. For example, uh, you already know, like you have the pair of words. When you start training the model, you already have bunch of sentences. So what we do is that, okay, let me do some annotations. So let's say this is one line, then there is the another sentence, then the another sentence and another sentence. Now you actually make a pair which says that if we take this pair and we already know the true labels, like if this is the sentence and this is the next sentence, uh, if we simply just ask the model to predict the entire sentence, whether the new sentence what the model predicts, right? The new sentence what the model predict, is it exactly same as the sentence that was hidden, right? So imagine like this, as in the mask model, you were masking the word, but in next sentence predictions, you are asking to predict the entire sentence, not only just one word. So if the model is able to perform like the or even to predict the next sentence entirely correctly, we say like this is a win situation. And if it's not, then it's an incorrect pair. And while training the BERT model, the actual BERT model from the paper, they said they used 50% of the correct pairs and then 50% of random sentences, right? To increase the sentence prediction. And BERT is then trained on both of these schemes, right? It is trained on masked language models as well as NPS. So MLM and NPS together is applied while the BERT training. Okay, not only just one sequence, one scheme. NPS is next sentence prediction. NSP, sorry. Okay. So BERT sizes, as I said, like this BERT is nothing but an encoder only. So this is the encoder, typical encoder block that we remember. It has self-attention layer, and then it has a feed-forward neural network. So if you combine these encoder 12 times, right? So if there is an encoder, let me call this as an encoder, and 12 of these such encoders, right? Encoders actually creates what is called as BERT base. So if you go back to the model here, remember I downloaded BERT base, which means I am looking for the model that has 12 encoders in it. If I make this large, right, again, the size of the model is going to increase, because then I will have a model which will have 24 such encoders. And remember that each encoder block will have like its own weights and matrices. Imagine if you combine 12 such encoders, so you will end up having 110 million parameters. So in today's world, you will see that all these big models, you will say that, okay, the GPT model is 7 billion parameter or 32 billion parameter or 178 billion parameter. What exactly you are doing, you are just increasing the encoder layer, right? You are increasing more encoder layers in it. And that's how the number of parameters, the learning or trainable parameters also increases. Okay. So be very cautious about which type of base model that you want to actually use. If you use smaller models that will have lower parameters, it will be easier for you to fine tune them. But if you use a big model, let's say 340 million parameter or a 1 billion parameter model, fine tuning those will be very time consuming and cost expensive, because then you will need like more GPUs to actually fine tune it. How these transformers handle so many parameters? Because remember, what was the biggest advantage transformer brought? What was the biggest advantage transformer brought in terms of LSTM or RNN? Okay, let's ask this as a quiz. Attention layer, okay, that is good. Attention layer only is a substitute for long-term dependencies. Yeah, that you can also handle with the exactly parallel processing. Parallel processing of data. That was the biggest advantage with transformer architecture. And now you can actually use data like parallel data processing, which can be enabled using GPU. And that's how these parameters are being handled. So imagine like all these training is happening on one different GPU. So you can literally do the training of this. So as I said, like these are 12 encoder blocks, right? 12 encoder blocks. So this can actually run on one GPU. This encoder can run on a different GPU and a different GPU and different GPU. And then these GPU can actually communicate with each other to share the data, right? Or doing matrix multiplication and addition and so forth. So that's how it actually uses GPU computations to handle such large sizes. And that's why over the period of time, because now people have started training massive data like entire Wikipedia, they require bigger GPU machines. Okay. So GPU machines like H100. So this was the H100 CPU machine, which was actually used to train your chat GPT models. And look at the price, like you will be shocked by the price, H100 price. So it's somewhere around, I think, $25,000 and convert $25,000 to INR, almost 20 lakh rupee for one GPU. And these H100s, actually, they have, so NVIDIA stock prices actually started booming because uh, Facebook, Google, and OpenAI both now require these GPUs to handle bigger models. So everyone is now in a race to build the massive model, and they're trying to defeat everyone, right? So the earlier ChatGPT model was 1 billion parameter, like sorry, 7 billion parameter. Then it came like uh, even more bigger parameter model on even more bigger parameter. So there is no limit, like there is no theoretical limit on how many big parameters you can have, because all you just need is to increase the encoder size, right? So if you have 24 encoder, let's say you say that, okay, it's now my wish, I want to add 100 layers of these encoders. Now, in order to support this 100 layers of encoders, you need more GPUs, right? So there is a GPU farm which will actually run this, right? So that's why like NVIDIA is becoming super rich right now, right? Their stocks are booming because everyone is now in a race to buy the GPU and do that training. Yes, there are models, right? That's why I think, again, like we are going into a different debate, like is 12 billion model not sufficient? Is it bad? Is it bad at doing things, or is it bad at doing things? Okay. So if you go and download a large model, right? So let's do that. Download it. I think it's almost like 1.4 GB model, since it's much more bigger. Okay. And it will still be able to predict what you could have predicted with a base model, right? It's still predicting A here, right? I'm trying to learn a language, right? So I think the important point here is that there is no, we'll say, like a rule that you should not use big models or you should not use small models, but it all depends on the use case also sometimes, like what kind of use case you are running. Okay. People wanted to have more parameter models because the more parameters when you increase, right? So, okay, let me tell you what exactly is happening there with the GPT models. So the earlier GPT model, right? If you see GPT-2, then got advanced to GPT-3, which is actually the base for your Chat GPT, the initial Chat GPT that they released. And GPT-3 was very good at generating like new text, but it was not able to do mathematical calculations. Okay. So if I give 2 plus 3 equals, right? Now, if like see the like irony here, that we are not looking at, so this is also a next word that it's want to predict. So it's a prediction, not a calculation. Okay. So what the model is treating, it is treating this as a new next word to predict, but it's not calculating this, right? So that's why people said that, okay, if we yeah, this uses this as a string. So sometimes it might say 8, sometimes it might say 6, because it is actually a next word predictor only in the end, right? So that's why they are trying to increase the number of parameters so that they can tap inside, see, or and tell me like where exactly the intelligence is actually happening. It is actually happening between these encoder blocks, right? We saw that the intelligence is actually captured inside between these encoder blocks. So if you increase like more encoder layers, so what it is saying that it will capture more intelligence. Okay. So in order to capture more intelligence, you need to increase the encoder blocks, and that will actually increase the number of trainable parameters. So that's why like people are going crazy to build like more larger models, right? Uh, but yeah, I think there are also very good studies which says that if you keep on increasing, there is some level of saturation will happen sometimes, and you will not be able to extract information because information will also saturate at some time. If the data increases, won't it increase the processing burden? See, data is also one aspect of it. Saket. It is being speculated, right, that for building these ChatGPT models, they have used the entire internet, right? So the scheme that they actually used is they went to Google, right? Whenever you do, uh, let's say Harvard. So when you do a Google search, Google actually gives you these pages. So what ChatGPT did, it actually scraped out the top 10 pages of all Google indexes. And that was the data for them to be trained on. Unlike BERT model, which was just trained on the Wikipedia dataset and the Google book corpus, ChatGPT actually trained it on top 10 pages of Google itself. I don't know, like they simply just scraped it out, right? They simply just scraped it out because you cannot, because it's a search engine, right? You cannot uh, disallow a person to use a search engine. So that's totally fine. Even Google doesn't own the web page. So when you see here, like there are many web pages, uh, Google is just showing you the web page information. So the web page, so when you click on that, Google doesn't own this particular page. So now anyone is can actually scrape this information out. So that question was out of the picture. Okay, coming back to BERT. So we have different sizes. So remember what these parameters are. These parameters are nothing but the encoder block that here. These encoder blocks had these vectors, right? These vectors. And if you count the dimensions of these vectors, this will go crazy, like 110 million parameters. Okay. Now, how does BERT works? So just like your vanilla encoder of the transformer, the BERT actually takes the sequence of the word as an input and keep flowing the outcome of the encoder, which is nothing but, okay. So the attention scores keeps on flowing inside these encoders and you will get the outcome. So each layer applies self-attention, pass it to the result through a feed-forward network, and then hand it over to the next encoder layer. So now let's do some classification using this BERT model. Right? So let's use this BERT model to do certain classification. So everyone, please open up your Jupyter Notebook instance. Another one. So for this, we will use one data set. Let's do sentiment analysis using BERT encodings. So we'll read this as a pandas data frame, pd dot read underscore CSV, and we'll directly pull this from uh, a GitHub repo, right? So this is the GitHub repo that actually contains some text, and corresponding to that, we will have some labels. So we'll put it here and we'll tell that this is delimiter as /t and header is none. Okay, so the data frame should look something like this. Okay, so I think this is the movie review sentiment. So 1 means a good score and 0 means a bad score. So what we'll do, we will actually now download the BERT model. So we'll do from transformer. Okay, let's import transformer directly. Import transformers. This might take some time. Cool. Now, so when you download this, right, there is there are a few things that first get downloaded. One is the vocabulary text, right? So if you go and check this out, here somewhere in the config, you must find okay, maybe I need to search, but yeah, here you will get the model itself, the parameters of the model. Like these are the weight matrices, tensors, and you also need a tokenizer. So for any Hugging Face model that you when you download, right? So you need to actually grab the weight of the model plus the tokenizer. So what we'll do, we will actually download this. So we'll say model class and then tokenizer class and pre-trained weights from the distal BERT model, distal BERT dot tokenizer, and which model that we want. We want it for the distal BERT. Remember, like distal BERT is the smaller version of your BERT. Okay. Now, the first thing that we need to do is to convert this text into some sort of encoding representation by the distal BERT. So how do we do that? So tokenize these sentences and convert the sentences to encodings. So a typical like how do we can actually use df dot tokenize sentences, and that will be equals to df. We are looking at this column, which is the 0th column, and then we can use pandas apply function, and inside that we can use lambda. Okay, I think I can go with the intelligence. It tries to, no, I think this is wrong. This should be lambda x apply tokenizer. Okay, I actually missed one thing here. Let's first get the tokenizer for this BERT model, which is we get from the tokenizer class dot from pre-trained, and we give the pre-trained weights. So the tokenizer gets initialized, and then we will also initialize the model. So the model will be from the model class dot from pre-trained weights, and now the model is also initialized. And after this, we can create a new column which is called as tokenized, and this will be applied on your df0. We'll use a lambda function to call this tokenizer and use a function called encode, take all the sentences one by one, give it to the tokenizer.encode, and add special token equals true. I'll tell you like what exactly this means. So let's try to run this. I think it shall take some time because we have quite good amount of data here, which is df dot shape, almost like, okay, it's done. So we have total like 7 K records. So now if you look at your df head, so it has actually tokenized this right +1. Okay, let me hide some of the print statements here so that everything goes in one line. I think after doing this, you need to write step number 8, 9, 10, and 11. These are the model size. So this distal BERT is a 628 MB. and this is 466 KB. So this is MB and KB that we are talking about here. Yeah, size of the models, correct. Okay. So here you will see that your sentences actually got converted into something, okay, which is as good as doing this. So let's say I write this, for example, I love Python. It will actually encode, and you will see that what it has done is it has encoded I into some vocabulary ID, and Python did this, and then you have two extra tokens here. These are the special tokens that we are talking about. Okay, so your encoding scheme, no, it's not padding actually. It's a special token. So this is like, it's called a CLS token. It's called a CLS token, which is used for classification. Okay, and this is called separator token. It means like there is another word after it. But one thing to be remember here is that the tokenization here, when it happens, it's not a word tokenization. It's not a word tokenization. Basically, what we are actually aware of from our classical machine learning. In BERT model, there is a different tokenization algorithm which is used, which is called as word piece algorithm, word piece tokenization. But for now, remember that the tokens that you see here, these are nothing but tokens. These tokens are not generated by just splitting up the word, right? Like a string, funny, comma, and, right? These are not the tokens. Rather, we use a different tokenization strategy, and there is one algorithm which is called as word piece algorithm. So we have tokenized the sentences now, right? So let's run it through our Distilbert model. So for in these each sentence, right? So let's say if I write like this, I love Python language, you'll see that it will have like more tokens now getting added, right? But for any machine learning model, you actually need a consistent tokens. Okay, so maybe let's say if you keep a token length of, let's say, a sequence length of 60, it means like if converting to this sentence, I love Python, it will have 104 5 and so on and so forth, and 102. Rest remaining 55 tokens will need to be kept at 0, right? So that's what is called as padding. I think you guys already know about padding from image processing. So let's do that. So we'll add some padding here. So we'll define one max length equal to 0. So in this sentences, whatever is the max length that we will find, we'll do the padding, or we'll get the padding length for them from this. So I will loop through all the DF tokenized, right? And if my length of that vector or this list is greater than my max length, I will assign just the max length to that. And this will actually give me what is the maximum length of the sentences in my data set. Okay, so you can check the max length now. So max length is 67. It means we need at least 67 values here, and rest remaining will be padded to 0. So we say that, let's say, padded equals np.array I plus 0 max tokenized dot values. We need to import numpy as well. Okay, so I think the padded information, what you will see is something like this now. So each sentence will be now a 61th length long. Like this will be the length of 61 and rest remaining will be the values itself. So max length is nothing but, see, here we don't know what is the length of the sentence. This sentence lengths are varying actually in nature. So we basically what this piece is doing, it's actually finding the max length of the sentence, like how many words are there maximum in the sentence, and that will becomes the max length actually. So we are actually iterating over all the tokenized words and grabbing the length, and whatever is the maximum length, we will then pad it accordingly, the remaining of the tokens. Got it? Okay. So also we will need to, if we give all these values, like which are the padded values to the BERT model, it might get confused. So let's also have some labels. We'll say the attention mask. Wherever the padded information is equal to 0, we are just keeping the track of that. So it act like a flag. Okay, basically. So the attention mask here, if we take the shape. Okay, and now let's do some modeling. So encoding all the tokens with digital BERT. So we already have the model. So we'll get the input IDs with, we'll convert these padded information. So far, I think these are NumPy arrays. So first of all, we need to convert that into tensors. So we will use import torch, and we'll call this as input IDs is nothing but torch.tensor, and we call this as padded. So this will convert all these NumPy arrays into torch tensors. And now you can actually put these torch tensors into the model. Also, I think we have used the attention mask, so we can get the attention masks also converted into torch tensors. Okay. What if we don't pad? If you don't pad, then you will not have consistent input sequence, right? Then you will have a variable input sequence length. That will be a little problem, right? You need like you can say a fixed input sequence length whenever you give to a model. Okay, so attention masks are nothing but these are like a flags where wherever you have kept 0, right? The padding information. So actually this will hold the indexes of wherever there is a 0. That's it. So we'll do torch.nograd. Okay, then we can give these input IDs to the model. And remember what is model? Model we have defined as our digital BERT. So we'll give that, and the attention marks needs to be given to the IDs, wherever it is like 0. So we'll grab that. So it might take some time to run. So now each row is rows tokenized words are now going into the digital BERT model, and it's now actually predicting what kind of encoding it will have based on its pre-training. Okay, whatever it has learned during the training process, because we are now using transfer learning to grab the features here. Okay, so maybe movie sentence review, this data set was not part of the digital BERT training, but now you are actually kind of using that information to encode. Assume this like a word to vec encoding, right? Okay. I think it will take a lot of time, and my RAM is also getting shooted up, almost consuming the ones. So instead of, so like, since we are not on GPU, what we can do, we can actually restrict this DF to some, let's say 1000 or 2000 rows, right? Otherwise, like, it will keep on running for long. So let me quickly do that. So tokenization is okay, but here exactly what I can do, I can restrict this to have df dot head 1000. Okay, so let me kill this. Okay, I need to restart the runtime. So when you will be running this again, you can remove this limit. Like, so we are just taking 1000 rows to optimize the run. Yeah, I have to run this again. We'll see. It's a time consuming process. Yeah, it's still taking some time. We can also change this to the TPUs if you want. Let's see if we can get some speed up there. The only change that you need to do will be that you need to pass this to CUDA. This also to CUDA. And the model also to the CUDA, where we have defined the model. Yeah, here, dot CUDA. It's in 3 places. Let's rerun this again. So now this can run on directly on the T4 GPUs. Let's see if we get any performance improvement. It should be always done at the input, the data, where exactly is, wherever is your data and wherever is your model. So I think that happened very quickly. You can see. So that's the advantage of using a GPU, right? So we already have, like, say, some good GPU there. So the training, sorry, the inference happened very quickly. So now these are the last hidden states. And if you go and check the last hidden states here. So the shape of this is going to be a 3-dimensional tensor, right? So what does this exactly means? So this exactly means is that you have 1000 rows, like 1000 rows. One, two, till 1000. Then 59 is basically the maximum sequence length, right? So remember, like last time it was coming out to be 67. So 67 was the maximum length, the max length. But this time, since we have reduced this data frame to only 1000, so that's why the maximum length coming out to be 59. So this is going to be 59. And then we will have the outcome here, the hidden units, like these will be the hidden units. And we have 768 such dimensions in this, in the third dimension. Okay, so this is the hidden unit output. And what we are interested in is the CLS token. So remember, right, when you started the BERT model, we had 101, right? So this 101, which is at the 0th position, right? This is at the 0th position, is actually the encoding for all your sentences. Okay, so that's why we will only fetch out the 0th position last hidden state outcome. Okay, so the features basically that we are looking for, the features will be nothing but the last hidden state 0, and since it's a 3-dimensional image, we'll take all the rows on this dimension. We will only take the CLS token, and we will take all the values from the 3rd dimension, and we'll then convert that into a NumPy object. Okay, we first need to convert that to item and then to NumPy. So whenever you want to do that conversion back, okay, yeah, this is, we can do like this also. We first need to detach this from the GPU, attach a CPU, and then convert that into a NumPy object. Okay, now if you look at the features, no, we don't need to reshape actually, because now NumPy is not running on GPU. Okay, so you need to first detach it from the GPU, because we are using a GPU inference here, and then convert back into NumPy. So this is the features that we wanted for all the input sentences. And now we can say like these act as input labels. So the target variable is nothing but the df1. And now we have both feature and target variable. So either you can actually do like a scikit-learn based logistic regression model, because it's a binary class classification problem. So we can either do that, or you can also make it as a artificial neural network. So that can also be done. So we'll probably just in interest of time, we can do this as a binary class classification using logistic regression. So we'll just recall our knowledge from scikit-learn dot model underscore selection, import test train split, train test split, sorry, train split. And what we'll do, we will actually get X train, Y train from the features in the target. Our test size will keep it like 80-20. So we'll have 800 samples for training and 200 sample for testing. For the model, we can get it from scikit-learn leader model logistic regression. We'll define the model. Silo.fit, X train, Y train. And then probably we'll also need to evaluate the model. So what we'll do, we'll first do the ypreds equals clog.predict x test. And then we'll use from sklearn dot metrics import accuracy score, and the accuracy score y test ypred should be 82%, right? We are using just 800 samples, but if you run it like on more data, you should get a better accuracy. Let me just clean this code a bit. We'll keep it here. All the import statements we'll keep here. So this is the piece of code that you need to run. So the word piece algorithm, in the word, as I told you, like the tokenization that you see in BERT model actually uses a word piece algorithm. I'll try to quickly tell you like what exactly is word piece is. So, and what's the intuition is. So let's take an example. Let's say you want to have a bird called Bugs, right? Then what we'll do, we will take the first word and try to find the longest subword which starts with this word B. And the longest subword will be bugs, right? This could be bugs also. This could be bug also, right? This could be B, this could be bug, this could be bugs also. And let's say somebody just misspells it and it writes as B-U-G, B-U-G-G, like this, bugs, right? So this is can also be a longest substring, right? So what we do, we generally like suffix this with double hashes. Now the double hash U can be the longest subwords, and that's how we actually make the token out of this, right? And the finally then with hash G. So we say that any given word bug can have these three tokens. Now these are the tokens here. So the definition of token is not the actual word that we are generally used to within natural language processing, but this is the how the word piece algorithm actually works with. And then there is some another piece that it tries to do. It actually tries to match the pairs which are matching together, right? So it will then compare some pairing like this word with B. There might be other words also in the sentences. So they will try to match and try to find the frequency of their occurrences. And based on that, it actually tries to give a score. What is the advantage of having word piece algorithm? So word piece algorithm actually can handle out of vocabulary words also. Okay, so sometimes like it's not possible to put everything into the vocabulary, but then this word piece algorithm is sufficient or good enough to handle those out of vocabulary tokens.
Transformer, as of now, just understand transformer is a black box, right? And this black box is doing something. So basically, the transformer, when it came, when the RNN model fails to do when you have heard about something called sequence to sequence uh, modeling in a recurrent neural network, it failed to do the translation, right? It failed to do the translation. Then the transformer architecture was proposed. So basically, before transformer architecture, there is one paper came, and this paper is called something called Attention All You Need. So Attention All You Need says that uh, in 2017 it came, and it also varies that okay, the encoder is every part of the encoder is maybe related to the every part of the decoder with some of the factors, and that the attention mechanism was saying. So they introduced RNN with attention, and then they found that okay, it's working, but RNN was still a limitation. We'll see in detail. So what I'm saying here, that they started with something called language translation task, and this language translation task, as of now, the transformer, you can understand that something happening behind the scene here. Let me take a pen, laser pointer. So something happening behind the scene where the how are you become the input, and then the camo questa is the French word that will be your output, and something happening behind the scene, right? So this part, what something happening, that will open one by one. So when you go to the next part, that okay, what may happen? So actually, it's more about that. Okay, it's how are you is going to be an input to something called the encoder, and encoder is going to send to something it is going to send their input, and that input, the output of the encoder becomes the input of the decoder, and that decoder finally give me the output, right? Means my input is the encode. What happens here? The encoder is going to take input, and that input might be in some format. It's not the text, but how the input it going to take, that we are going to understand here, right? And it gives some output, and that output becomes the input of the decoder, and then it becomes like a output that we are going to expect, right? This is what so far we understand, that this transformer architecture is having something called two things. One is the encoder, other is the decoder. Now, if we go further, then encoder, this encoder is not only a single encoder. Instead, it is the stack of the encoders, right? Similarly, this decoder is not a single decoder. Instead, it's the stack of the decoder. Means the input of how are you is whatever that happening here, right? It goes in this encoder, right? Then this output becomes the input of the second encoder. Then this output of this second encoder goes to the third, and so on, right? And then it becomes to the third, last one. If you go to the paper, right? In paper, it's 6 encoder and 6 decoder they have taken. The original architecture that was consist in the paper, it was happening 6 encoder and 6 decoder. But it depends. It's a hyperparameter, so that we can, depending on our need, we can increase number of the encoder and decoder. Now let's move further. So we'll understand this, what is happening behind this one encoder block, right? Let's move further. So in encoder workflow, what is going to happen, right? So here we have a 6, right? So I'm going to focus on this single one. And the single ones, basically what is going to happen, the primary function, if you try to understand what is happening behind the scene, whatever the token that we are going to send right here, how, R, and U, and all those things that need to be tokenized, and this encoder is going to make a contextualize, remember the word, contextualize representation, right? And the crux is that earlier in RNN, remember in RNN what we used to do? In RNN, we send our input token one by one. But here, we are sending the input token at one in a parallel. No, Kapil, it's not batches. It's a parallelly we are sending, you can say the batch also, but the parallel processing is happening here, right? So this input is going here, that this input need to be converted into some of the embedding, right? After the embedding, we will going to add something called the positional encoding. This input embedding and positional embedding is going to happen. And then this vector that we are going to see that need to be converted into a 3 arrows. What is this 3 arrow? We'll see that what is this 3 arrow. Then something called multi-head attention happened. Then add and normalization happened. Then feed forward happened. Then again add and normalization happened. And then we are also sending this add and normalization to the next layer. This complete NX part is happening. So now let's jump on this input embedding. What is input embedding and how it happens, right? So let's move and understand it. So this input embedding. So let's understand that, okay, there is something called a word token. We tokenized it and we send input that input embedding. So there are the several way of the tokenizations, and the tokenization we generally take with the help of the byte pair encoding, right? With the help of this byte pair encoding, we tokenize our words, and all these tokens are sent into the embedding layer. So that embedding layer might be, you can use any embedding layer like word2vec and other things. In the paper, they have taken word2vec, right? Or any embedding layer, or normally you can simply start with any kind of other part. Then after input embedding, right? So how R and U put into the input embedding, and then it has been embedded into a vector size of 512, right? Now, once these three vectors are ready, the three vectors, how, R, and U. So we are sending this how, R, and U into these three vectors, and these three vectors are ready. I'm going to add something called this word vector. There is something called the positional encoding. Now, why positional encoding? Remember, the when we started learning the sequence modeling, means the RNN, why RNN came in this picture for the, especially for the text? Because RNN keep track of what word comes in what position in a sentence. Now, RNN was slow. Why? Because we are giving input to the RNN model each word with respect to time, and each time one token was passed, right? So that became one bottleneck. That is one bottleneck. Also, the next bottleneck was the vanishing gradient. Someone has already said that in the chat. Now, try to understand. When we are sending here in back, what we are trying to send, we are sending how are you at a once. Now, when you try to send this how are you at a once, then how your model will understand that this first word is how, then it after that R will there, and after that you will be there. This sequential, the positional value, the position of the word in a sentence was not known to my model. For that, we are going to add something called the positional encoding with that word vector, right? And then the embedding with the positional context that we get. Now, what positional encoding has been used? So the positional encoding which has been used is called the sinusoidal positional encoding. And it is based on the sine waves, right? So if someone is going to ask you that this, because sine, if you see the curve of the sine, right, it's add some value, so that the sine is going to add some kind of the vectorized form, so that a special position can be matter there. And also, like here, I have mentioned here that it is ranging from -1 to 1, representing from here. So that why positioning coding? So understand that, okay, we are sending the parallel, and to make that what kind of the words will go to what label, that we have to add the positional encoding, right? So that is how it has been mentioned here, that each dimension is represented unit frequency and offset of the wave with value ranging from the -1 to 1, effectively representing the edge position. So this is the answer of your, and it's not only I'm saying, when I'm saying, so sine and cos are almost same. Only if you uh, make a range, make a shift of 90-degree, right? So sine becomes cos, isn't it? Now let's move to the next layer. There will be encoder stacks, right? And the encoder stacks will transform all the input sequence into a continuous representation that encapsulate the learned transformation into the entire sequence. And it will consist of a multi-head attention as well as the add and normalization, right? I mean, it's fully connected from here to here. It's a fully connected network. So the positional encoding, the embedded input with the positional context that we have, right? That we are going to send into the multi-head attention, right? And after multi-head attention, there is add and normalization factor that we have. And after that, we are going to send it to the feed forward neural network. So this is the step number 3. Now, in this step number 3, there are multiple steps. The first step is multi-head attention, right? So what is happening in the multi-head attention? So basically in multi-head attention, right? It's basically it's try to find it out that how each word is related to the its sentence. Means how each word is related to each, not its sentence, each other word in the sentence, right? So this is what I'm saying, that in encoder, the multi-headed attention utilize a specific attention mechanism known as self-attention. And this approach enables models to relate each word with the input to the other words. Means how, let us 3 words like a, how are you? So how, I mean, how are is related with you, how is related with R, and how is related with you. So it's you can say that it's why it's saying the self attention, because the 3 words, right? These 3 words, it's going to understand that what is their relationship, what is their contextual representation among themselves, right? So this is the multi-head attention. Now, how it happens? So remember in back, so go back here. When we are sending, right? When we are sending it here, it's going to convert it into a 3 things, right? It's going to convert it into a same vector. Let's say we are sending how this x1, x2, and x3 are the 3 representation of my words, right? This x1 again, it's going to convert it into a 3 more words. And those words, those vectors are the query vectors, the key vectors, and the value vectors, right? So in next step in multi-headed attention, a query vector will form, a key vector will form, and the final value vector will form, right? Now let's move further and try to understand that what the next thing going to happen? So basically, this query, key, and value. So this query and key is go on the linear transformation, linear layer. And after this linear layer, there is a matrix multiplication happen between the query and key, right? See what I'm saying here. This matrix multiplication happen between query and key, and then we'll scale this. And after scaling, we are going to this is normalization factor is going to happen. And then we going to pass it to the softmax. And then what the value is coming, that value vector is again matrix multiplied by this. And then we'll finally concat, because we have, this is only happening for the one vector. So we have a 3 vectors, right? So this 3 vector is going to be concat, and that concatenation is going to again send for the linear transformation, right? So as of now, this is happening. So again, come back here and try to see that, okay, we have x1, x2, and x3. It's going to pass. And then this one x1 is going to convert it into some linear transformation. There is a query matrix. There is a key matrix. There is a value matrix. With the help of this linear transformation, which is going to multiply this query, key, and values, we are again multiplying this query with the key, right? And this query with the key, the multiplication will happen, and we'll scale it. And after scaling, we'll pass it to the softmax layer. And what the output is there, right? Again, multiplied with our values and vector, right? Then let's say, and I have a 3 vectors. So we're going to concatenate those things. Debasis, we are going to concat. So remember, we have a 3 vectors, right? Each vector is going through this transformation. And then we have how is going to give you one vector, key is going to give you one vector, and value is going to give you one vector. We are simply concat that, and then we are passing to the inner layer. So as of now, just understand that we have this query, key, and value, and then this is what is happening. We concatenated, and remember, there was a stack, right? There was several stacks of the encoder. Let's say we have h times, and those becomes the head, multi-head. So then it becomes the h times we are going to do. So this query, key, and value will go for the h times, and h time it concatenate and happen here. So finally, it's going to yielding h dimensional output value. Now let's understand everything into a detail. So I have this query, key. So queries has been multiplied with the keys. So all the query 1, 2, and 3, the query that we have, and all the keys 1, 2, and 3 keys that we have, we are doing a matrix multiplication, and we got one score. And then you will see that with the heat map, this how it's going to be related with each other, right? That is what I'm saying. Once a query, key, and value vector is passed through a linear ladder, or that product matrix multiplication is performed between the query and keys, and resulting a creation of the score matrix. We got the score. The score matrix establishes the degree of emphasis each word should place on the other word, right? So it is going to give me that, okay, how each word is related to the another word into the sentence, right? And then what we are going to do, whatever these scores are there, right? I'm going to divide with this score with something called under root d of k. So d is a dimension of this key, right? And we are going to divide so that we can scale the score. Why we are going to do that? because to ensure more stable gradient, as the multiplication values can lead excessively large effect. And then finally, we are going to apply with the help of the softmax. So we apply the softmax, and then higher scores get the high end value and lower scores will be getting depressed. Right? And final, after doing this, what this matrix will be? This matrix is nothing but my attention weight. And this attention weight is going to apply with the values vector and giving me the output of the decoder. Sorry, encoder, one encoder. Let's move further and try to understand this. Means this output is nothing but my attention mechanism. And here I also explained that this we broke our query and key and value h times, right? And the process is known as the self-attention and happens for each smaller stage or heads. That is why it's a multi-head attention, right? Now, what is the next step? Remember, the next step is the normalization and the residual connection, right? So in each sub layer is followed by a normalization steps. And also there is a residual connection. Why the residual connection? Residual connection is going where the residual connection helps. Residual connection helps in there is something called the vanishing gradient, right? To minimize the effect of the vanishing gradient, we'll do this skip connection, or we also say that the residual connection. So that if the model becomes deep, we can train this. So we normalize that. Okay, so here it's multi-head attention. Multi-head attention goes to the normalization layer. And now, what is happening behind the scene? Now, after that, next step, we pass it to the feed-forward neural network. In feed-forward neural network, it is first it linear layer, after that activation function, again linear layer, and then add a normalization. Same thing happen. And this output, right? This output is final output of the decoder that we have, right? And then you can see that this is my, okay, this is the encoder. The output of the decoder is main point. From the output of the decoder, we got this. That output of the final layer is set to a vector. It's representing the input sentence with a rich contextual understanding. Means one by one, we did it here, right? Come back, come back, come back, come back. Yes, here. So in one encoder, again, we are going to send the same thing. So output of one encoder will go to the input of the next encoder, and then it's try to understand, it's try to happen for the n number of times. And when it happens for the n number of times, the final output will be a final contextual representation, right? It is the final contextual representation, which is having the rich understanding. Means how every word is put into the each word. Now, Bhavya is asking that norm and feed forward is between two encoders. No, it is one encoder output only. See here, in one encoder only. And then it becomes the output. Now, let's move and understand about the decoder workflow, right? Now, what decoder used to do? Decoder is basically it's the work of the decoder is to give out, means take the input from the encoder layer and give the output as the every step of the time. So here the output which is coming, it's a sequential, right? So what does it means? that the decoder role centers on the crafting syntax sequences, means the output sequences. Mirroring the encoder, the decoder is equipped with a similar set of the sublayers. Means all the layers that we have seen is the similar only, but there are two things happening, right? There are multi-head attention that we understood, but there are something called the mask multi-head attention is also there. Now, why there is something called the mask multi-head attention? And at this final, when we put this linear and softmax layer, it will only output a single token each time, right? Now, let's go deep in each steps and try to understand what is happening behind the scene in the decoder layers, right? Now, let's understand this thing into a more detail. So, what I'm saying here that what are the steps are there? So there are mainly three steps happening. That there is output embedding, right? There is next step is the positional encoding, and third step is the stack of the decoder layers, right? So at the decoder starting line, the process mirror that of the encoder, means what is there in encoder, the same thing also going to happen in the decoder, right? Here first passes to the embedding layer, right? And then we add the positional encoding as we did like into the decoder layer. And then there are the stacks of the decoder layers. Okay, we have the stacks of the decoder layer. That's the same thing happening. But there is a twist. The twist is here. The twist is mask self-attention mechanism. It will be the mask and it will not look further. It will only see the token which is behind them. It will not look the token. So here also we are sending all the vectors, but to make sure that some values should be masked so that my value that what we have, it should not look forward. It will always look behind. And that is why the decoder also came, also say, also treated as a auto-regressive model. Auto-regressive model means what? It is only based on the past input it is getting, right? It is not look for the future input. So here when we say the mask self-attention happening, right? This mask self-attention is more of, they have given one example, when the attention score of R is being computed, it's important that R does not get a peak of U, which is subsequent word in the sentence. To make it happen, we have to mask it, and that is why minus infinity will be there. So see, the attention mechanism happen in encoder as well as in decoder. In encoder, we got every word. How are you? Every word in a sentence need to be tokenized and sent, and we try to learn that contextual representation of each word, right? And each word can look before also and after also, right? And that is why this vector, we got this score. We got this score, right? We got this score. So each vector was aware that what the niche thing is there. So each vector can look that how are you means each vector are here is aware of all the words. But in the case of the decoder, what we are sending, we are what the crucial difference, it prevents position from attending the subsequent position. Means when you are sending that what R is being computed, the attention of R is computed, we have to make sure that R will not get the information what there in U, right? So to make sure that R should not get into U, we will mask what is there in U. That is why this minus infinity is there. Now, why? Why? Because we have to do decoding part, and decoding part will happen one by one. But how the computer knows? This is what that for the making the computer aware. That is why we are doing this. And masking will happen. That will go into a detail. So we got this mask scored. Now, then there is one new encoder-decoder multi-head attention came. That is called the cross attention. In cross attention, the query and key come from the encoder, and the value is coming from this decoder part. And again, the same thing happened, right? So this is called the cross attention. Why it is called cross attention? Because this query and key is coming from the encoder part, and this value is coming from the decoder part, that is from the multi-head attention, right? Now, then again, we are going to add the feed-forward neural network. And then finally, here we put into the softmax layer, we have the N classes. N classes, we put the softmax layer. And then we got the highest probability word. So this is the next step. And then our final thing will be like this. That, okay, it goes as an input. Everything we understood. Then here is the mask multi-head attention happening. Here it is happening cross attention. And then always this feed-forward neural network and the final softmax. So this is the output of the decoder that we got. So this is the overview and the easiest way of explaining the transformer architecture. Now, the easier method that I said, right? That we understood that overview, that how this transformer model works. Now we are going to learn into a detail that why this transformer model came in the picture and how the things started. So we'll go deep and understand each thing into a detail. Now, let's understand everything into a more detail. So remember the RNN. So what is happening into the RNN? RNN, we send the input one by one, right? So the hidden state S0 start with, then we send something called the I. Then we send something called the output of this H0, and then I, something happened here, the transformation happened here, and the output becomes the H1. Then at the next time stamp, we are sending enjoyed, and then this H1 is having the understanding of this I as well as S0. So we're adding the enjoyed, and this enjoyed will again becomes the H2. So this H2 is also having the knowledge of this I and enjoyed, and that is how the I, S3 came, then H4 came, and then transformer came, right? And final H5 came in the picture, right? And these are HIs are nothing but the hidden state of the your encoder RNN. And H5 is the context vector or the concept vector, and it is having the knowledge of all those things, means encoder, I enjoyed, all those words has been embedded in this H5, right? And then we send into the decoder, and this decoder, this H5 becomes the first state of decoder, and then this H5 is responsible for making the translation. And at first time, it is going to send you NaN, and then transformer, and then transformer came in the picture, and then Padatai, something like that. And then it becomes the resistance, where Si is the hidden state of the decoder, and this is how the actual picture of the RNN is. So we are again learning the thing into a more and more detail. Now, in this detail thing, we started with the RNN, right? Now, in this RNN thing, I'm going to do the transformation from the English to a Tamil, right? And then one by one we sent, and this H5 came, and this H5 is able to depict this non-transformal parity and resistance, right? So this non again becomes the input of S2. This transformer again becomes the input of this, and this becomes the input of this. This is how our RNN works. Let's move further. So, but what happens when it was a smaller sentence? My H5 is able to depict and speak all this word clearly, but as well as the length of this word has been increased, the quality of this translation has decreased, right? So there was no such alignment between these non-transformer Padatai and resistance, and this I enjoyed the movie Transformer. So how this each word has been related with these output words, there was RNN was not solving this. To solve this, attention mechanism came in the picture, right? So what is happening in attention mechanism? So in attention mechanism, we create a copy of this hidden state vector S1 to S5. So we took all this S1 to S5, and then we just took this H1 to H5, and once this H1 to S5 that we have, we only took this extension score of this H5. Means we took this H1 to H5, and then we send it over to, with the help of one input sequence, we send the complete H1 to H5 with some mechanism. What are those mechanisms? So that mechanism is called the attention mechanism. And there is a parameter called alpha Ti. So this C1 will have the input of all H1 and H5, but multiplied by a term called alpha. And that is how it's look like. It's together or separately. This is what till now, let's go back. Go back. Till here, the things were happening into the sequence, right? Till here, the things were happening into the sequence, right? Now what I'm going, if your encoder part has been completed, just take all the hidden states. So I have taken all the hidden states, and from this hidden states, I'm going to apply attention mechanism. So this attention mechanism is nothing but I'm going to create one vector called C1 that becomes the context vector. And then I'm going to apply this. I'm sending this all H1, H2, S1 to H5 with some multiplication of alpha Ti to the first instance of this C1. So now I'm sending it parallelly, right? So it has been multiplied and we got the output called NaN. Now again, this NaN become the input. We have to C2. And C2 again can be calculated in the similar fashion. So C2 has been calculated, C3 has been calculated, C4 has been calculated, and then we got the alignment of the word called non-transformer parity resistance, how it's related to the output input. I enjoyed the film transformer, right? So half of the part in RNN was happening sequentially. Once we got the complete output of the hidden, we have done this parallel task. Right? Now, we got it, that how the things has been related, that NaN is related to I, this transformer is related to this transformers, and this potatai is nothing but the film, and this enjoyed is related to the resistance, right? And the function is align of YT to the HI. Now we need to look at this align H. What is align YT of HI? So it is nothing but the exponential of a score between a score function of ST minus 1 to HI, and then the exponential of all from 1 to n for ST minus 1 to HI prime. Right? Let's move into a more detail. Right? This is that we have. So this alpha Ti can be computed parallel for the all I. The answer is yes, that we did, because HI is available for all I and STA is also available for the TMSTMT, right? But means attention can be parallelized, right? So the take away from here that attention can be parallelized, but can HI for all I can be computed in parallel? What is HI? HI is the hidden states. Hidden state can be computed? No, it cannot be. Why? Because in RNN, we do things one by one, right? So there is one drawback, and it has becomes the major limitation. So everything about RNN based on the sequence to sequence model seems so good far, but they cannot do the linear. They cannot becomes the parallelism. We cannot parallelize the sequence to computation across the time step. So there is one need of new architecture, right, which incorporates the attention mechanism and also allow parallelism, also allow the parallelization, and of course, get rid of the exploding and the gradient descent problem. Now you guys can tell that why attention mechanism came in the picture. Sorry, why transformer architecture came in the picture. So attention came. Attention solved one issue. The issue is that how input is related to the output, right? And it increased. But there is something missing. What is it missing? That still we cannot train those model efficiently because half of the part is not parallelized. And to put this, to include this parallelism, what they have done, they have thought that can we remove this RNN? Can we remove this RNN, and based on this only attention mechanism, can we create one architecture which is going to solve my purpose of doing the encoding and decoding? And that is how this attention, the transformer came in the picture. So as of now, we only understood that why RNN are bats, though the attention mechanism came in the picture, but attention mechanism only solve the contextual relationship between the input and the output, but they have not speed up the process of the learning or the training of the model. So there was a need that we need to do the parallelism. We also need to do the contextual learning. And that is how the new architecture came in the picture. So let's learn about this new architecture. So how we transition from RNN to the transformer. Let's go here. So from the encoder, we did encoder with attention, and the attention score has been passed. We simply come to our transformer model. So I will give you one more time. This is our encoder-decoder. After encoder-decoder, we came into RNN. It was the RNN encoder-decoder. From the RNN, we came here RNN with attention. And from this RNN with attention, we put into the encoder. So we completely removed the RNN block, and we started with word embedding. And word embedding, instead of attention mechanism, right? Remember, we were doing the attention mechanism here, right? This attention mechanism. Instead of attention mechanism, we are using something called the self-attention mechanism. Now, this self-attention mechanism is the replacement of what? This self-attention mechanism is replacement of this guy called hidden weights, hidden states, as well as this attention score. So we are going to replace this guy with this guy called self-attention, right? So now there will something very important come. So when we go and look that the mathematical expression of this, right? The mathematical operation of this will look like this way. Okay. Before that mathematical operation, let's understand what is happening behind the self-attention. So in self-attention, you guys understood that, okay, this will be the all I enjoyed the movie Transformer, and that has been converted into the token, and the token is again converted into the word embedding, and that word embedding is going to the self-attention mechanism, right? The word embedding and output are also the vectors. And then this attention is, so it requires as a pair of the vector as a input, right? So one vector is this. And remember, this self-attention mechanism requires two vectors, right? A pair of the vectors as an input. So one vector, can you think this word embedding as HI? So this becomes HI in RNN encoder. And then let's understand the self-attention into a detail. So as of now, here we only understand that, okay, this becomes the self-attention and this becomes my HI. So I'm sending this HI, and then something happened here in the self-attention. But in the self-attention also, in attention mechanism also, we need two vectors. One is the H1 to H5, one is the alpha 11 to the alpha 15, right? So two vectors are there in the original attention mechanism. So in this attention mechanism also, we need two vectors. One vector we got as this input embedding can be treated as one vector. That is what it has been mentioned that, okay, let's take as of now this embedding as a HI that was there in the RNN. Now let's understand this self-attention intuitively. Mathematically we'll understand, but what is intuition behind that? So to understand intuition behind that, let's see one sentence. The animal didn't cross the street because it was too tired. Now, tell me, this it correspond to the street or the animal, right? So now we say that the word it in the sentence refer to the animal or the street, and we know that it is referring to the word animal, right? Now let's take another example. The animal didn't cross the street because it was congested. Now, how it has been related? Now it is referring to the street. Yes. Now you can understand why self-attention came in the picture. Means it is very important to establish a strong connection between the words it to the word street or animal based on the context. Right? So it is very important. So here, if I take, means we need to have some mechanism which says that in this specific word, it is more related to animal, and this specific word, it is more related to the street. And that is the intuition behind the attention mechanism. And why it called self-attention? Because it is happening within a sentence. Within a sentence, how the words are related to each other. If we try to find it out, if we try to give that attention name is called the self-attention. Paragraph are nothing but longer sentences, right? If we are going to put as an input, it can be the same bit. Now let's move further and let's understand what will be our goal. So the goal is, given a word in a sentence, we want to compute a relational score between the word and the rest of the word in the sentence. Right? This is my goal. To achieve that goal, we have to make a matrix, and this matrix need to fill by some of the value. So that this is nothing but our self-attention matrix. And the value should be comes like this, right? So can we think the headers of the first column as a SI? These are the SI. Header of the first column are the SI, and the header of the first row as a SJ. So this becomes the SI and SJ, just for a convenience. Then this becomes the SI, this becomes the SJ, right? And now basically what we want that both the vector SI and SJ for the all IJ are available for the time spent T, right? Where in sequence to sequence model, where SJ for LJ was only available at one of the time. So now this part is available for us. And once this part is available, can we compute it at a once instead of doing it as a sequentially? So that is what I'm saying. Does it allow us to compute the value row parallelly, that is all at a time? And the answer is yes. And remember the score function. So this score function of the attention mechanism is nothing but st minus 1 multiplied with ut attention, then vt attention and sj, and then one it goes under the tan s transformation and again multiplied with a va, right? So this is having three vectors s, h, and v. It was involved in computing the score in each time step of the decoder in the actual attention mechanism in encoder-decoder, right? So basically, we need three vectors. One vector is this, one vector is this. So we have a two linear transformation, and we apply tan h, one non-linearity, and finally a dot product. That is Vt multiplied with the what is coming from the non-linearity, right? Which has been multiplied here, right? So the input of the self-attention module is only the word embedding Hj and Hj, right? So basically we need three vectors S, H, and V. But as of now, what we have only the input as a HI, right? So what we can do? So we need to get 3 vectors for the each word embedding. How we do it? And here comes the linear algebra to help you. And linear algebra, what is going to do? It is going to do the matrix transformation. So how many matrices we need? And what are those 3 matrices? Those 3 matrices are nothing but and those vectors are my query matrix, key matrix, and value matrix. And when we multiplied my Hj, means all the hidden right, this Hj multiplied by this query matrix, value matrix, and key matrix, we get our query vector, key vector, and value vectors. So Qj is called the query vector for this word embedding Hi. Kj is called the key vector, and Vj is called the value vector. So basically, what we are trying to do, these are the respective Q, WQ, WK, and WV are the respective linear transformation matrix, right? So let's calculate. The answer will come here, that why this key value is coming. So we put this self-attention mechanism, and the self-mechanism, I applied this linear transformation, and I got Qn, and then K1 and V1, and so on. We got this transformer representation of this current transformer, and also go to the Q5, and then it's K5, and then which got the K5. And all is happening in parallel, right? So we have ST minus 1 also, SG minus 1 also. This value is fixed. This value is variable, right? So a score function will be our dot product. So we got E1. And my E1 vector is Q1 dot K1, Q2 dot K2, and so on Q1 dot Y1. And alpha 1j will be the softmax. Remember the softmax that we are getting? And then we finally apply this Z1, which is the output of this attention mechanism. That will be the J1 to 5, alpha 1 of J, V of 1J. Now, what this E1? E1 is nothing but the query vector multiplied by the key vector. This query vector multiplied by the key vector means, it's simply intuitively it can say that what is the importance of this specific word with respect to the other words. That is why for one Q1 we are making dot product with the each query. What is the importance of this specific Q1? For this specific Q1, I am looking the importance of this word with respect to the all other word. And that is why I multiplied with Q1, K1, Q1, K2, and so on, Q1, 5. And that will be my alpha 1j. Remember, it's 1j. Means it's giving the attention score of the first word with respect to the all other words. And then we are taking this the softmax, which is going to normalize and give the actual value. And that is how we Z will come. Now, query and key is word embedding word H1, right? Yes. What is Q1? Q1 is the transformed. Remember what we did. We have this H1, that is nothing but 100 is the H1. This has been transformed with this linear transformation matrix, and we got Q1. Now, what is Z2? Z2 is again I'm talking about Q2. Okay. So with respect of the Q2, I'm looking each key. So each key I'm looking, and then I did the dot product. Then I put the softmax and get here. So, and we repeat all with the other Z. So we got with this. Now also this can be go into parallel. Means this can be done into the parallel. Means all the Q, all the K, and all the V can be done in the parallel. As of now, they have taken 64 is the dimension. Right? Now we got the vectorized output, and this vectorized output Z is nothing but my softmax, means the query transpose multiplied by the key. We did the normalization here, remember, under root dk, and then we put it this multiplied with the value, and then we did the softmax. So this is my final value, where dk is the transformation. Now, what will be the dimension of this guy? The dimension of t multiplied by 64 multiplied by 64 into t is to t cross 3. Right? Dimension of z is nothing but t multiplied by t and t multiplied by this. So this got cancelled. T multiplied by 64, t cross 64. And then d scaled. So it is called the scaled dot product. Wow, this is what I wanted from you guys. Now, we got the scale dot attention head. All the things has been done clearly. We put it here, and we have similarly we have one head, two head. Now, why this different head? So the idea behind is, let's come back and try to understand. Call CNN. So in CNN, we do different kernels, right? Filters. We apply different filters, and we assume that, means our intention, that each filter is going to take a different feature, is take out different features from the image, right? Similarly, here we also thought that adding more than one head, right, will also give us the different contextualized representation of that word. That was the intuition behind that. And this motivate multi-head attention, which is simple extension of the single head attention. Got it, guys? Why multi-head attention came in the picture? Now let's come back to the basic one. So this is my encoder, this is my decoder that we have, right? And we got our each layer n equal to 6 that we guys learn. And then it's 512 here. Then let's take one linear, one softmax feed for one neural network with one hidden layer. And then again, 512 is out. So we got here, we got here, we got here, in total output we got. And then in output of the for neural network is the maximum of this plus weight multiplied by weight plus B2. This WQ, WK, and W things we instantiated with the random values, right? And these are the learnable parameter, so that when my model will learn, the value will change. Means it will learn the complete things into a detail and it will get trained. So these matrices that we introduce, that was dimension of 64 multiplied by this, guys. These all are the learnable parameters that we have. So we have considered 8 heads. So this total is this much of the parameters that we got, right? And then the total of the parameters will be this. So in feed form is 2 to the power this, and we have 3 million parameters per layer. Now in Encoder stack is this, we have 6 layers, and each is having t multiplied by 512. Then number of the parameter is 3 millions, number of the and multiplied by 3 millions, we have a 6 layers, we got 18 millions parameters. So only in encoder, we have the 18 millions parameter, right? Now let's understand about decoder. So decoder, what we are sending? We are first sending none, then transformer, then Padatai, then resistance, right? And from input, it is coming from the encoder, and then output is coming one by one, right? So what will be the output dimension? It will be the number of 1 multiplied by 307 t, right? So decoder stack, what is happening? So let's understand about the decoder stack one by one. It also considered multi-head attention, but it is the mask multi-head. Now you guys will understand. Remember, most of you having the difficulty. Let's understand into a detail. So we have first mask multi-head attention. And remember, there was an input coming from the encoder. So when input coming from the encoder, that becomes E, and that mask multi-head attention pass through one linear transformation feed-forward neural network, and that will go, and that is called the multi-head cross attention. Why cross attention? Because here the key and query comes from the encoder, and the value comes from the multi-head attention, right? Now, what is teacher forcing? Why the target sentence being fed as one of the input to the decoder, right? Usually, we use the decoder previous prediction as an input to make the next prediction of the sequence, right? How? The drawback of this approach is that first prediction goes wrong, then there is a high chance that the rest of the prediction will also go wrong. Yes? And that lead us to the accumulation of the error. Of course, the algorithm has to fix this training process, but it all take long time. And that is why the teacher forcing algorithm came in this picture. That is, we are sending the ground truth also. So what is mask multi-head? That query and key has came multiplied with the self-attention computed as a query, key, and values, and multiplied with the embedding respectively. But at the same time, decoder layer, the time has H1, S2, and S3 are the word embedding target sentence. But one important difference. Here comes the specific things, that masking to implement teacher forcing approaching during the training. We have to implement this, and we can't use teacher forcing during the inference. Instead, the decoder act as a auto regressor. That is, I was trying to explain that time. That we have to put the ground truth so that masking will happen. Now, how masking has been done? So masking is done by inserting negative infinite as a respective position. So all that position T we have, and it will take the triangular matrix format. One half all 0 and other half is the negative infinity. Right? You can see it here. So this is your mask multi-head attention, where we have the vector S1 to ST coming from the self-attention layer of the decoder, right? Then we also have the vector E1 to ET that is coming from the encoder stacks, that all layers share to the decoder stacks. And again, we need to create query, key, and value vectors applying this linear transformation with query vector, query matrix, key matrix, and the value matrix for this vector Si and Ej. And these are called the encoder-decoder attention, or the cross attention. So that came, and we again applied a softmax, and finally we concatenate the vector, and this is how it goes. So we send go here, none here, right transformer, and this has been, these two guys has been masked. So it's sent to the mask for neural network. Here the input came from the encoder, cross attention happened, and then we got our this query key of matrix is happening here. See what is happening. We key and value coming from here, query is coming from this side. And then this function become a Q2, K2, V2, and this WO2. This WO2 coming from this pipe. And then it becomes our parameters. And this is how we calculate the number of the parameters.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
Yes. Right? So basically, as of now, you just understand that Hugging Face is, there is so many answer of this question, but as of now, you understand that Hugging Face is a company, right? Hugging Face is a company which creates a different which has created a platform where several machine learning models, dataset, as well as spaces, means it is a kind of a one-go solution or one-to-go place to find everything related to machine learning. Means, so generally what you do, generally if you create your model, right? So that model creation happen on your maybe in your server or in your laptop. But if you want to share that model, so you need to deploy that model somewhere and store that model somewhere, and you can leverage that model somewhere, right? And that model might be your own model, and that is a closed source model that you have built on your data set, right? So if and there are several people who are doing the same, but there are something which can be shareable. Means suppose I have created one model and shared the code, and someone want to leverage the same code and same model. So earlier, either you can give that model to them, but the benefit of the Hugging Face is you can put that model into Hugging Face model spaces, and from there, someone can already download it. So if I can say that Hugging Face is a GitHub for machine learning, so it is like a GitHub, but it is GitHub for machine learning. And they have, so in Git, there is something called LFS, large file system. So GitHub and Git, so with the help of this open source Git command, so there is two things. GitHub is one enterprise solution where your all the coded we used to do, right? That is different thing. I'm talking about the Git, the source code management system, the Git SCM, the version control or the source code management system, where we put the code and we may make it private. Your repository can be a private or can be a, like I will give you example. Just give me 1 minute. Let me give the example of, so I'm giving github.com. So this is the github.com. Here we can find our repository. So let me go here and find JCSE. So if you go to the users, right? So this is my repository, right? And inside repository, I have several, it is my GitHub repo, and I have created several repository like a time series, basic Python, open source LLM, Prequeen, RAG, Haystack, and so many things. Means if you just open here, right? So I have created some code, and I have made this code as a public so that everyone else can use it. But if I want to upload some models here, then as the model size can be large, this GitHub cannot support it, right? So for that there is something called one platform, a scheme, and that platform name is huggingface.co. Remember, it is not .com, it is .co. So here we have several things. Here we have a models, we have a data set, we have spaces, we have a post, we have a documents, we have a solution, and then is the pricing. Means it is free also, as well as it will be paid also. So there are some services that can be paid. Okay, I see someone has raised the hand. So let's learn about that. What are the different things that we have? And then we'll see, we'll try to create one of the model here. And then after creating the model, we'll try to load it and do the different things. So in the Hugging Face, there are the different components. First thing is the model, right? I will tell you that what the models are. Basically, you can understand that models are nothing but where all the open source or closed source model we are going to put it there, right? Basically, the open source model only, right? What are the data sets? So data sets are uh, the collection of the data sets which can be uploaded by the user, and there are several data sets which can, with the help of that, we can use the data sets to train our model. So you can leverage this data set. Data sets is also a library. So with the help of this data sets library, right, you can download whatever the data sets there on the Hugging Face. We'll see that how to do that. Then we have a spaces. What is a spaces? Spaces are nothing but, suppose if you want to deploy the model, right? So if you want to deploy the model, the same model, and so you need the compute to deploy, you need the servers or maybe the containers and all those things. So to doing the deployment, the spaces are provided by the Hugging Face, right? And beyond this model, data sets and spaces, we have some other open source library like Accelerate and others, which is going to help in model building, right? And finally, there is a community page where you can interact with your fellow developers. So mainly the models, data set and spaces are there, right? Then we have open source library and documents and the community. Now let's move further. So what is Hugging Face, right? Let's try to understand it. And first we try to understand that how to do it. So first thing is about the model. So model are nothing but Hugging Face can host all the different type of the open source model, which can be the large language model also, the diffusion based text to image model also, audio models, and more, right? And the best part here, that with the help of this Hugging Face tool, CLI tool, right, we can access those models, right? For example, when developer thinks of typical version control and file management, they use something like Git and GitHub, the example that I have given, right? But however, only using Git limit our capability to work with the large file system, right? And with the help of this Hugging Face CLI tool, we can use with the ML files. And how the models looks. So if you see, the models look like this, that this is a page that we have in models page. You can see that time when this PPT was made, right? This time we have 6 million kind of, yeah, not 6 million. It's 6 lakhs, 4,000. This much of the models will be available there. This is not .keras. It is mainly PyTorch model, and there are something called the safe tensors format. So now let's understand more thing, that what the model pages will be. So the model, if you go inside one model, right, there will be a model page, and it include lots of the tool and the information, right? And there will be some direct link to run the inference, how to take the inference and all those things. And then, and remember that it is not essential that every model is having the model page. So actually everyone can create a model, right? And one can upload those things. So it depends on the user who is going to create the documentation. So if the model page belong to one company, so, or some authentic user, then you might get so many of model cards which is having the proper documentation, right? But for the other model, you might not get. But what is data sets, right? So for the training and evaluation, you can host your data sets to the Hugging Face library, right? And it can also contain the data sets using audio data, image data, text data, and several kind of the data sets can be hosted over the Hugging Face, right? How the data sets looks like? So data sets looks like that based on the task. These are the different data sets are there, right? We'll see those things. We'll see those things, that how we can look further and all those. Now, with the help of this datasets library, right? With the help of datasets library, we can download the data with the command, right? But there may be some data, right? There is some model and some things are already there, where remember when the Llama 3 came or the any other model came, so we need some access to download it. Might be you have not used that, but I am telling that when Llama 3 came, right? Llama 3 is a large language model uh, given by Meta. Meta means Facebook. So they have restricted the access. Though Hugging Face is a platform which is open source, but even in Hugging Face, you can restrict. Like simply, remember, in GitHub, there is a repo that can be a private or a public. Similarly, a model which can be gated or the open source. Now, what is spaces? Spaces are nothing but where you can, yes, Bhavya, for the every model, you need to specify that which model, they will not give you the license, but every model is having the corresponding license, right? The MIT license, Apache license, different kind of the license should be associate when you are start with uploading your model, right? What are the spaces? Spaces are that suppose if you want to take one inference, you want to deploy that model. So with the help of the spaces, you can do that, right? So let's say here in this example, in Gradio, we created one, take this image, and from that image, if you want to remove the background, so with the help of that Gradio app, which is nothing but the instant mesh model has been running on this, we can do it, right? So it is taking the, it is more about that how to use the model into the real life, or how to take the inference from the model. The species is all about those things. Now, apart from all those things, we have this model in the Hugging Face. We have transformer, diffusers, gradio, accelerate, and many more. What are the transformers? Remember, we don't, people do not sell model on Hugging Face. You cannot sell, because Hugging Face itself a company which going to charge for it. Now, remember the transformer, if you code the transformer, right, and you try to use for your machine learning from the scratch with the pure vanilla Python or the PyTorch, it will be very difficult. Even long back when I was doing with BERT and this one library called Keras. Before Keras, there is one more library was there, right? TensorFlow. So even coding in TensorFlow, a transformer was very difficult. So what Hugging Face has done, Hugging Face has made our life so easy. Hugging Face has made our life so easy that with the help of this transformer library, right? With the help of the transformer library, so with the help of this transformer library, we can do this word with the few line of the code. Just with the few lines of the code, we will do that. Now, what is diffuser? Diffuser is more about the diffusion model. So it's more about from text to image generation. So when there is a diffusion models which works on the basis of the text to image generation, right? That diffuser library uses the diffusion model behind the scene, and it also will integrated in the Hugging Face. Then there is something called the Gradio, or people say it a Gradio. Gradio is a simple UI, right? User interface. With the help of that is a Python based UI library. With the help of that, you can simply create a web app very easily, right? So with the help of the single click, you can create one application. Now, what is Accelerate? Accelerate is a library which accelerate our the process of training a model, right? And so on, right? And then we also have open source libraries as well as the documentations. So for the open source library, the source code might be on the GitHub, right? But the official docs are, or the example will be on Hugging Face. As example, let's say if you want to know about the transformer. So the transformer maybe have this Hugging Face transformers, the state of the art machine learning for PyTorch, TensorFlow, and JAX, and all those things. All the code will be hosted over GitHub. But if you want to learn more about this, so all the documents will be on the Hugging Face. Now let's understand what is transformer. Transformer, you already know that if we have any pretend transformer, right? This, with the help of that transformer library, you can use that. Diffuser is nothing but a diffusion based model. Generally, it's a text to image generation. And Gradio is creating a GUI, your ML applications, right? So community means you and me. The users like you and me will go and create a community and discuss about all those things. That is about the community. And then finally, let's come back and create our account and then also create the tokens so that we will be able to create a model. So go to huggingface.co. Everyone go to the huggingface.co. Devashish, ML Ops is machine learning, DevOps for the machine learning. It's an enterprise grade practice, right? Here, spaces are just about to give you the quick demo. Everyone signed up. Make sure you also install Git on your system. Git is there, right? And then you will see that this is how it looks like. So let me do it for you. I will do, let me do login because I already have dot fastai at gmail.com and then so this is your Hugging Face, right? This is the Discord community. Let's understand about the model. So you can see here we have a 7,64,133 models, right? And the model is also having based on the different tasks. Let's say the task is text classification, right? So if I click text classification, then I can see that I have 66,297 models that we have, right? And then if you want to do the sort, right, you can either sort with the trending, which it has been done, or you can go for the most like, right? You can see that Finbot has been most liked. Then you can search for the most downloaded, right? You can see Facebook fast text image identification has been most downloaded, or maybe recently created. This has been recently created about 1 hour ago, and maybe recently updated means this is updated about 1 hour ago. So this is how you can check that. Let's say I'm just checking up the most liked and I'm just taking about this Finbot model, right? So if I check this Finbot model, I will see that I have this model card, that what this model about. And this model is about that, okay, this is a pretend NLP model to analyze financial text. It has been built further by training the BERT language model in the finance domain, using a large financial corpus, thereby fine-tuning for a financial sentiment classification, right? This is about the FinBERT. If you go down, okay, only one thing is having here. Now, see here, the inference API has been already given. Now, they have given one example. Let's talk about some Tesla. Tesla, no, TESLA. Tesla stocks are skyrocketing, right? So right now, what I'm doing, I am simply showing you that how you can go and from that model, from the simple model, right? You can look for the what task you want to do. Like, let's say I'm going to do the text classification, right? Or even question answering or the translation. Let's say this time I used something called the translation. And it says that now if you just use here translation, right? So there are 3,670 models has been hosted over this Hugging Face, right? And in that, you can see here that it's 3.2 million download and this T5 base model. Here you can sort it out on the basis of trending, most like, most downloaded, and so on. Let's say I have chose most downloaded. So most downloaded one is Google T5 Small, right? Let me use this. So I'm just taking here, and then it shows the model card. The model card shows that it can be used for the encoder, and it's an encoder-decoder kind of the model where these are the languages that we have. And we can, with the help of the encoder-decoder T5 model, we can get it here. In this, remember in earlier, we have a very limited documentation, but in this case, because it's coming from the Google, everything, model detail, usage, bias, training detail, evaluation, and every citation will be there. So here, see the model description. The developers of the text-to-text transformer model writes that we propose reframing of all NLP tasks into unified text-to-text format where the input and output are always text string. In contrast to the BERT style model that can only output either a class label or a span of an input. Our text-to-text framework allows to use some same model, loss function, hyperparameter for any NLP task, right? Then it has given that it is developed by person. It is which kind of the model is there. It is a language model. Which kind of the language it has been trained on? It has been trained on the English, French, Romanian, and German. What is the license that we have? It is Apache 2.0, right? Which is the all related models. So all T5 model that we have. This is the research paper. And finally, you can also see the code for this T5 model. So what I clicked their GitHub repo, right? And I came here that, okay, this is the T5 code data that we have. It is out of the scope type. Is there any bias? Is there or not? Recommendation that you have. What kind of training data it has been used, right? From the model card, you have to go file and version, right? And you can see we have the model, right? We have a PyTorch model. Then we have a safe tensors. So these are the file format in which my model has been stored, right? And there is a community. Remember, the community means we have the discussion about this model, right? So if you have any bug or any suggestion, so you can do here as a model, as a user, right? Then how to take the inference, right? So I'm just computing that my name is Volgov and I live in Berlin. Let me do it. And we see here that okay, it has been translated in this language. Let me do here. My name is Girijesh and I live in Bangalore, right? Let me do that. So it's going to convert. Main name is Stir Girijesh and Andu Iche Lebe in Bangalore. So it's doing the translation in the German. This is one example, right? Then you can also see here that you can deploy that model. You can use that model, and even you can fine tune that model over this auto train, NVIDIA GDX, and Amazon SageMaker. Obviously, these are the paid things, right? These are the paid things that we can do, but it is not required now. Here we can clone the repository, right? And here we can, if you want to create your own collection, you can add to the collection, right? Then this model, what this is, it's saying that this model can be used in the PyTorch as well as the TensorFlow as well as the JAX. Also, this model is also available in the Rust language, and we can format with the ONX file system as well as the safe tensor file system, right? It has the 5 language support. It can do the text to text generation. It can use for the summarization and other several tasks. Now, let's take another example. We are doing translation, right? Now, let me do here this space. So these are the space which has been holding. So let me take this this space. So let's see. It takes some time. So this is the demo of the music gen, a simple and controllable model for music generation presented at this, right? So here we can describe the music, or let's say Indian Bollywood music, right? And condition on, okay, I don't want any file, should be, let's say if I generate record from the microphone, we put the generate, let's see how, what kind of things has been taken. So it's taking that, it's going to take 82 seconds. The processing is happening. So it's from text to music. Let's see how it goes. I am doing it the first time. Otherwise, we'll take some other example. Okay, let me. You guys are able to see this? Able to hear this? I think it's kind of cool. So with that, we can even generate the music. Now let's use some other. Let's use this chatbot. Okay. Now this chatbot is H2O GPT, and behind the scene, it's using the T5 model. So, hi, how are you today? I'm just asking a normal question. And then the answer is, let's see what the model is giving the answer. Okay, looks like it's not working. Let me ask, what is 2 plus 2? Submit. Okay. Okay, it's already in running state. So might be this is happening behind the scene. Okay, it is using Llama 270 billion chat. So why it has been showed here in T5? Especially using T5 small. Okay, let's move further. What is the model card? What is file version? What is community? And then how to take the inference API, and then how to take the inference, and then finally any of the spaces. T5 is GPU, right? T5 is not GPU. T5 is the name of the text-to-text model. Okay. So now let's come back and go to I want to create a model, right? So even everyone can create a model. So I'm going to create a model, and what I'm going to do, I'm going to give a model name as a, what name should I give? Let's say I'm giving Intellipaat, right? And then I'm going to use the license, let's say Apache is not there. Leave that. I'm just giving MIT license. And then I'm putting it as a public, right? And then I'm going to create the model. So now there is a model card. So here we can edit the model card, right? And license is get Apache, and then here I can simply say that This is the test model for our LLM class, right? This is the test model for our LLM CLASS, right? And then commit the changes, first commit, right? And then we can simply edit it here, commit, first commit, do the preview, commit changes to main. Okay. Control X. Control V. Okay, this has been done. So there was some, what was the issue? The issue was that I have not formatted it properly. So it has been committed. Now you can see the code here, right? This is the code. You can download it, copy the download link. You can download it, right? This is the commit. And if you check, this is my model, right? This is my model that we have. And from model card, we can increase, and there will be a setting, right? And from that setting, we can then make whatever the access request is there, that is the discussion all will be there, all things we can do. Before that, one more thing we have to do. We have to go and we have to go to the settings, and in settings, you have to create your access token. So I have already created the access token for the one for the Llama, one for the Longback, for one Udemy course, which I have created. For that, for teaching Hugging Face, this was Longback. I think last year I have created. For you, you have to just do here, and then you can give your token name, and then you have to give that appropriate permission, and then finally use the create token, right? This you have to do if you want to use this Hugging Face. Then next thing is about model has been done. You can create the model. Even from the command line, you can do it. We'll do the practical. Then there is something called the data sets, right? So the data set is more about that, okay, what kind of data you want, right? It's also depend on the task. So let's say I want to train my model on text classification. So I took the task, I put the text classification, and then you can see all the data sets which has been uploaded that has been done here. Let's say I'm taking most liked. So Open Okra are the most liked, Glue, Slim Okra, IMDb. I think you guys have heard about IMDb, right? So IMDb dataset you guys have heard, right? This is the same datasets. And datasets, you guys are able to see that these are the datasets. And with the help of these datasets, right, which you can see, these are the label as well as the text that we have in data. So this is how the words look like. And this is the split of the data, that 25,000 is trained and 25,000 is test, right? So this is the data set that we have. Now, after dataset spaces, now you can create your own spaces. It's just what you can see. It's just kind of your Gradio app. So let's use this Flash LoRa, right? So this Flash LoRa, it's more about it's interactive demo of the flash diffusion on top of the existing LoRa, right? So these are the things that we have, and we put the LoRa weight, we put the prompt, and things will come here, right? Let's say I'm just putting this. So I created this by interior prompt. Make it pixel wise and run that. So I selected this 3D render has been selected. I put some of the things, and then this is what is happening. It's taking too much time. Okay, GPU task aborted. GPU is not there. So it's required GPU, and we don't have the free GPU. That is why it's not happened. So let's say some other GPU, or maybe you can use all running app, live update, Midjourney, stable diffusion. Let's say I'm using this. Interior prompt. Student learning LLM. See, the students are learning LLM, or let me do that transformer model. Transformers. Okay. Transformers architecture. Okay. So see, a student learning the transformer architecture, that prompt engineering, right? Okay, let me put some advanced setting. Okay, seed is there, height is there, width is there. Okay, let me use some example which has been already given. The astronaut riding one green horse. I'm using this astronaut hiding on the green horse. Let me run this. See, the astronaut hiding one green horse. Right? Okay, this is a diffusion model. Now, let's start our actual work. So let me use the next part. Transformer and the text model. So let's directly jump on the transformer and what they can do. Okay. So in transformer, what I'm going to do, we are going to learn. Okay, let me select the runtime and make it as a T4 GPU. Save it. Let me do the connect. Okay, it gets connected. And then first thing what I'm doing, I'm installing datasets, evaluate, and transformer. So datasets you already know, transformers you already know. What is evaluate? So evaluate is nothing but remember in machine learning we have a different metrics, right? For the accuracy, for the classification we have a different metric. For the other we have a different metrics, right? So evaluate consists the matrix related to the text data which is on the Hugging Face. Means is Hugging Face related like a blue score, rouge score, all those things is already implemented behind the scene in Evaluate. So this is the metric library from the transformer Hugging Face. This transformer you already know, right? I installed it, right? Now, what I'm going to do, why I say this transformer, this Hugging Face is made our life very easy, because they have done lots of the thing behind the scene. So what they have done, so from transformer library, if I'm importing the pipeline, this pipeline function is having lots of the thing. Let's say I want to do sentiment analysis, right? So I can create a pipeline for the sentiment analysis, right? Let me just cut it, right? This has been done. It will take some time. It says that it's a positive, right? Let's say if you want to do for the 2 sentences. So I have been waiting for the Hugging Face course in my whole life, and I hate this so much. So if I execute this, so first is positive and second one is negative, right? Now let's understand that this is my sentiment analysis pipeline I have downloaded, right? Let's say I have downloaded something called a pipeline, which is zero sort classification. So in pipeline, we have a different pipelines, right? Okay, someone is asking that what if I want to know for the both? So similarly, you have to just do like this. Let's see. This is -1. Because what does it means? That I have waited for the Hugging for course for the whole life, but I don't like it. Right? That how to know that what are the pipelines are available. So for that we have to go and check into the documentation that what are the pipelines are available, right? Also, you can go here and check into your function definition. So here I'm doing a zero sort classification, and then what I'm saying that take this sentence, right? And then tell me that it's this specific sentence belong to education or the politics or the business, right? So let me do that. So you can see this course is about the transformer library from education, business, and politics. It has given 84% confidence on education, 11% on business, and 4% on politics. One person has said that with the help of this dir function, we can get this pipeline. If pipeline are there, right? You can get the definition of all those, that what are things are there, right? So basically, this dir gives that what are the method available for this, right? So these are the methods, right? Now someone is asking that what is happening behind the scene. Okay, let me show you that what is happening behind the scene. Just give me a minute. Transformers pipeline behind the scene. Okay. Yes. So behind the pipeline, what is happening? So first the tokenizer will work, right? Then the model, the whatever tokenization has been done, it has been sent to the model, and whatever the output is coming, right, that has been post-processed. As example, that there is a raw text that this course is amazing. It's going to be a tokenizer, and tokenizer is converted into the IDs. That IDs goes to the model. Model give you the logics, and these logics are going to do for the post processing, and that is going to give me that positive or negative label. Right? This is happening behind the scene. Got it, guys? Okay. So someone's look Java. Okay, if you want, I can give you that also. Doc. So this is the doc string is there, right? See, this is more about the doc string. But the best way to go and learn from here, that's our documentation, and you use pipeline. Pipeline. So it's not behind the pipeline, it's more of that what the pipelines that we have. Go here, go here, go here. Maybe some other place will send you. So as of now, we have seen that two pipeline. One pipeline is about the sentiment analysis. One pipeline is about the zero shot classification. Next one pipeline is for the text generation, right? So I again imported from transformer, import pipeline, then generator. From generator, you just take a pipeline equal to text generation, and you just give some sentence, and then it will start filling next line one by one, next word one by one. Now you have to tell me behind the scene what it uses. Is it uses encoder type model, decoder type model, or encoder-decoder type of model? Who have said right the decoder only model? That is correct. Why? Understand. Remember what the task of the encoder. Encoder task to just learn the contextual representation, right? In encoder, what was happening? In encoder, only attention mechanism was happening, right? But in decoder, one by one, there is output is coming, right? So when and that output was it was the generation kind of the model. So here we have given this input, right? And then we start that, okay, do generate next one. So you can see that no model was supplied. So we are using OpenAI Community GP2. What is GP2? Generative Pre-trained Transformer. This is a decoder kind of model, right? Let's do now. Here you can see that, okay, can we also use something called means if here by default it's using GPT-2. Can we specify the model, that what model we wanted to use into a pipeline? That will also possible. And it can be like generator I'm giving, right? So with the help of this pipeline name, we can give that what model we want to use, right? So that is what is happening here. And then I can also say that maximum number of token you can give 30, and then number of return sequences equal to 2. Means you can give 2 sequences. So let's see. In this course, you will teach you how to. Then it will start from how to. After 2, what is that? In this course, we'll teach how to read a text, how to write a word you want, how to make very successful application of this kind. Please note that you need minimum 1 month. You die something. Why it stop as 2? Because I have given max length equal to 30. How to know that which kind of model? It depends on the task. You have to do the sentiment analysis. So for the sentiment analysis, do you need to generate something, or you need to just understand and the contextual meaning, right? Now, how I knew that it's a decoder kind of the model? Because it is a generation task. Generation task can be only done by decoder kind of the model. And yes, it is all from the Hugging Face. This transformer library is coming from the Hugging Face. Now, let's understand about this masking. So now the next pipeline I have choose as a fill mask. So I'm doing the unmasker, that this course will teach you all about dash models. If you means there are model which is only encoder model, there are model only decoder model, and there are model which consist of the encoder and decoder both. So BERT, I think you guys have already learned about BERT. That BERT is an encoder base. Just now, after I think half an hour before, I was showing you T5 model, where we were doing some translation. That T5 model is the encoder-decoder model. And here where we are doing the generation task with the help of the GP2 or distilled GP2 that are only decoder kind of model. So here I put the pipeline as a fill mask, and then I have given that top k equal to 2, means give me the 2 probabilities. Instead 2 probabilities, let me give the 3 probabilities and see how it happens. So it will give you the 3 probable word which can be used here. So it again use the mask language model, that is Distill Roberta, and then one is mathematics, right? Another one is computation, another one is the predictive. So these are the 3 top K. What is top K? Means top tokens which having the highest probability, right? Now let's use the next pipeline NER, right? So my name is Sylvian. Let me use my name is Girijesh, and I work at IBM in Bangalore. Bengaluru, right? Let's see how its NER things are happening here. Okay, so this is a person, Girijesh. This is a organization, that is IBM, and this is the location. This is Bengaluru. Okay, I have given the spelling long, but still it's able to Bengaluru. See, okay, location. Yeah, Bengaluru, but it able to fetch it that, okay, this word is location. This IBM is an organization, so NER also can be done. Remember, it was so difficult that time when we tried to train one model for the NER, right? Here, with the help of the pre-trained model and with the help of just using your pipeline, you are able to do your NER work with the few, just 2 line of code, right? Just 2 line of code. Now, what is a start and end? A start and end means this is the 11th. So it will start from the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is the 11th word, right? And 8, 9 means 8 words and 10 is there, right? 19th I'm ending. So this is the start of the word. This is the end of the word. So Hugging Face has made our life very easy. So in industry right now, most of the things are either happening with either Hugging Face or with the help of the LLM. Let's move further and try to do the question answering. Right? So for the doing the question answer, I need to give some context. So I'm giving, again, I'm going to take this same sentence, Control C, and I'm going to give it here that this is the context that I have. Control V. So my name is Girijesh and I work for IBM in Bangalore. Right? The question I'm asking that where do I work? So the model has been trained that from given context, it will answer this question. Let's execute this. So it says that the answer is IBM and it starts from the 34th and end at 37. The score is 66% of things that we have. Confidence score. So the last task is summarization. So this is the sentence, this is the paragraph, and I wanted it to summarize. So I use the summarization pipeline and I just simply use that. Now, can you guys tell me that in summarization pipeline, which kind of the model has been used? Any idea? From the class that we have gone through, right? Can you guys tell me that which kind of the language can be used? Now, why? Because see, here we are taking the encoder and then giving it the output as this. So it is more about a translation kind of the work or summarization kind of the work. So encoder will encode those things and then that will decode. In decoder part will do the summarization, right? And finally, if we want to do the translation, you can do the translation also. This course is produced by Hugging Face. Right? Now, I'm going to teach you one case study, and that's case study about the classification. And here we will be going to use the still BERT model. So what basically we are going to do? We are going to work with the still BERT model on the sentiment classification. So remember I was talking about the data sets. So from data set, right, import list data set. And then all data sets I'm going to, so from this list data set function, I'm putting into the all data set and trying to fetch you that what are the data sets are available on the hub. So let me execute this. Okay, so it's getting connected here. Okay, so these are the first 10. Now, let's say if you want to do for all, let me give you that what are the, how many. So just use len function, and then you can see that how many data sets are available right now. So 1,77,643 data sets are available. Right? Now, let's do one thing. Let's load one data. So I have loaded one data. That data set name is emotion. So I'm loading that. Could not find. Okay, so that data set might has been removed. Okay, emotions. It is S. Okay. Emotion is not there. So looks like this data set has been removed. Okay. Then what we can do? Let me see if this data set is there or not. Okay, this data set is there. This part is there. The original URL in the book is no longer available, so we'll use this one. And then you will see here. Then let me create this. This code is having lots of, okay, this code is not working. So better emotions data set, remove that. Okay. So thank you, Abhijit, for finding out the correct name of this location of this data set from the Hugging Face. I hope it will work now. Okay, we let it complete. Okay, this is done. Now the requirement is installing here. Oh, I need to tip it. Again, I have to do it. Okay, this we have done. Let's use this also. After selecting an order, we just need to train, evaluate, and deploy using. We don't need to train. This is what I'm saying since the beginning. Hugging Face is all about pre-trained model. We can fine tune if we require. Hugging Face does not provide GPU. Hugging Face is having collaboration with AWS or NVIDIA to provide the GPU. Now let's say, now it's working fine. Now let's see what is behind this. So we got our emotion. So now you can see we have a train, we have a validation, and we have a test. So in train, we have a 16,000 rows, which having the text as well as label. Similarly, in validation and test, we have a 2,000, right? Now, let's see, I'm creating train DS from train. So my data set got feature train and 60,000, I got a train DS. And length of the 10 DS you can see here is 16,000. You can also check that what is my train DS. So I didn't feel humiliated, label equal to 0, right? Let's see the label name. So train DS and column names, we have a text and a label, right? Now let's see what are the features that we have. So we have that text is string type, right? Label is having 6 number of labels. First is sadness, joy, love, anger, fear, and surprise, right? So text is data type is string, label is data type is class label, and these are the names that we have, right? Let's say if we want to see this fifth one. So this is the text and this is the label that we have. Okay, this 3, 2, and 3 is there. So text, I feel humiliated is 0. I can go from this to this is 0. And again, I am grabbing the post that I'm wrong is 3. This is how it has been done. Now, if you want to do only for the text, you can just see that it's only text will come here. Only text will come here. This is what in my dataset is not there. Okay, remove those. Local dataset, this remove those. This is also not required. Okay. Now, I'm creating pandas data frame from the dataset. So remember the datasets that we got, and then we are putting set underscore format equal to pandas, and then I'm just taking train, all the train. So we got it like this, that this is my text and this is my label, right? Now what I'm going to create, I'm creating one helper function. So this 0, 3 are the numbers, right? Just I'm doing the map, that what is my map. Remember here we came that these are 0, these are 1, 2, 3, 4, 5, right? So we need to just map it. So for that, I have created one function here that label integer to string. So here I'm just doing emotions of train, means train this data set, take the feature of labels, and then do integer to string of all the row. And that is how we will get this label name. See here the label name we got. This is the sadness, anger, love, and all those things, right? Let's see the class distribution. So I'm plotting here with matplotlib, and we can see the joy is having the most, after that followed by the sadness, anger, fear, love, and surprise, right? And why it came into the descending order? Because I put ascending equal to true. So it starts from the surprise and it ascending into the joy format. Now let's see how longs are tweet. So I'm creating one more column, word per tweet, and then what I am doing, I am just converting this text into the string, and then I am using split method. So what split method will do, split method will just convert into the different words. And then I'm just taking into, I mean, this still here, it becomes the words of list, I mean the list of words, and then for that list, I'm just checking the length, right? So this will be the word of per tweets, right? And then I'm going to put all the box plot. Any difficulty in understanding this code? So generally all maximum will be from 10 to 30. Then let's reset the format. Now do the tokenization. So first is character level tokenization, right? Then what we can do the token to IDs. That can be done, right? Then we can put for the input IDs. These are the IDs that we have. And then we can create one categorical DF. That okay, bubble like this, prominence like this, Megatron like this. This one hot encoded vector can be done. And then we'll create a dummies. And then finally we'll, with the help of the torch, PyTorch, we create one tensor and we'll get this dimension is 38 by 20, right? Okay, why we are creating dummy? So we want to, this word need to be converted. I just taken one example that these are the labels, right? For these labels, we use this word that we have, this word that we have, that's we want. I'm just giving the explanation that how this word is converted into a vector, right? So for character level of tokenization, we are going to take, and with the help of the character level tokenization, we'll again use to do convert this all these things into a vector. We are doing the one hot encoding, right? You can see. Okay, this is done. This is the tokenized text, tokenized index, and the one hot encoded vector is this. This is one example where the character level of tokenization has been done, but we are not going to use that. We will going to use something called the word tokenizer. So word tokenizer is also very easy. Simply you do the text.explit and then we do it here. Say we see that tokenizing text is a core of task of the NLP, right? Now again we are going to, this is one of the way, but one of the difficulty in word tokenization is, so in word level of tokenization, what we do, we break our sentences into words, right? Once we break this, and then we will going to convert this thing into a different, this thing we try to do into a one hot encoding or some other part. But this will also not working because it suffers from one problem called out of bag error, out of vocabulary error. Because this language is having, English language is having more than 3 lakhs words, right? That is why we have to take one middle part, and that middle part is subword tokenizer, right? And the subword tokenizer is already implemented into the transformer library. And what it do, it simply do that, like tokenizing was there, right? So it will take token is one word, then maybe IG is one word, and then ING is the next token. Text is one token, I is one token, then off is one token, similarly like that. It will try to break the one word into the subword such that it will make it, your out of bag error will be reduced. where out of vocab error will be reduced, right? There are some algorithms like a byte pair encoding and others kind of things is happening behind the scene. Now, one more thing, whenever you are going to use any large language model, right? By default, you will also have to use the tokenizer of that model. Means each model in Hugging Face library, if LLM is having, right, it also having their dedicated tokenizer. Okay, subword tokenization is not clear. Let me give you subword tokenization. I think this one is the one. Yes, try to understand here. So what is subword tokenizer? Means it will start with one character at a time, and then it's try to add the most frequent things. Like here, un is becoming, right? So un become one token, then rel become another token, then unrelated become another token, right? Means with the help of the sum algorithm, it's try to see that this unrelated can be divided into some different token or not. So this is the algorithms. Like one algorithm you can see here, this unrelated. So un is one token, relate is another token, ed another token. Similar like that. So this is kind of the breaking of the word into the different subword is the main crux of the subword tokenizer. And the crux behind this is only that it will reduce the out of bag error. And remember one more thing, that for every model like distill BERT I'm going to use, right? We have a tokenizer which is related to this. Yeah, it helps because let's say I am using ing, right? So let's say there is something called the, okay, you got it right, breaking. So break and ing. Now break is one subword, one token, ing is one subtoken. Now that ing can be used several, right? In run and running, right? In running also ing is there. So for the running, I have a one token ing which is already known. So we got this tokenizer, right? Then let's encode the text. Encoding has already happened. Let's see the tokens, convert ID into tokens. Now there is a two tokens. One is the CLS, one is the separator. These are very important. Now this some special token CLS and sep token has been added at the start and end of the sequence. This token differs from the model to model. Means some name will be there, but this has been added when we do the tokenizer, right? Let's print convert tokenizing text is the code cast of NLP, right? Let's see what is the size of tokenizer that we have. We have around 30,522. Let's say the model length. We have 512 is the model length. What is the input? We have the input IDs and the attention mask. Remember from the encoder side. Now we are going to tokenize the whole data set. So we'll create one tokenizer, right, in a batch, and padding equal to true, truncating equal to true. And then first try to tokenize first two word in the tokens. They have printed it out, and this is how it has been done. Then I am creating all this tokenizer for the all special token and all special IDs and sorted and created on data frame. So this has been done. And then we got the emotion encoded equal to emotion.map, put the tokenize, and here the complete things I'm using for the tokenized. You can see now the token names. We have attention mask, we have the input ID, we have a label, we have a text.
So what you're seeing on the screen, right, on the right side, on what you're seeing right now is essentially like an evolution of everything that has happened over the course of the last, I would say, the last 5 years. But as you already see, the timeline between 2021 and 2023, and actually even within 2023, is significantly stretched. The reason for that is because, as I had mentioned earlier as well, and what you may have also observed in the industry out there, is there has been a massive influx of a lot of different models in this particular space over the last few years. Why is that the case? Right. So you all have heard about the encoder-decoder architecture. You have all learned about the transformer architectures. Transformer architectures being one of the fundamental reasons why things have completely turned on their head, right? So what you're seeing here, let me take you to the photograph itself. So this is the link. This is actually a very interesting page. They talk about this being like a practical guide for large language models. Unfortunately, they actually haven't updated this. It would have been amazing had they updated this, but unfortunately, they really did not update this as much. But I think I still want to drive the point here. The point here being that if you look at this photograph, what is very clear is the fact that over the last 2 years or so, there has been a significant influx in the number of models and the type of models that have sort of come out there, and that have started being used abundantly. So you have learned about the encoder-decoder architectures. So what you observe here, right? So everything that kind of goes this way, they are all encoder models. Everything that kind of goes this way are all decoder models, and models that go this way are both encoder-decoder models. Now, what do I mean? What do we mean by that? So as you can see, when you talk about encoder-only models, these are models that are only taking, raw piece of text, and then you have an encoder model over here, and that is essentially outputting a sequence of numbers as an output, very popularly known as your embeddings, so to say, right? So your encoder-only models are very, very popularly referred to as your embedding models. So as you can see, all of these models, right? So your Elmo, your BERT, Roberta, Albert, Electra, these are all models, and even Distal BERT, right, by Hugging Face. All of these models are very, very, very popular embedding models. What do I mean by embedding models? Well, you can use them for other purposes as well, but fundamentally, they are doing either sentence embedding or they are taking piece of text and converting it into some kind of a numeric representation. They are not necessarily used for anything else beyond that much. However, right, on the right hand side, if you take, for example, the decoder models are all the generative models where they are taking the embeddings as an input, right? And then they're actually, or embeddings and another piece of raw text as input. And then they're trying to actually generate some new piece of information out altogether, right? Which is why, as you can imagine, your GPTs of the world, right? GPT, your Chat GPT or your GPT-3, GPT-4s, they all are essentially in this particular space because they're all fundamentally, decoder models. They are essentially the second half of the model where they are taking a piece of text as an input and then generating another piece of text as an output. They're taking a piece of image as an input, they're generating another image as an output. So that's the reason why they're all transformer models, but more importantly, they're all decoder models. And these decoder models that you see on the right top, they have just grown in number like crazy in the last few years, right? So after this, right, even in 2023, there have been other companies like Mistral, like Claude, or rather Anthropic. Anthropic is here, by the way. but Anthropic has actually done much better in the last 1 year or so. They have come up with their own models, and yeah, there are multiple players that have sort of come up in this particular space. What are they all doing? What they're doing, and here's I'm going to give you a bit of the industry play here as well, right? Before we go into the technicalities of it, how is the space sort of evolving? I'll give you a bit of that industry perspective, and then we will go into the technicalities and the actual implementation itself, right? So, what are they trying to accomplish? What are these models all trying to do? What are these companies all trying to do by creating these models? Now, what they're trying to do is they're essentially trying to pump in as much data as possible into these models. Firstly, the world has realized that this transformer architecture is a game-changing architecture, right? Until 2017, 2016, when people thought, you know what, the best way to understand language is to try and understand language sequentially. Until that time, at that point in time, we did understand the encoder-decoder models, but more from an RNN, recurrent neural network / LSTM lens, right? So data was being sequentially read, you are sequentially generating outputs. But thanks to the transformer architecture, it completely changed the game. It took away the whole concept of sequentially reading data. It said, attention is a completely new concept. It brought in attention, and it said, you know what, you just don't look at one word, you look at a bunch of words together to try and find what the next word is. It completely revolutionized how context was being perceived over the last few years. So, long story short, point is that it has been proven with extensive amount of proof, thanks to ChatGPT, as ChatGPT has contributed to that proof, that now AI models can really understand language. That has been proven beyond doubt, right? So now you can really think of, so if you, for example, remember, have you all used any kind of a chatbot from a banking website or chatbot from a, from let's say a telecom company? Have you all used? Yeah, Zomato. It was very bad. If you remember, like 3-4 years ago, they were very bad. I mean, honestly, even now, they're not that great. But what you will start observing is the quality of these bots will change leaps and bounds. The quality of these bots will change, and it's already happening, just to let you know. It's already happening. Why is that the case? Now, because you can tell these models something in plain English, and these models will understand how to react, how to respond. That's the beauty about these models. We all have used ChatGPT. Have all of you used ChatGPT? If you're not, you're doing yourself a grave injustice. Great, fantastic. So you all have used ChatGPT. So the beauty is that the moment you start using a tool like that, you're essentially putting plain English into it, and it's able to really understand these models very, very well. And all of that is transformer architecture. Huh? There's nothing different there. You must have learned about transformer architectures in your previous session. It's all the same transformer architectures. So there's nothing different there. So the transformer architectures are essentially helping, and all of these models are pretty much wired the same way. So point being that now the world understands that these AI models have the ability to consume natural language and spit out natural language. They have the ability to read English and spit out in French. They have the ability to read in Hindi and spit out in, let's say, some other language, some other native language altogether. So they have really, a language is a start, and now over the last 1 year, 2 years or so, you must have also seen that they are not just large language models. You also have large image models or large vision models, where you're able to create new images just on plain text, right? So you're able to create images, you're able to create videos, you're able to create some insane high quality videos using these generative AI models. Again, so this concept has been proven And the world is extremely bullish about this sentiment. If the world really feels that this AI game is going to really change the course for the next few years. Now, that said, right, let me show you. This is something that you all have heard of. Okay. We'll get into the technical details in a few minutes. Probably in the second half of the session, we'll get into the technical details. But I just want to focus on some of the more outside in perspective. Now, when people talk about these models, let me bring up a McKinsey article that has been published. I can see 30th May. Generative AI. Let's hope I am able to. This is the one. Yeah, this is the one. This is the article that I wanted to bring up. So McKinsey, I'm assuming all of you are aware of McKinsey. McKinsey is a very popular, consulting company, right? So they do a good job. McKinsey, Bain, BCGs, right? So for example, my company consults quite a bit with Bain. McKinsey is one of the other firms that we also consult with. They are a strategy consulting company, technology consulting company, whatever. So there are two very, very interesting articles that have come up exactly on the same day. So May 30th, 2024, there is this that was published by yes. So two articles have come up exactly on the same day, right? Oh, just one day difference, right? One on 30th and the other on 31st. McKinsey on one side is saying that the AI in 2024, Gen AI adoption spikes and starts to generate value. So they have apparently conducted a survey. But then what they're saying is that the AI adoption has really taken the world by storm. A lot of companies are adopting artificial intelligence, starting, AI has regularly been used, but 2023 onwards, a lot of companies have started to use generative AI based solutions within their ecosystem. And then what they're seeing across all business functions, people are seeing that there is a massive uptick in Gen AI based solutions. And they also talk about the fact that across multiple sectors, right, marketing and sales are the ones that are primarily using generative AI based solutions. And they also talk about some really interesting solutions here are much more likely now than 2023 to say that they're using Gen AI, right? So, and then they also talk about the fact that across all of these areas, as you can already observe, there's a lot of budget that's also being spent. So today, companies are at least spending a good $5 to $10 million. Bain sent me an article the other day saying that they're able to spend at least a good $5 million in per year in terms of budget as far as AI is concerned. So on one side, their survey is saying that the world is doing, or AI is really helping drive a lot of value. As you can see here, investments in Gen AI are beginning to create value. Whereas on the same day, you have another article published by the Wall Street Journal where they're saying the AI revolution is already losing its steam. The pace of innovation in AI is slowing, its usefulness is limited, and the cost of running of it remains exorbitant. So somebody else has actually written this article. Perfect. This is the article. Yeah. So this was the article that was published. The AI revolution is already losing its steam. So there are some companies that have definitely made money. Nvidia reported an eye-popping revenue last week. So last year they had they made their revenues, and some of these companies have made a lot of money. But it's only the technology companies like Nvidia's, like the Intels, like Microsoft's, and Amazon's making money, but not necessarily any of the other actual companies that are going to be using AI. or generative AI per se in their things. So they're saying that the OpenAIs are making a lot of money, the Anthropics are making a lot of money, but not necessarily any of the other companies, like let's say any of the CPG industries, or let's say some of the other industries. They are not necessarily making money because the cost of using these models is extremely high, and um, it is slowing down the rate at which people could actually start using it. So they gave some examples over here. My point is, the point that I'm trying to drive here is that these models, from a research standpoint, the world has really moved on. The world has really started to create, or the AI research industry has been doing an amazing job with regards to these models. However, when it comes to real world practical applications, there are still a lot of doubts. The world is sort of split, the industry is split. Some of them think that it is very valuable, some of them think that it is not very valuable, it is still very early days, and that the space will probably evolve over a period of time. Now, if you take a step back, what does this mean to us? As practitioners, as data scientists, and as practitioners who are going to be adopting the space of large language models, as practitioners of generative AI, one thing that we all have to bear in mind is that this, AI will evolve. My perspective and my understanding of this particular space is AI as a space will significantly evolve over the next few years. Generative AI is here to stay. The models will only get better. The model will only the large language models large vision models, the generative AI space will only become smarter and smarter by the day. Now, when they become smarter, they're also the hardware will become cheaper, and hence you and I will be able to use these models in a much easier fashion. People will start finding better applications of these models in real world scenarios. I will give you a couple of examples of how these models can be used, in specific areas. I can take, for example, my own industry, the world that I come from, the consumer packaged goods industry. A company like mine, or let's say a Pepsi or a Coca-Cola, all of us, we come from the beverage industry. So the kind of problem statements that we could use, that we could solve using generative AI, could very well be very, very similar. So I will give you a few examples of firstly how and where these generative AI models are being significantly used, the lay of the land, and then we will start looking at some examples of how you could maybe implement some of those. Okay. So I'll start with something more fundamental, right? So let's talk about firstly what is the space of Gen AI. Okay. So where did this space sort of come up? So let's understand how and what is this generative AI. So you remember in the beginning of the session we spoke about those big circles, right? So those big, the big AI, right? ML, and we told that ML is essentially a subsection of AI, and then we told ourselves that somewhere inside this also lies this thing of DL, or deep learning, which is essentially a subsection of or rather a subset of machine learning. And as you would have observed in your deep learning sessions, a lot of the work that we would have done regarding deep learning is very, very similar to that of your machine learning, right? So you just have a cost function, you're minimizing it, and blah blah blah. Now within deep learning, right, there are two kinds of AI under deep learning, right? Again, why deep learning specifically? Because see, the thing is, the moment you talk about deep learning sort of has opened up a very interesting set of a very interesting landscape, right? Because of the neural network models, it has created some extremely new avenues. So within the deep learning space, there are two types of problems. One is deterministic, right? There is deterministic deep learning or deterministic AI, and the other is generative. What is the difference between the two? So simple question. I have two images. one image of a cat, one image of a dog, right? And when I ask a machine learning model to say, you know what, between these two images or these two, sets of images, right? Try and tell me which one is a cat and which one is a dog. Let's say I have 10,000 images of cats, 10,000 images of dogs, and I have a machine learning model that I'm asking to figure, like, given any new image, learn from these images of cats and dogs and tell me on any given day, if I give you a new image, what is it? Is it a cat or a dog? It can be cat, dog, or let's take, for example, if there are even 100 classes or 1,000 different classes. In such a scenario, even in that case, what you're doing is you're getting your model, you're getting your machine learning or your deep learning model to simply learn the differences between each of these classes, right? You're not asking it to create anything new altogether, right? This AI model or this deep learning model is simply trying to understand sort of a very, very large, ultra complex decision tree of sorts, right? I'm simplifying this concept, but it is essentially trying to learn simply the difference between 10,000, 1,000 different classes, or five different classes, or 20 different classes. You're just asking it to discriminate between one class versus the other. You either refer to it as deterministic or discriminative is also another terminology that is often used. Discriminative AI, which is also the same thing. These two, deterministic or discriminative AI, essentially what you're saying is you are trying to simply find differences between two different types of categories, or 10 different types of categories, or 100 different types of categories. However, there is this completely other side of AI which which learns from a lot of data, but from all of that information, it tries to create newer pieces of information. It tries to create newer piece of content, newer sets of language, newer set of images, newer sets of videos. So that is referred to as this area of generative AI, where your AI is trying to create completely new content. Now, so far as you would have imagined, we never spoke about generative AI. Why? Because it was also not possible for us to, or these models weren't capable of doing something like that. It's only very recently, to some extent, there was a kind of category of models called GANs, generative adversarial networks, which was able to do it. But more broadly speaking, it's only very recently, and large contribution of that goes to the transformer architectures. Because of the way the transformer architectures works, because of the way the transformer architectures have this encoder and decoder concept, the moment you were able to build good decoder models, people now were able to create newer images. People were able to create newer content. So far, all of the models that we've learned, right, all of these discriminative AI models that we've learned, they don't create anything new. They're just taking an additional piece of information. They're either helping you classify or they're helping you make better sense of it. But that's pretty much it. But only generative AI models are truly creating something completely new. They're trying to create a completely new object. They're trying to create a completely new piece of text, and so on and so forth. And that is all broadly because of the capabilities of your encoder-decoder architecture or your transformer architecture, and more specifically, the decoder models are able to automatically create newer pieces of information. If you remember, your LSTMs can also create, where you remember the sequence to sequence models where you pass a sequence of images and then you're creating new pieces of new sequence of a new sequence of text. That those were also in some sense generative, but they were not very accurate. They were pretty bad. So, which is why, more broadly speaking, it's the transformer models that have helped us become or create a newer area or a completely new field of AI called as generative AI, which is sort of a logical extension of your traditional AI models. So don't think of a generative AI as a completely new field. Generative AI is still a subfield of deep learning. It's very much a subfield of machine learning, is very much a subfield of artificial intelligence. It is that minor area which today is creating huge inroads into how, or huge transformation in how people use AI on their day-to-day affairs. Now, because of these generative AI models, and mind you, right, when I talk about Gen AI and I'm talking about generating text, I'm talking about generating images, I'm talking about generating audio, I'm talking about generating video, and so on and so forth. Do you agree that deep learning is a part of machine learning? Within deep learning, you have learned about the LSTM algorithms, you have learned about transformer algorithms, transformer architectures. Do you agree that they are all deep learning? So if your transformer model is in your transformer architecture, right? So you must have learned about when you've discussed, I think this was the deck. I'm trying to pull up that particular deck actually. Yeah. So you heard of, you must have seen this, right? This is, I think, what was discussed with all of you. In your transformer architecture, when you pass a piece of text in English as an input, your encoder, fundamentally what it tries to do is it takes that piece of information and it converts that into some kind of a numeric representation. And then you take this piece of numeric representation, sort of some kind of a input. Your decoder will then start generating the output in whichever language you want. Right? Do you agree that this is still a deep learning model? Because these are nothing but, your encoders are simply nothing but, if you remember, they're all nothing but your regular deep learning models that are being trained over a period of time, right? Over large volumes of data. So now, if you simply break this, or so imagine you have trained this encoder-decoder model or this transformer model. Imagine you have trained this for a very, very, very large amount of time. Now you don't need anything else. Now, if you just take, for example, this part of the model, you pass it some piece of information, you pass it some numbers. When you pass it some numbers, it starts generating, or you pass it numbers, or you pass it some piece of text like this. However, it starts generating newer information. So imagine you pass information here in English, it starts generating information in Spanish. You can ask it a question, and then this one starts generating outputs, starts generating responses. You can now train these models to do some very, very specific tasks. You can ask them to do Q&A, question answering. You can ask these models to do this architectures to do, I'll pass some piece of text as an input, you generate, instead of generating text as an output, I can ask it to generate images as an output. So I can ask these models to do some interesting magic over here. That is the reason these models are essentially generating new information. They're generating new pieces of content which were not already available. So if a transformer model is a deep learning model and a machine learning model, generative AI models are simply nothing but a transformer model only. A part of the transformer model is simply nothing but a Gen AI model. Far from, AGI. AGI will take time, but this is a massive step towards it, because we have been able to get we have been able to get these models understand language like never before. Earlier, Google Translate used to use some very, very older models, older techniques. They were still pretty decent. But now the translation is just amazing. The translation models are very, very, very good these days. Over a period of time, if you observed, even Google Translate has significantly improved. The reason for that is because of these models. So Google Translate today uses an encoder-decoder generative AI based model. Yes. Yeah. Now, the part that I want to cover right now is, firstly, how can we use these models, right? So let me show you a couple of examples of how some of these models are being used. And then I'll take one step back and then I'll explain like multiple industry applications, and then we will go into something that's all the more, into something that's a lot more detailed. So just to kind of explain how this space is evolving, right? So one thing that you all have to understand is that these models that we are talking about, these generative AI models, they are all pre-trained models. All the most popular Gen AI models, or almost all of these generative AI models, they are all pre-trained models. They have all been trained on massive volumes of data, right? So the point that I'm trying to drive here is that these models have been trained on huge volumes of data. Now, in this space, right, let's take ChatGPT as an example, right? ChatGPT is just one of the many models that is currently available for people to use along with ChatGPT. All the models that I showed in the image previously here, right? So these are all the different generative AI models. As you can see, they're all different Gen AI models. The ones that you see on the right side, you have Llama 2, Llama, GPT-4, Galactica, Palm, blah, 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 Codex, Instruct GPT, GPT-3. There's so many different models that are currently available for people to use. What you need to understand about these models is that no, it's not that they only use a decoder. It's that they also have a decoder. It's a both combination of encoder and decoder. The thing is, they also have a decoder with them. If you just have an encoder, then you're only converting images to numbers or text to numbers. But if you also have a decoder, you can convert text to numbers and numbers to another piece of text or to another image or whatever. So they have encoder, but the decoder is the most prevalent one in this case. So the most popular models that you would typically refer to as, right? So your GPT, by the way, when you refer to as GPT, these are pre-trained models. When somebody refers to as pre-trained transformer, and you have, let's say, your models like Claude, you have models like Llama, and so on and so forth. There are a lot of different models that are available. All of these models, for a lack of a better word, are all pre-trained models. Right? They're all pre-trained models. On what data sets have they been pre-trained? You can consider pretty much the all of internet, right? So the most, instead of calling them pre-trained models in this world, these models are very popularly referred to as, any idea what are they referred to as very popularly? Foundational models. They're referred to as foundational models. Basically, they're pre-trained models. These models have been trained on the complete internet, all the books that have ever been digitized, all of the Google Images data. These models have been trained on such massive volumes of data. Even Gemini, for that matter, right? GPT, Claude, Llama, Gemini, any of these models that you take, they've all been trained on some huge volumes of data. The problem is that you and I will never be able to build a model like this because I have a 16 GB machine and you probably have a 16 or an 8 or an 8 GB machine. So you and I, technically, let alone training the model, you and I cannot even actually download this complete model on your own machine because these models are massive in size. Some of these models are 20 gigs, 30 gigs, right? So the size of the model, let alone the data set, once the model has been trained, the size of the model itself is 30 GB, 40 GB. So let alone training such large volumes of such models, you and I will not even be able to download them. So how can you and I use these models? There are 2 to 3 different ways that you and I can use these models. Number one. So we'll talk about access to these models in some sense. But within these models also, even if, let's say, you somehow find the way to get the compute to train all of these models, the second question is, man, how do I train them? What is the architecture that they have used to train these models? That is also not known to a lot of us. Not the architectures of these models are not open source. In some cases, like Llama, for example, the model has been open sourced, but not the architecture. Nobody knows what the underlying architecture is, right? In some cases, the model's underlying architecture has also been open source, but in most cases, nobody even knows Like for example, VGG16, if you remember, you knew that it had 16 layers. You knew that the first layer had how many ever, like, these many different, this was the input, this was the output size, and they were using these many different filters and so on and so forth. You don't have access to that information also for a lot of these models. I wouldn't say all of them, for most of them, you don't have access to them. So point is, one, these models are massive, that have been trained on massive data centers. Number two, these models, you don't even have access to the architectures of these models. You may know high level how they've trained it, right? Like for example, in one of the in one of the Microsoft build conferences, the OpenAI team had actually spoken about how they built the GPT 3.5, GPT 4 models. They had very, very high level spoken about it. My point is, there's nothing that you and I can even understand with something like that. They had spoken about the process of how it's been trained and everything, but now there are a lot of articles also that have tried to learn or build on top of it, and so on. Training process. Let me pull this up. So this is the one. So by the way, this if you ever have time, try to follow this man, Andre Kaparthi. He is very, very popular. By the way, this is sort of what they shared in public. They spoke about how a GPT model can sort of be trained, like very high level. Again, the underlying is a transformer architecture, right? So you know that. But the thing is, there are 4 different stages. There's a pre-training stage, there is a supervised fine-tuning stage, and there's a reward modeling stage, and there's like a reinforcement learning stage. There are apparently 4 different stages. And in each of these stages, there are some different types of algorithms that go in. And as you can see, thousands of GPUs are being used, months of training. Good examples are GPTs, Llama, Palm. They're all some good examples. And same is the case here as well. Reward modeling, reinforcement learning, supervised fine tuning. They're all different categories of different models. We'll discuss about this in much more detail later on. My point is that today you and I have pretty much very little visibility into the actual architectures of these models. What does that tell you? It tells you that these companies are holding on super tight to the underlying architectures. We know how they've been built bits and pieces, but not the whole thing, right? So high level, right? Raw internet, pretty much. $30 trillion. Sorry, 3 trillion large data set is what was used here. 3 trillion words, very much the whole of the internet. That is what was used to train the GPT models. And they're just throwing larger and larger volumes of data against it. So the second thing, so those are the foundational models and the architectures. We will understand some of the details of these foundational models as we go along. So now, as I said, then how do you access these models? So as I said, here, some models are closed source. Some of these models are closed source. Some of these are open source. Closed source meaning the source code of training is closed, and here open source meaning the source code of actually how the models have been trained is open. In both the cases, accessing these models is very, very complex, it's very challenging. So how do you access these models? So meaning, how do you do inferencing? So to inference these models, there have been a lot of companies that have come in and that have created these API layers on top of it for people like you and me to access these models. So they've said, be it the open source model or the closed source model, we have access to, we have built these APIs, around this that can give you access to all of these different models. And they say, we will, if it is an open source model, we will host that open source model on our own compute. And then we will simply will have to access these through an API. If it is a closed source model, meaning this is a model that is hosted by OpenAI themselves, then in that case, we will just give you a very thin layer through which you can access these models. Meaning, we will abstract all of the complexity for you. You don't have to worry about anything. So these APIs per se are being built by your companies like Microsoft or AWS. These cloud companies are the ones that are actually building a lot of these APIs or providing the compute for people like you and me to access. So why are they doing that? Because you might want some kind of enterprise level security. You might need some level of some form of enterprise level guardrails around how the cyber security concerns and everything. So in all of those cases, Microsoft's and AWS's are providing these open source as well as closed source models in your tenant, in your Azure tenant, or in your AWS tenant, or in your Google Cloud Platform tenant, in your GCP tenant, so that you don't have to download the models, but these models are guarded by your own tenants. So there's security and everything is sort of taken care of. Now comes the poor boy or the poor girl, the developer or the data scientist who's trying to access these models. Now, how do you access these models? So you can access these models at multiple levels. If you want to access an open source model, you can go and access the open source model as well. You cannot access GPT. You can try and access some of these open source models. You can go to GitHub, or you can go to Hugging Face models, and you can download Hugging Face Hub, and you can download some of these open source models, and then you can try and do it yourself. If you say, man, I'm not very keen on downloading the raw model and then working on top of it, I am just interested in using the model in as is, then you can just access some of these APIs either through the APIs that are provided by the companies itself, right? So like Google, Microsoft, AWS, or OpenAI, or you can also sort of host one of these models on like a VM and then try and access it. Generally, this is sort of the most preferred route. The third way for you to access these models, right? The third way that you can access some of these models, I wouldn't say it's like a way, but it's more like a developer sort of a approach. You can say, you know what, and the problem is, because you are going to be accessing the GPT models, you're going to be accessing the models from from Llama, you're going to be accessing the models from cloud. There are some companies, what they have done is they have written a small, again, an orchestration library. So these are libraries, these are more Python libraries to simplify how you can access these models, right? So what you could do is you can sort of download some of these libraries, get access to the underlying models, and then you can start accessing straight away. So these libraries are libraries like LangChain, Llama Index. There are a bunch of different libraries that are available over here. So you can sort of go download these models, and then you can access these models straight away. So these are all the different, this is sort of the current lay of the land as far as the Gen AI models is concerned. Yeah, the second way is like, you don't need to host the model yourself. You don't need to download the model yourself. All that you have to do is you will have to basically simply access these models. See, like you're in an enterprise setup, so you don't want to download the model, you don't want to use an open source model that somebody else has hosted. All you are interested in doing is, and I need a model that is a pre-trained model that is hosted in a secure environment, where even if I put the data in it, I am not going to have a problem with it, right? So I want to access, I need a system where something like this is nicely available for me to work with. So in such a case, what do you do? In such a scenario, the best way to kind of think about it is that what you could do is you could try and like access some of this through the Azure OpenAI models, or you can try and download a model from the AWS Bedrock, and you can access it or whatever. So those are like some of the other options that are available in this case. So LangChains and let's say LangChain or Llama Index, they are not model providers. They are just small orchestration libraries that abstract how you can access multiple models. Because if you have to access, let's say, the OpenAI models, you need to write a code in a certain way. But if you need to access, let's say, the Claude model, you need to write the request body, and the code has to be written in a certain way. Same with, let's say, the Llama Index. So same with the Llama models. So how do you like create one common library, a middleware, or an orchestrator that helps you access all of these different models in like a very abstracted manner. Exactly, the abstract factory pattern. That's what a LangChain really here is. They are just an abstraction layer. And they also provide some capabilities, but they're pretty much an abstraction layer. Okay. So the GPT-3 and the GPT-4 models, even if they are closed, you can access them through Microsoft. That is Microsoft's game, by the way. That is what Microsoft is trying to do. So that's the beauty. Microsoft and OpenAI have a deal here. So what they're doing is all the OpenAI GPT-3, GPT-4, GPT-4o models, all of them are now being made available through Azure OpenAI, which means that these models are hosted on Azure and they can provide you access through your Azure tenant. So that's the beauty of it, number one. There's a lot of AI wars that are going on over here. Microsoft is after everything and anything. Yeah, literally. So I don't know how many of y'all followed the saga of Sam Altman getting fired and again being made the CEO and everything of OpenAI. Yeah, it was crazy. It was like a soap opera. Luckily, I was in San Francisco at that time. The day when Sam Altman got fired, I was in Mountain View. I was there, and I was like a commotion there. Everybody on the floor were like talking about. I was at Microsoft, and Microsoft was like talking about this, and Microsoft immediately made the offer of getting Sam Altman as onto Microsoft and then give him a separate team and everything. So it was kind of funny. But a lot of that happened on like one evening, one weekend. It's super funny what everything happened there. All right, so let's go. Let's go one step further. So how do you now access these models? Okay, so let me quickly show you some. Yeah, I want to show you this, like a very interesting, set of companies that are sort of playing in this space across different global landscape. This is sort of global landscape of this. So, for example, in North America, if you look at it, you have, again, these are all different companies that we're referring to, right? So in the multimodal space, you have Gemini. These are models, by the way, Perplexity, and Meta and ChatGPT, or rather the OpenAI models, so on and so forth. You have all of them in this space. From a chatbot space, you have these Lean, Observe AI. They are all different companies. On the tech space, blah blah blah. So in Europe, again, you have different companies. In Asia, AI21 Studio. In China, they're doing a fantastic job. Tencent is doing a very good job. By the way, China is playing a massive game here in this area as well. This is the other thing that I wanted to also show you, which is, see, there is one thing that I also want to talk about here. So you have seen this space, right? Now, today, when people talk about the fact that a lot of companies are making a lot of money in this space, unfortunately, India is not in leading in the space. They're playing catch up. In the AI space in general, India is sort of playing catch up. So yeah, we're kind of punching above our weight a little, at least in the tech space. Unfortunately, I don't know why that's the case, but that's the case. So if you think of which companies are making money, what kind of companies are making money here, in the in this Gen AI space. So you can think of all the different players over here, right? So if you think of it, ChatGPT is free. There's a freemium model and there's also a pro model where you are expected to pay like $20 a month. So ChatGPT is making money, or OpenAI is sort of making money through that. In the enterprise space, of course, companies like Microsoft and AWS are making money. Llama Index, LangChains, these are open source libraries, so they're not actually making any money. They're open source library. They have their own platforms that they have built, so they are probably making some money. So if you look at this complete ecosystem, who is actually making the most amount of money? Who do you think is minting money here? Compute providers. So there's even one level lower here. So there when you talk about compute providers, there are two forms of compute providers, right? Compute providers to train the model and compute providers to do the inference of the model. The company that made shitloads of money is Nvidia. Why? Because Nvidia graphic cards, GPUs are needed to train such massive data sets or massive models, and Nvidia's made that guy has become rich, right? So he's become a billionaire. He's the newest billionaire on the block, right? So he has suddenly made most amount of money that anyone else could have ever thought of, right? So the companies that are making the most amount of money is the ones that are at the lowest end, right? So the companies that are giving the compute providers. So your Nvidia compute and hardware providers are the ones that are making the most amount of money. Nvidia, you have Microsoft, you have AWS. Google is trying to make money out of this, but that's where the money is. Most amount of money is sort of going in here. The second layer of money is of course going into all of these companies that have created platforms. So LangChain and Llama Index, like companies, they are never making any money. But what they've done is they have created some observability platforms, or LLM ops is what they call it. Right. So there are some companies that are in this area. They are making some money. They're not making the most amount of money. So as you go from bottom to up, or rather, the money is higher money, lower amount of money, and as far as the value chain is concerned, then AI training institutes are probably way at the top. They're making the least amount of money. Trust me about it when I say it. They're making the least amount of money. Right? Those are surrogate businesses, right? So they're not actually making any money because of the industry. They're just surrogate businesses that are just trying to like Bheti Ganga mein haath dholo types. But the thing is here, the next companies that are actually making a little bit of money are the companies. These are the product firms. So, right. So these are the product companies that are building product capabilities on top of it. Like for example, no, not Meta, not Google. So maybe something like that. But if you think of, again, sort of, they are also making money here through their products. So Microsoft Copilot, right? Or you can think of AWS's AI capabilities, or you can think of, let's say, somebody has built, let's say, a tool that will give you access to that will help you make analysis much faster. Somebody has built you something like a mid journey, for example, is probably going to be here. Somebody has built a small product that will help you, let's say, analyze PDF documents better. So all of those products. So SaaS capabilities, the software as a service market, that is what's making the next amount of money. The last and the least amount of money are the actual companies that are using AI. This is the actual industry, right? The final users, consumers of AI, right? So like for example, the manufacturing industry, the CPG industry, where AI is actually being implemented in, they are making the least amount of money. because they're at the top. They're paying for all of them, right? For example, my company pays all of them, right? Because I am looking for a tool that will help me make that will help me, that let's say help analyze my unstructured data. So I will also need to create a piece of compute that will probably help me make my models better, right? I'll probably need to also pay these companies like LangChains and these of the world, because my data scientists will require some kind of LLM ops. So I'm sort of paying everyone from top to bottom. I'm paying everyone. So the biggest hit today, and remember, the cost of all of this has to be borne by these industries, not the end consumer. So, for example, we make beer, man. So, as a CPG industry, I cannot cascade this cost to my end consumer. If you are drinking beer, if I simply say I'm going to increase your beer price by 2 rupees because I need to bring in new AI capabilities into my ecosystem, they're going to be like, what the heck? I don't care. I'm going to hit my sales. So without impacting my end consumer, I will have to soak in all of this. So the only way to do that is to piggyback on the promise that AI will help cut jobs. Do you understand that? The only way that I can use all of this, that I can actually leverage all of the AI capabilities, is if this really works. I'm happy to invest in all of these areas. If and only if I have the promise that AI is going to help cut jobs, or AI is going to help me make, become a better company, meaning it's going to help, do some things faster. It's going to help me do some things easily. I don't need as many people to do the same job, or rather the same number of people can do much more than what they were doing previously. The productivity is very, very important. If AI promises productivity, then all of our companies are going to invest. That is the narrative that I am selling in my company as far as AI is concerned. We're saying, you know what, if you bring in AI, it'll help you do some things much faster. It'll help you maybe, become more productive. Yeah, not cut jobs. Let's be very honest here. When we say we're not going to cut jobs, we're not going to basically cut jobs, but we're not going to hire as faster either. Right? We're not going to be hiring more people. If 20 people quit my company, I'll probably only backfill for 15. That's what we mean by cutting jobs. A lot of the industry, you need to understand that when we say we're not going to hire, we're not going to backfill, that will not, I mean, that's the whole, see, that is the sentiment that's out there, everyone. You need to understand that this is why a lot of companies are firing people. This is why, see, you also have to understand, why did Microsoft fire so many people last year? Why did a Google fire so many people last year? That's because in 2022, because of this whole hype cycle of, yeah, AI is going to come, everybody started building some massive AI products, and suddenly you started to realize that there are no takers for those products, and now you have created a massive bulk at your own. These product companies were soaking in all the pressure without really being selling it to the companies. So automatically they had to fire people. They had to let go of people. So again, remember that this is an eventuality, right? If AI is here, AI will have to prove value for it to stay. I want you all to understand that part. But cool. Okay. So that said, now let's go one step further, right? So we're going to be leveraging some of these, orchestrators. We'll try and access some of these models that are available out there, and see how it works. Okay. So let me go here. I'm going to start with showing you. So I'm going to be using the OpenAI models as a part of the session. Let me just go back here, playground, chat.openai.com. Cool. Okay. So you all have used ChatGPT. Okay. And you all must have also used, I don't know if you have used Microsoft Copilot, but I am a huge fan of, not fan of Microsoft Copilot, but the idea of a Copilot. I'm a huge sucker for it. I think it's like a massive opportunity for us to kind of really take this forward. So if you don't have access to ChatGPT, you can also use Microsoft Copilot. It uses GPT-4 at the background, and it's free for people to use as well, actually. So everybody can use it. I think there's some credits if I'm not wrong, but everybody can use it if you think of it. So yeah, you can use both, either this or that. Yeah, man, I mean, they're all the same. Gemini is better, ChatGPT is better. ChatGPT is not funded by Microsoft. I mean, OpenAI and Microsoft have a deal, right? The deal is Microsoft funds the OpenAI projects, but OpenAI then takes their models and lets them host, and they have an exclusivity deal to have OpenAI models hosted on Microsoft Azure. That's pretty much it. But what you will observe is these models are available on both sides. Microsoft has their own Copilot. ChatGPT is also there. ChatGPT is for everyone. ChatGPT is not necessarily, I mean, this is also hosted on Microsoft, but Microsoft has nothing to do with this. This is just a pure play, OpenAI's interaction with the external world. There's no Microsoft play here at all, so to say. This is Microsoft's way to interact with the end consumer. So we all have used these models, right? So, like for example, if you ask a question, explain superconductors like I'm 5 year old, and then it comes up with a nice response for you immediately. As you can see, you have the model and everything also over here, and then you can ask for like a bunch of different things. So point is, when you ask a question, it generates a nice response for you immediately in this particular case. So this is how these models sort of work. When you ask a question, there is a quick response that is being generated. Now this UI that you're seeing over here is for people, is for everybody and anybody to access, is for non-practitioners, right? So it is for the common man, right? So to access. But for you and me, because you and I, we plan on building more complex systems, right? So we are not going to simply be using it just to do Q&A. We'll be using it to do Q&A and much more complex systems. So in such a case, we need access to the underlying models, right? The model itself. We need access to the underlying model itself. So how does that work? So to get access to the underlying models, so you need to understand that all of these models that you see here, they are all powered by, as you see, the Chat GPT that we're talking about over here. Chat GPT is like a product that has been built on top of the underlying GPT models, the GPT-4, GPT-3, GPT 3.5, that suite of models, right? So 4.0 and so on and so forth. That suite of models, the foundational models are those. ChatGPT is like a capability that has been built on top of it. So when you ask a question to ChatGPT, ChatGPT somehow finds a way to route it to GPT-4 or a GPT-3, and then generates a response, and then it returns it for you back onto the UI. And in between, there are like a bunch of different steps that happen over here. So exactly, ChatGPT is merely just a chat interface. It's just a web product or a web interface for you and I to simply interact. The underlying models, right? So the underlying models over here are still the foundational models that we're referring to. So what you and I will be doing is we will not be accessing these models through here. We would rather be accessing these models from there, right? So we will get access to the underlying models, the underlying complex models that you see over here. We'll try and get access to these models. What will we do with getting access to these models? So once you get access to those models, then we will start seeing all the different functionality that you are able to do through the chat interface. We will start doing it through backend. We will do it programmatically. Now, when you start doing it programmatically, then you can see how you can integrate and create those smart workflows and integrate that into your pieces of work, right? So we will get to that. Like for example, how can I use natural language to, let's say, do some data analysis? Here you will have to type it out and everything. You will have to put the data set, paste the data set here. There's certain limitations beyond a certain point. However, you could kind of do that in a much more efficient fashion if you have access to the underlying data sets. So we'll talk about that, right? So we'll try and see how we can do all of that when you get access to the underlying model itself. So let's firstly see how to access the underlying model through APIs, and then we will take it one step further, right? So the first step is to be able to access the models through APIs. And then after that, we will see how we can start building slightly more intelligent workflows. ChatGPT is trying to, because ChatGPT is not trying to answer these questions based on what it has learned. ChatGPT is trying to also, so there are two kinds of information that ChatGPT has, right? ChatGPT has learned some information, and then the other is ChatGPT is also trying to access all of this information in real time from the internet, extract it, summarize it, and return it. So it's doing both, some from its past knowledge, some in real time. So it's doing sort of both in parallel. The real time thing is referred to as retrieval-augmented generation, which I will explain. And some by default bases some of its history. So we will learn both. We will try to understand both. Cool. So there are two things, right? There's a pro version and there's also like there's the free version. The pro version is it has access to the internet. The free version doesn't have access to the internet. So it only has access to data until a certain, not data, but it has only been trained until a certain point. So when you ask it any question, it only has memory until at that point in time. So it will only be able to return responses until that time. So the model by itself does not have any knowledge. Okay. The model just has the ability to answer questions. But if you wanted to answer some questions basis some information, then it doesn't have the ability to do so. So what do I mean by it? If you ask it a question, the model will return a response basis everything that it has learned so far. It is not holding any data. So when we say that the model only has knowledge up till a certain time, that means it has only learned about the world affairs until that particular point in time. So if I ask the open source ChatGPT what happened to Donald Trump during his rally recently, it will not be able to answer, right? How do you think the world would have reacted to, let's say, somebody like a Donald Trump getting shot very recently? It would not have access to that information because it doesn't know that actually Donald Trump actually got shot. So my point is, it does not have the necessary context. It might just make up something for you. It might just make up some random stuff for you. But the underlying understanding of an event like that, it doesn't have that information because there's no data backing that information. Had it been the case, it would have been trained on that concept, those words and everything like that. So, okay, simply put, the model has no knowledge. The model only has the ability to understand language, right? It is just a great speaker without the underlying data corpus. It is just a model that has learned a lot of books, that understands a lot, that has learned how to consume information from a lot of these books. As a result, it may have a perspective about what is being spoken about in those books. That's pretty much it. But it's not holding information by itself. Number one, it's just like any other deep learning model. Number two, if you wanted to comment on anything that's happening right now out there, you need to give it information. You need to provide an environment for it. You say, you know what, take all of these 100 documents, bases all of these 100 documents. Now you tell me what do you think is happening? Let's check. Comment about the recent so there you go. It has access to this information. It is open to internet now. This is because I think this is a GPT 4.0 model. If I change it to it's only available. So okay. So clearly this is only the GPT 4.0 model, hence it is nicely access to this information. It's not real-time use product, but it is very clearly accessing this information from this thing. So because they've swapped it to 4.0, 4.0 now has access to internet, so everybody can try it. So long story short, the point is yes, it has access to it. It has fetched information from the internet, as you can see. So the point that you need to understand is what it was able to do is it is able to make this commentary simply basis these articles. It did not make up stuff by itself. It looked at all of this information and it summarized that information and it returned the response for us. That is what I want you to understand, that there are two aspects to this. The model is not coming up with information all by itself. The model is only looking at this information from historical data set, summarizing that, and then it's returning that back to us. So that is one thing that I want you to understand. Funny thing, and that is, by the way, is retrieval-augmented generation. So what it just did is retrieval-augmented generation, and that is exactly what we learn as well. Cool. Okay, awesome. So let's go. So what I'm going to be doing for the next few minutes is I'm going to be spending some time trying to explain how this piece works. I just want to also pull up one. So this is a presentation that I got from we did a small workshop at MIT, and then for some of our leaders, and then this is like a very interesting piece of presentation that I got there. I'm happy to actually share it with you. Okay, cool. This is like a session that they actually do. It's called LLM fundamentals and stuff like that. So this was like some topics that were covered during the session. One thing that I just wanted to show you all is this. This is what I was talking about. So the GPT-3 model, right? The GPT-3 model. This is sort of a good piece of information that I think was available in that document. So this is what I was talking about. So if you take, like, for example, the GPT-3 model, I'm not even talking about the 3.5. We'll talk about GPT-3. Approximately 30 billion sentences from the internet and books, right? 410 billion. So these are all the different four data sources that they extracted this information from. Common Crawl. Common Crawl is like an open source internet, crawled internet of sorts. And there are a bunch of different books. Wikipedia is one of the smallest data sources here, as you can see. Common Crawl is like the largest data set. So very much the internet. And this is, I'm talking about GPT-3. GPT-4 and GPT-4.5 are even much, much, much larger than this. So going back here, so what are like how do you like access a model like this, right? So let's start from there. The first step here, and this is what I was showing you all right a while ago, is to be able to access this underlying model. Now, to be able to access this underlying model, the first thing is you need to get access to the model itself. Right? So how do you access the model? I'm going to be using the ChatGPT, or rather the GPT suite of models for this example. And what I have done is I have actually purchased the keys. So I have approximately around, I think, $50 worth of I have $50 worth of credits in this case, and I'm just trying to use that information. Yeah, this is for all of my sessions. So I have a key that I've created, and I'm going to be using that particular key, and this key is available for me to use here. So a key is required for us to be able to use these models. Okay, this key is only the only way for us to try out some of these models. Earlier, they used to actually give away credits, $15 worth of credits for everybody to use. Unfortunately, they've discontinued doing that now, and for that reason, not all of us will get it for free. Now the thing is, so now that I have access to that particular key, then how do I use the model? Right. So from where can I get the model? Where can I get access to this particular model? So let's actually go here. Right. So there are. So let's go to the docs. So here, now OpenAI has built their own interface, as you can see here. Right. So rather their own documentation. They have their own library from which you can access the models. Right. There are a bunch of different models that are available. They have also some information on how you could do prompt engineering, stuff like that. But we'll firstly understand how to get access to some of these models. So first things first, let's try accessing the model directly through the OpenAI library itself. So this is how you will have to access the models. Let me just quickly copy this piece of code, and then let's go to Python. Let's go to this file, new file, Jupyter Notebook. And exclamation pip install. I think it's OpenAI, right? What's the name of the library? OpenAI. I think this already exists on this particular environment of mine, but let's install it anyways. Perfect. So the library has been installed. And then let's go. So from OpenAI, import OpenAI. And now, if you want to access the GPT-4o model, this is how you go about it, right? So you're saying now there are a couple of things that you need to understand. So there's client dot chat.completions. So I'm creating an OpenAI client over here. What I also will have to provide is the API key, API underscore key, which by the way is something that I have access to here. This key is the same key that I would have got from the OpenAI website. So if I actually go back to the, to this, if I actually go back to API keys, this key is what it is. If you don't have a key, you can just click on this and it will create a new key for you. Okay. And I'm using the same key over here. So that key will provide me access to this particular GPT-4o model, and it is asking a question, write a haiku about AI. And now what you will start seeing is the response. That's the completion. That's the chat completion. So you asked it a question and it has responded to you. You see the message here? Code weaves through silence, machine mind wakes, learns and grows, whispers of the cloud. So, and it has, as you can see here, it has taken the role of an assistant over here. So as you can see, there are two roles, the role of a user and the role of an assistant. So there are three things that you need to understand. When you ask a question, right, there are multiple ways you can ask these questions. One is you can ask a question there are three roles you could take. There is the role of a user, there is the role of a system, and there is the role of the assistant. The assistant is the bot, user is you, and then there is, of course, another role of the system. Meaning you might want the AI to play a specific, you might want the AI to sort of play a very, very specific persona. You might want it to bear a very specific persona, and that persona can be embedded into the system prompt. I will explain that as we go along. But broadly, when you ask a question here, this is essentially how you can get access to the 4o model. Instead of the 4o, you can also ask it to take any other model that you wish to. 3.5 model, not the 3.5, the 1.5 instruct. 3.5 unfortunately is not a chat model. 3.5. What is the model that has access to us? Yeah, so this is, let me actually just find the models here. Oh, there are only two models that are available. There is the 3.5 Turbo. This is the only other model that is currently available. The 3.5 is not available. Let me click the Turbo. So perfect. There you go. This is the older model. This is one of the older model, and this is generating, generating a response for that particular older model. And again, a slightly different sort of a response, as you can see here. Artificial mind, learning and evolving fast, future of the world. This is like a haiku that it is creating. And you can also, of course, ask it to create different sort of, different kinds of questions. What is the differences between AI and Gen AI? And it will start generating a response for you in a minute. Awesome. So now if you look at the result here that it has generated, yeah, artificial intelligence, AI or artificial intelligence refers to a simulation of human intelligence, blah, blah, blah. So this is the same exact response that you would have seen if you had asked a question like this over here on the chat, the chat response as of now. Now, the thing that I want you to understand, and this is the part that you need to be very, very careful about, is this OpenAI model that I'm currently using is a model that has been hosted by OpenAI. This is not an enterprise instance that I'm using. If I were to use this particular model, I would think about it like a million times in my office, because I don't know if this is safe or not. I don't know what OpenAI is doing with it. OpenAI, of course, claims that if you're taking a token and everything, we don't use it. But man, who are they, right? So like, I mean, how can we trust? So this is one thing that you will have to be very, very careful about for sure, right? Then again, as I said, there are two things that you can do here. One is the role of a user, and then you can also here pass Here you can get it to ask a completely different question. You can say, hey, I can get it to bear a certain specific persona here, right? And I can ask it to sort of operate a certain specific way. Like for example, here I can say, hey, look, you are uh, a tech blog. Keep the article is very short and the response is short and engaging. So what I'm asking the system to do here is I'm saying, hey, answer this question, but every time you answer this question, bear this in mind, right? I'm specifically asking it to bear a specific persona while it is responding. And I can also say, respond back with always with specific examples or include very contemporary examples of the questions asked. So that's it. So I'm asking it to bear a specific persona here, and then I'm asking it to reply back to the same question. But this time, if you observe, that particular question is going to be responded very differently. So by the way, let me just print completion dot choices of 0 dot message. Perfect. I just remove the print statement here. I hope it prints it. Cool. Okay. Okay. So now I'm going to ask it to respond back to this. Message one of, oh, sorry. So sorry. Role, colon, system, content. Perfect. Now you go. There you go. And now when you look at the response, this response is hopefully going to be slightly different than the other. Role of an assistant, completion. Perfect. So personalized medicine, blah, 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 whatever the rest of the example. So it's the Apple Face ID. So here it's actually including the responses of Apple Face ID. GenAI can be applied in understanding genetic mutation and can cause diseases like cancer, leading to targeted treatments of patients, whatever. Now, I don't know why it's saying GenAI for this, and I can, if I switch to 4.0, you will start observing that the quality of the responses are different. And ideally, what what they claim is that this is actually much faster as well. The 4.0 models are much faster as well. So artificial intelligence and generative AI are both hot tech topics, but they aren't the same thing. AI refers to machines designed to simulate human intelligence. Classic examples include recommendation algorithms, blah, blah, blah. So again, as you see, it's also adding its own, all of the smileys and, these imagery and everything as all by itself. So yeah, that's how your OpenAI libraries sort of work. However, you can sort of repurpose this for multiple other reasons as well. So for example, I can say, hey, here's the GPT 4.0 model, and I'm actually going to swap. Doesn't matter actually. And I'm going to ask it a very specific question, and I'm going to say, I'll just swap it. Sorry. Cool. So, and I'm going to say, look, you are a data analyst in a technology company, and then you write high quality code and make high quality bug free code, and your expertise is in Python and SQL. So I've essentially given it a persona now. Now what I'm going to ask it to do is I'm going to say, write an SQL query, or write an SQL query to analyze sales of a market in in Europe. And here I can say you have access to the sales database and user customer demographic. So let's go. So that's a question like that. And then you can look at, so now it's taken a very, very different persona. And the hope is it comes back with an actual SQL query here. Certainly, to analyze the sales of each store in Europe, you would typically need to access at least the two tables, one containing the sales data and then the blah, blah, blah. And so it's actually here, as you can see, it's actually given you the SQL query as well. And all of this calculates the total sales for each store, group by, blah, 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 and everything. What I can ask it to do here is, and this is where the whole part of automation that I was referring to sort of comes in. And I can ask it to start being a little more, I can ask it to start being a little more creative in how it is. I can say, ensure that the results. So all of this I'm putting in a system prompt, which means that I'm asking it to specifically bear, whenever it's responding back to any question moving forward, it'll always have the same kind of the system behavior. Ensure that the results are always returned, and ensure that you only return the SQL query and or Python code and nothing else. The response can be as a string in a JSON. So now I'm asking it to be very, very specific. I'm saying don't return anything else. Return the SQL query in a JSON format. So perfect. There you go. So that's it. So it simply says query. It's a JSON string, query, and the actual query itself. So now you can imagine, right? So if you can think of something like this, now whenever I have a question, I can sort of build like an analyst on top of this. Imagine I can stitch I'm able to build like an agent which keeps going back to this piece of code. Every time I have a question, I simply put that question in here in this location. And every time I simply get like an SQL query as an output, and I can have like a simple chat interface, and that SQL query can be connected to the underlying database, to my actual database. It fetches that response and then returns that as a chart or something for you. The whole thing can sort of be fully automated for you moving forward. Does that make sense? Do you understand how this works, everyone? Do you understand how you can use these models under the hood? Instead of using the chat interface from the front end, you're using the underlying models, and to interact with the models, you're currently using the the OpenAI chat interface here in this case. Okay. Now let's go one step further. Okay, so these are like some very obvious examples. Now we can sort of go one step further. So now the question is, how can I now start? So imagine if I have to give this one a little more context, right? So if I want to tell it, look, you answer the question only in a specific fashion, but answer the question from can I provide my own file to this? Or can I ask it to, create a particular piece of analysis basis some piece of data that I pass to it right now, right? Instead of I simply asking it to write a SQL query, can I say, hey, here's a SQL query, write a SQL query, but here's a sample data set. Can you write a SQL query to analyze this complete data set? So now the question is, how can I take it one step further? How can I ensure that all of this information that you see here is something that it is actually able to not just implement, but more importantly, something that it can actually analyze from an existing piece of data, rather than just trying to come up with something. Here, there's no real context that it needs to refer to. But imagine if it needs to refer to something before it responds back. For example, if I say, hey, here's my website, why don't you actually go ahead and help me answer some questions based on this particular website? So now things here are getting slightly more and more complex, right? So, or if I say, here's my data set, why don't you actually go ahead and start answering questions on this particular data set for it? Or here's all of the PDF documents that I have. Why don't you now start answering questions for me basis all of this data? Now, this is where things can start getting a little tricky. Things can start getting a little complex. That is where you will require, slightly more sophisticated frameworks for you to deal with something like this. That's number one. Number two, as you can see here, right? So this code is a little, for a lack of a better word, this code can get a little irritating beyond a point, because every time you have to write the system prompt, right? I mean, why do I need to write a system prompt? I can actually write like a wrapper on top of this, which by default sticks the system prompt every time I ask a question. Like, why should I specifically add this as like another thing on top of it every time I'm asking a question? That's like just duplicating a lot of code, duplicating a lot of information. So can I like make this experience for me to interact with these models a lot simpler? Absolutely, yes. And that's where I will introduce you to the LangChain models in the next few minutes. I'll actually walk you through the LangChain models itself. And what you'll observe, the LangChain module here, what the LangChain module helps you do is it kind of simplifies this whole access to the underlying models and the underlying data as much as possible. So let me just quickly show you that. So firstly, let me show you the LangChain wrapper. And then after that, I will show you how you can sort of do all of that adding that additional data sets and stuff like that on top of it. Okay. Look, the system persona that I'm providing here, every time I ask a question, I'm expected to sort of stick that system prompt along with it, which makes no sense. Like every time I need to just add it, can I not automatically create a small wrapper function that helps you, like every time you're asking a question, it just simply adds this as an additional prompt along with this prompt and then sends it to the model. It'll make it so much more easier, right? So like basically like a template, create like a prompt template of sorts that will help you access these models much better. So the second thing also is here I'm using directly the OpenAI model. But imagine if I have to access Meta, the Llama models. How do you access the Llama models then? They will probably have a different interface, isn't it? So for example, if you were to look at the Llama 3 model, and if you were to access the Llama 3 model over here, not the Llama 3 is open source. The MARM. So here's where the Llama model is available. So if you were to access the Llama 3 model, this is by the way the Llama 3 model, you need to use the Transformers library. So you will have to interact with the Llama 3 model completely differently, like how you would have interacted with a different with a with the pipe with any of the Hugging Face models. You will have to interact with that model that way, which is again sort of irritating, right? Because like the whole code that you have written, you cannot simply switch from OpenAI to that one. So again, that's a bit of an irritating challenge that you will have to deal with. Same with, let's say, if you were to use any of the other models that are available out there, you will have to again switch. So that's where this whole library called LangChain sort of comes in, right? So if you look at LangChain, this is the, if you go to LangChain, so this is LangChain, the largest community of LLM apps. So that is fairly the truth. They're actually one of the first few people who sort of got started with it. So LangChain helps you access the models very easily. It helps you create a bunch of different things by itself, right? It has something called as a prompt, for all of the prompt, it has a prompt template. It has a bunch of different tools, blah, blah, blah. It has like a bunch of different things that you can access. So let's quickly take a look at how this works, right? So let's quickly take a look at how LangChain works. So instead of directly accessing OpenAI, LangChain has their own thing called as LangChain OpenAI. And then you simply say LLM is equal to OpenAI. By the way, I have put the environment variable in this .env file over here. So when I simply say load.env, it simply loads it into my environment. I can simply access the model directly from here. And the model that it has, I think it is GPT 3.5 Turbo. So I'm importing a prompt template here. So here's a simple example. See, this is a system prompt if you think of it. I want you to act as a financial advisor for people in an easy way, explain the basics of. I've put like a placeholder over here. Limit the response to 15 words, right? And now I'm simply saying, this prompt template, I can now use it wherever I want, whenever I want. There is only one input word, which is this financial concept is like the input variable, one variable that it needs to basically ask. Once this prompt template is created, I can simply add prompt.format, and I'm adding income tax as like a prompt, as like a query over here. So it's basically going to insert income tax into it, and I'm just simply going to query against it. So it's going to return. So the prompt here is, I want you to act as a financial advisor for people in an easy way, explain the basics of income tax, limit the response to 15 words. So when I ask it to respond back, income tax is a percentage of your earnings that must be paid to the government. So what has happened here is this prompt has also been nicely printed here. So I want you to act as a financial advisor in an easy way, explain the basics of financial concept. This financial concept is simply nothing but the prompt itself for me, that has been formatted, as you can see here. So that's it. So that's how this sort of works. It's like trying to create like a wrapper on top of it, which will help us access this template much faster. Now, instead of income tax, I can simply switch to, I don't know, ELSS, equity linked saving schemes. Instead of ELSS, I can simply switch to GST. Okay. Now, here's another example, another prompt template, right? So in this case, you're asking it to do, I want you to act as a data analyst who's good at SQL. Same thing, right? So you have 5 tables with 20 columns each. Assume an entity relationship diagram for a sales database. Answer the following question with a SQL query. And you'll ask a question, whatever your question is. What are the customers with the highest sales? And it will just simply return, it will just simply respond back to this particular question with the SQL query. Select customer name, blah, blah, blah. And it has returned the query for you completely. Make sense? Okay. So now, this is, again, so now this, wherever you go, you can use this particular template one And then you can simply refer to template 1 as like the template for asking any kind of an SQL query. Similarly, you can create another template that is to do with, let's say, a financial bot. That way you can create as many templates as you want. The point is you don't have to reuse the code. That will automatically rewrite all of this. You can simply say template 1, and then you can simply pass it here. Whatever template you created this prompt, you can simply just pass that particular prompt over here and that will be taken care of. So you're eliminating the need for writing code multiple times. Make sense? In enterprise context, I will have to feed the table definition as well. Yes, you are absolutely right. So here you can pass the table definition. Table definition can also become another variable then in this case. Right? So you can have two variables, table definition, and here you can have or rather an ER diagram, and then you can have two variables here, and you can probably pass that as like a JSON string or something, and this table definition will have to be passed in here, right? So question is this, comma, whatever is your table definition equal to whatever. You'll have to pass it as whatever, and then you can sort of ask the same question. Of course, you'll have to ask the question, and you'll have to also pass the table definition here in this case. So there's a small error somewhere, but I guess you get the point. Made a mistake. This is not required, just to let you know. This is good enough. Cool. So what you can also do, right? Instead of writing the code like this, you can also use the other kind of models, which is the chat model. So see, you need to understand that there are two types of models that are available. Let's actually go back here. So here, if you look at the models, so there are, you need to understand that there are two types of models that are available. One is a chat-like model, and the other is a regular completions model, right? What do you mean by that? So the chat models are essentially the models that are powering your chat GPT, chat-like experience, right? Like for example, a GPT-4o. This is a chat model. The 3.5 Turbo is not necessarily a chat model. This is not built for chatting. This is just for simple completions, sort of an exercise, right? Like for example, if you simply ask for it to do a specific task, it will do it. But if you want to exactly do like a chat experience, 4o is built for a chat experience, right? 4o has been trained for a specific kind of a chat experience. So in that case, what you could do is you could kind of, if you want to use like a 4o kind of a model, then you can kind of do it a little differently. So here you can of course pass the user and all of that kind of a behavior. So let me show what I mean by that. Let me go back here. Okay, using a chat model like 4o. Okay, so in this case, right? So let's go for example, this one. So this is the regular OpenAI models. These are the chat OpenAI models. So I'm going to load the LLM here. So LLM is equal to chat OpenAI of model is equal to GPT-4o. Sorry, 4o. That's good enough because the environment variable already has the key, so I don't need to pass it explicitly again. And then I can give all the messages. So the messages here are first one, which is that of a system. And then you can simply say whatever the system message. You are a very helpful very cordial translator. Please greet the before you respond back. You are proficient in English as well as Hindi. Also, while responding back, share a small. After you respond, share a small piece of trivia related to the question. So perfect. Okay. So I've given it like a system prompt. And then here, what I can also do is I can provide the human or the user prompt. It's called as a human prompt or like a user prompt. Whoever is the user, this is the human prompt. And here, so now I'm actually passing it like a this sentence from English. Translate this sentence. It is raining very heavily in Mumbai. Let's say I have this question. I have this messages. These are two messages that I have, and then I'm going to have this LLM sort of respond back. Response is equal to LLM dot invoke. Oh, sorry. Oh. Okay, brilliant. The responses are here. Hello. The translation of your sentence is raining very heavily in Mumbai. In Hindi is मुंबई में बहुत तेज बारिश हो रही है. Trivia: did you know that Mumbai's monsoon season typically lasts from June to September, and the city often receives more than 2,000 millimeters or 79 inches of rainfall during this period. So that's it. So that's how this goes. You could sort of do this, of course, using a prompt template as well. Now here you can, whatever I just showed you, you can kind of use this through a prompt template as well. So let me actually show you how you could do it using a prompt template. Using prompt templates. So how would you do the same thing using prompt templates? Same thing. So you simply say prompt is equal to, let me actually go back here. There's only one thing I need to change. This is a prompt template. Similarly, you would have a chat prompt template. From LangChain underscore import. Perfect. So now we can simply go here and now load a chat prompt template. So prompt right, and now you can simply say chat prompt template dot from messages. So again, this is sort of some piece of code that is required from a prompt template sort of a lens, from a LangChain sort of an approach. So very simple. All that I have to do is, of course, I need to just pass these two messages. Let's go. Perfect. The only thing is this one, the human one, has to be a variable. Right? That has to be a variable. And then all that I'm going to do is chain is equal to. So this is LangChain's new way of accessing it. So the prompt and the LLM, this becomes a chain. A chain is simply nothing but basically the same thing here. I can also write it this way, just to let you know. Where does that go? Prompt. We can write it like this. And then we can say chain dot invoke of input colon. What is the question? And is that it? Or do I need to do anything else? This is response. Perfect, let's go. So what happened? The object has no attribute content. Change the library again, I guess. Cool, that's it. So here you go. Hello, I'd be happy to help. Now the beauty is this prompt is a template now. Wherever I go, I can just use this. I just have to run this line of code, and this is all nicely embedded inside this template. So I don't need to do anything at all. I just have to use this chain now wherever I go, and I can just use it wherever I want. Okay. Now, one thing that I want you to understand is while you're using all of this, right? So let's go here, and here's where you need to understand some of the aspects around pricing. Go to the dashboard. Let's go to usage. Everything that we just did so far, right? This was the GPU GPT-4o model, right? So everything that we've done so far has costed me a total of $0.04 as of now. That's the cost that I have incurred so far. Okay. It has nothing to do with subscription. It has to do with credits. So somewhere here you can actually see the credits. You go to billing. See, my credit balance is 49.94. Doesn't mean and so if you don't have that, if your credit balance is 0, then you will not be able to run anything. So just bear that in mind. Okay. So congratulations. This is how you access any of your large language models, at least the OpenAI models. Now the question is, okay, this is all great, man, but what if I have more data? So here, this is just one question, man. This is okay. But if I, let's say, I need to pass, let's say, a document of 10,000 words. Like, for example, I say, translate this sentence, and I also, let's say, have one more input here. You're a very cordial translator. Let me take the same example, and let's say you are a very smart, very sharp, let's say, great, you are a good data analyst. Let's go this. And you have an expertise in analyzing structured data. So this is, let's say this is the input question. Okay. And in the input, let's say this time, instead of just asking a question like this, I say analyze the data, analyze the, provide an So let's say I give it a small piece. So the point is, this is where things can start getting a little tricky. Now I'm asking it to, I'm probably going to pass like a, data set to it, and I'm going to ask it to start analyzing some of this information. So I have like a banking data set here, a small data set, and I'm going to probably pass this information to it. So I'm just going to pass this information to it, and let's go here. And so this is like a data set, and I'm going to say, given this data set, input is equal to, so this goes through, and it considers this data set as a part of it. There you go. So if you see here, what it has actually done for you is it has actually gone ahead and it has given you the complete way in which it expects you to execute this particular piece of code, or rather to perform this particular analysis. Now what you can do is you can actually ask it to perform that analysis itself, right? So it has given you the summary of the personal loan column, but now what you can do is you can actually ask it to go ahead and execute all of that and generate the output for it. To perform this analysis, you would typically use statistical software or a programming language like Python with libraries like pandas, blah, blah, blah. If you provide the data set with more specific details, I could offer a more detailed analysis. So now here, you can ask for it to go ahead and perform the same sort of analysis over a period of time. I don't think it has actually taken this column, but let me just be doubly sure about it. Let me just be sure that it is actually taking this in. So what you can actually do from here on, sorry, break down the personal loan. Yeah, see if you see here, it is by age, gender, and income levels. It is actually asking you to do all of that analysis. So it is able to actually read some of the other columns that you see here, and it is able to suggest some of the recommendations here. You will need to, of course, ask it for more something that is more specific here, right? You will have to say, consider the first column, first row as the actual, data sets and stuff like that. You will have to basically ask it to create something that is more relevant. Just give me a second. I just want to make sure that this is taking that data as an input here. Just a second, and then we can close. Sorry. Cool. Yeah. So here you go. This is that one small piece of change. My point is that if at all you were to get this, this bot, or rather this particular LLM, to try and understand what this data is, you will have to pass all of that data as a part of the prompt, right? All of that information will have to be passed in here as an input. Only then it can sort of understand that information, right? So that is the only way that it will be able to understand how to do this. The data set is CSV with the first row as the act. All right, so this is what you need to do. You need to pass this particular data as a part of the prompt. The data starts. So now you're essentially asking it to go ahead and analyze all of this and return the response. So there you go. It has analyzed the total records of 45, counts number of individuals who have taken a personal loan, 8, number of individuals who have not taken a personal loan, 37, percentage of distribution, 17.78% of people have taken a personal loan, who have not taken a personal loan, findings, additional observations. The basic analysis can be used as a foundation for more in-depth analysis. You see that. Point is, if you needed to perform more of these detailed analysis, the only way that you can get it to do all of that is if you actually pass all of that information to it in the actual prompt. But as you can imagine, passing all of that information in an actual prompt can be super, super tedious. Especially if the data is here, this is just 45 rows. Imagine if it is like 100,000 rows. Then what do you do? So the beauty is that these models, that we're talking about right now, they all have this wonderful ability. If you go to the models here, right? Go to talks. If you go to the models, so the GPT-4o model has the ability to handle at least 1,228,000 tokens, which means that you can pass up to 128,000 pieces of words or pieces of tokens in this prompt. That's the maximum that you can pass. Anything beyond that, it will not consider. So if that amount of data is available, then it can comfortably, generate a certain output for you. That is not an issue. But anything beyond that, that is where things can start getting a little tricky. That is where things will start becoming a lot more complex and a lot more tricky. So in such a scenario, what are you expected to do? That is where we will introduce ourselves to something called as Retrieval-Augmented Generation. Okay.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
So when you look at any of these LLMs, right? So there are two inputs that you would typically pass. One is the prompt, or rather, before I ask the prompt, I'm just going to call this the question. And then you pass the context. And then you ask it to, and of course, it generates a response. What do I mean by a question? What do I mean by context? And what is the response? For example, when you ask it for, hey, who is the president of, when you ask a question like, who is the president of the United States, right? So who is the president of the United States, right? So you ask a question like this. And then the context here, context is simply nothing but where do you want it to respond this particular question from, right? There are two ways you could do it. You can either provide an explicit context. What do I mean by an explicit context? Meaning you can provide it a list of Wikipedia articles and you say, you know what, try and find the answer from these list of Wikipedia articles, right? You can either say, you know, try and find the answer from this Wikipedia articles, or you can simply choose not to provide this information. You can say, you know what, I don't care. I'm not going to provide any of this information. Like, I'm simply just going to ask this question and I'm going to expect it to answer this particular question. So this nuance is very important, because when you ask a question like this, when you say, who is the president of the United States? And you're simply asking this question without the context. If you're asking this question to the LLM without the context, the LLM will try to answer, will come up with a response. But how will it respond back to this particular question? The LLM will respond back basis whatever it knows. Whatever the LLM knows, whatever the LLM has been exposed to. Okay? What do I mean by that? Consider the LLM as a young kid, as a baby, as a child. Right? Consider the LLM as a child. Right? And this kid has been exposed, let's say, to data all the way up until, let's say, 2022 September. I think the OpenAI, the GPT 3.5 model was only exposed until September 2022 or something. So now this model has seen all internet data until September 2022. Almost all of the internet data until September 2022. So when you ask a question, this LLM is not database, but it has seen all of the information until that point in time. So this LLM will try to respond back basis whatever it has learned or whatever it has seen until the September 2022. Now, what does that mean? If the president of the United States had changed after September 2022, it will not be able to answer that question. It will probably make up something, right? If you are asking a question that has information that is not there in September, that is not there up until September 2022, this will still create a response. This will still come up with a response, but it'll just make up some random stuff. It'll come up with some random information because it can. That's a large language model. It's not returning a response basis reality. It is just making up a response. That is referred to as, that making up a response is referred to as, any idea? A word that starts with an H. You must have heard about this. Hallucination. Hallucination. So it's going to hallucinate. Hallucination means it is going to come up with a response that has no factual basis. It'll just come up with a response just because it can. Right? Just because it can. And it is able to come up with, it is able to generate information, but is not grounded in any kind of reality. So the problem is, and this is what I want to, ground here. The key takeaway here is, when you're asking a large language model to respond to questions, basis everything that it has been trained on, then because you and I don't know exactly what is all of the information that it has been trained on, there is a greater chance that your response could be a hallucinated response. This output, there is a larger chance that it could respond back from hallucination or respond through hallucination. It might just come up with a response. It might look very, very realistic, but it might just hallucinate. It is generative completely. There is no deterministic responses at all. Everything is generative. How does it remember if the information is not stored? See, it is not remembering. You are aware of how. So my point is, it is not consciously trying to create a correct response. It just, of its innate nature of learning, it just comes up with the right words one after the other, thereby coming up with the best response or the most realistic response that it has been trained on in the past. I am not saying that it will not hallucinate otherwise. See, I want to make something very, very clear, everyone. If you ask any question before September 2022, will it always come up with a response that is 100% grounded in reality? No, not always. There is no guarantee to that. Nobody is saying that if you ask a question before September 2022, it will always come up with a response that is grounded in it. It could hallucinate then as well. But the likelihood of it hallucinating is much lower in that scenario because it has been exposed to that information. So it's more likely that it will come up with a response that is more realistic and more factual than otherwise. So, as I said, when you ask a question to the large language models, if it has been exposed to some of that data, it can respond back. Even then, there's no guarantee that it will always respond back with the right responses. There's a larger chance that it will come up with a better response. However, if I ask it any question that is not a part of its trained data, then there is absolutely sure, then we are absolutely sure that it will just make up some random response, which may or may not be true. What do you do then? So in that case, you need to sort of control it. The best way to do this is by making it very clear to the LLM that, look, you don't use your historical knowledge, you just use your ability of understanding language, but use this new context that I'm going to provide here, right? Don't try to over engineer this. I'm going to provide you like some documents over here, a list of 10-15 documents. So whenever you're trying to answer this question, only look at the content in these documents and then come up with a response. Now, when you do that, what happens is you are then forcibly grounding it. You're forcibly grounding it to only answer it from this piece of information that it has access to. If it doesn't know, if it doesn't see the response of that particular question in these documents, then it will either say, I don't know, or you can either, like what Vipul is saying, you can either get it to say that it doesn't know, or you can also maybe make it, you can also maybe get it to guess basis a certain kind of understanding that it has on these documents. Solving a passage, it's like reading comprehension now. So you're getting it to do reading comprehension. So you have a kid that is extremely good at English. You're saying you don't use your historical knowledge. Here's a passage. Here's a question. You answer this question from this passage. That's it. Right. So don't use your memory. Just use your ability to understand English. Look at this passage. Look at this question. Try and answer this question from this particular passage. Reading comprehension. That's what you're asking it to do now. But at scale. But at imagine Wikipedia scale. Imagine the common crawl scale, right? So the complete internet sort of scale. At that scale, you're getting it to do stuff like this. That is what we mean by context, right? So providing the relevant context. So when people keep referring to the word context and context in the case of large language models, this is essentially what they're saying. So a question plus the context put together is referred to as both of these put together is referred to as, what's the word? What is it called as? The question and the context put together is referred to as prompt. That's the prompt. A question and the context put together is referred to as prompt. Now, most of our time and effort that we will be putting in is to engineer how this prompt should sort of look like. How should the question look like? How should this context look like? What should be the relevant context for a given question? How do you know how much context? And also, right, remember, these large language models cannot have massive prompts. There are certain restrictions on how much this prompt could be. So you need to come up with some techniques to dynamically create these prompts, dynamically find the relevant context to answer a particular question. Because this context size cannot be massive. It cannot simply be like a few gigabytes of data. There are certain limitations on how big that context size could be because the LLMs have only been trained to deal with a certain context size. So in that case, how do you handle such large context sizes? Right? That is where we will be introduced to something called as, that is where you will have to find a way to automatically curate the relevant context for a given question. So if somebody is asking about President of the United States, I need to create this context in such a way that there is approximately the response to this question in somewhere in those documents, right? So some kind of relevant document should be present over there, right? It doesn't make sense for me to put the President of the United States. I cannot assume that this will be able to answer who the President of the United States is from a document that has to do with carpentry or pottery for that matter. It makes no sense for me to pass documents like those. I can probably pass documents like maybe about United States. I can probably pass documents about maybe Donald Trump, Joe Biden. Maybe I can pass some relevant documents like that and thereby try and answer that question. So how do I dynamically curate the context is where we will introduce ourselves to something called as RAG, Retrieval-Augmented Generation. The question that you ask for, the response to the question that you ask for is probably going to only be present in a few documents of all the corpus that you have. You might have, let's say, a few terabytes of data, so few gigabytes of data. You cannot pass all of that data as context because the LLMs have certain limitations on how much context they can carry. You cannot simply say, I will pass all the data to it. For example, in the example that we did, where did that go? Yeah. For example, to be able to answer a question like this, analyze the personal loan column, we pass this whole thing as context. But man, I cannot pass the whole thing as context at all times. To be able to answer a question like who is the President of the United States, I cannot pass the complete Wikipedia corpus as context. So in that case, I need to be able to retrieve the right documents from the complete Wikipedia corpus that I can handpick and pass so that so that my LLM will be able to effectively summarize information in it and generate a response. So that process of finding the relevant context for any given question in such a way that it finds the best response, or it generates the best response, is what is referred to as retrieval-augmented generation. It's not just retrieving the right document, you're retrieving the document, and through that retrieval, you're able to generate the right kind of response. Exactly. You're trying to find the not very specific, but approximate sort of context is what you're trying. Okay. Is to find out that is correct. So let's go. Let's look at some of these examples. Okay. We'll start there and then we can build on top of it. So I'm going to do 2 examples, but we'll try to get there. Prompt is not a query. Prompt is not only a query, it's a query plus the context put together is a prompt. Okay. So what are we going to do here? Let's go back here. So I'm going to be using the GPT 3.5 turbo model. So I'm using the GPT 3.5 turbo model, and I have the same ENV. You all should also be able to access it. I'm then just opening up the client, the OpenAI. I'm using the OpenAI library to start with. So let's ask a simple question. Okay. So let's start with a super simple question. Control plus. Let's start with a very, very simple question. Which athlete won the gold medal in the high jump at 2020 Summer Olympics? See, I'm asking it a question. I haven't trained anything. I am just using the GPT 3.5 Turbo as is. Okay. I ask it a question. How do you ask that question? You remember this, the chat completions, chat completions.create. You provide the model, you provide the messages, and you simply execute that line of code. That's all that I'm doing here. System, here you answer questions about Olympics and the saying, and then role, and I'm passing this particular query, whatever the query is over here. And I'm using the 3.5 turbo model. This GPT 3.5 turbo model is what I'm using here. So now you ask it to generate the response. And yeah, there you go. Sorry, let's go here. This is the query. And perfect. Generate the response. Mutaza Sabarsim of Qatar and Gianmarco Tamberi of Italy both won the gold medal. I don't know if you have actually watched this high jump finals in 2020 Summer Olympics, the Tokyo Olympics. It was actually very fun. This was amazing. Where actually 2 athletes had won the gold medal. They just kept going on and on and on. And then finally, this guy, Mutaza Sabarsim of Qatar, he decided, let's just share it. And the other guy from Italy also agreed to it. Actually, the other way around. I think this guy proposed that they share it, and he agreed to it, and then just simply shared the gold medal. It was an amazing sportsmanship spirit that was kind of shown at that time. But anyway, the point is, do you see the answer? Mutaz Sabarsim of Qatar and Gianmarco Tamberi. So it has actually come back with a response. They decided to share the gold medal after both clearing the same height and agreeing not to participate in the jump off. So perfect. So if you actually go back and take a look at this, at the actual result, response of this. So this is from the Athletics 2020 Summer Olympics men's high jump. If you actually see it, Mutaz Sabarsim emerges as a joint winner of the event following a tie between both of them as they clear the 2.37 meters. Both Tamberi and Barsim agreed to share the gold medal. So it's like a fun thing. So it kind of happened on August 1st and 30th July. But anyway, the point is, so here I asked the question. I did not provide any context. Right? I did not provide any context. I just simply asked it a question. And because the 3.5 turbo model was trained on something, it was actually able to go back and generate the response for it. Right? Which athletes won the gold medal in curling in the 2022 Winter Olympics? How many of y'all are aware of the game curling? Are you aware of curling? Yeah, a game of giant marbles on ice. That's exactly what it is. Actually, if you look at curling, it's this port. It's this. So they've got this hot case kind of thing, and then they just kind of run it, and then it needs to land in this place. But anyway, point is, doesn't matter. That's not the point. The point is, we're looking at curling at 2022 Winter Olympics. So I asked it a question, like which athletes won the gold medal in curling at 2022 Winter Olympics? Same question, same piece of code. I asked it to generate the response. The gold medal in curling in 2022 Winter Olympics was won by Swedish men's team and the South Korean women's team, is what it's saying. Okay, sounds pretty accurate. Okay, let's actually go and check. So Swedish men's team and South Korean women's team is what it's saying. Men's curling, Swedish men's team, which is true. But the women's curling was not the South Korean women's team. It was actually won by Great Britain. It was actually won by Great Britain. But it says the South Korean women's team had won it. So it kind of messed up, of course, clearly, as you can imagine. Right? Sweden did win the men's World Cup. Actually, the reason why Sweden won is because Sweden is actually a champion in that sport. Sweden has been actually winning this for the last few years, for the last few occurrences as well. But it was not even the South Korean team, let alone South Korea. South Korean actually did not even participate in this sport. So it kind of made up this answer. Does that make sense, everyone? Do you understand where we are headed to now? Now, this is the dangerous territory. This is the place where, yeah, a lot of confidence, right? So it kind of came up with the answer with a lot of confidence, seems absolutely accurate. So the reality is, why did it even answer when it has the data? So it doesn't have the data. It doesn't have the information. So that's the nature of large language models. You're asking it to generate text. It is generating text. Why are you holding it responsible for it? You asked it to generate something, it ended up generating something. Why are you holding it against it? So it did what it did. But the problem is that it, of course, hallucinated in this case. Right? So it just made up the answer. Just like how you and I would make up an answer in an examination when you don't know the answer to a question, you just make up because you know how to make up answers. It just made up an answer. So it just made up an answer here in this case. Right? Now, but the thing is, you can now specifically ask it to control and not make up, stuff like that. So one simple thing you can do is you just ask it not to do it. You just ask it nicely. You say, or explicitly, to be more precise. You simply say, answer the question as truthfully as possible. And if you're unsure of the answer, say, sorry, I don't know. Right? So you're asking this as a blanket thing. Actually, if you ask me, you can actually put this in the you can sort of actually put this in this thing. In the system prompts, right? So and that should be, so you can actually just add it here. So you just added you answer the questions about 2022 Winter Olympics, answer the questions as truthfully as possible. And if you're unsure of the answer, say, sorry, I don't know. And now you ask it to answer the same question. Now this time, when you ask it to do this, what does it say? Sorry, I don't know. The same question, but this time with a more controlled and the right kind of prompt. It actually came back and said, I don't know. What does that tell you? What does that tell you? It tells you that you need to ask the question a right way. You need to know what to ask to get the right kind of responses. Yeah, it doesn't default to hallucination. See, you need to understand that large language models, it's in their nature to come up with sentences and words and create sentences that are human readable. That's what they've been trained to do. Large language models were never trained to come up with right answers. You need to understand that very clearly, everyone, right? So large language models are not trained to answer right questions. They are not trained as, to participate in quizzes. They are trained to speak the language the right way. That's what they've been trained to do. Thereby, if you get it to specifically but they've also been trained to reply to instructions, right? They've also been trained to understand the instructions and operate by these instructions. They've been trained to do two things. One is they've been trained to speak language well. Two, they've been trained to obey instructions. These are two things that they've been trained to do. Thereby, when you provide the right kind of instructions, they will operate the way you want them to. If you don't give them the right instructions, they will go all over the place. But how does it know that it doesn't know the answer? Yeah, because see, how would you know? Okay, so here's the thing. When you're speaking something, do you know you don't know the answer? When you're making up an answer, do you know that you don't know the answer? Of course you know. Right? In the case of a model, the way it knows that it doesn't know the answer is when it's generating words, right? There's a probabilistic estimate that you have, right? There is a probability of the next word. So it decides if that probability is appropriate or not, is beyond a certain threshold or not. If it thinks that the probability is not good enough, then it simply returns back saying that this is inaccurate. This response is inaccurate. What's the next step? So imagine we were able to answer this particular question, and as you can imagine, the fundamental reason for that, why the GPT 3.5 Turbo could not answer this question is because of this reason. This only has access to data up until September 2021. These models, or rather, these models have only been exposed to training data sets up until September 2021. So you ask them to answer anything after that, it doesn't have context. So it will never be able to answer that response. So what do you do then? So in that case, if you were to get it to answer those questions, how do you get it to answer this particular question? So that is where, so you know that this model is good with language, but this model does not have the right context to answer. So you're able to answer, it has the right ability to frame responses, but this question doesn't have the right context. So how do you provide the right kind of context, right? So that is what we're going to be doing right now. So we're going to be providing it custom data sets, right? To help the model answer the question, we can provide relevant custom data as a part of the prompt itself. And this extra information will help answer it better. That will act as context and it will start answering this response much better. So that's what we're going to do. So what I'm going to do is this curling article that I spoke about. What is that? So this curling article that I spoke about, I'm basically going to just copy this. Right? I'm just going to simply copy this article and I'm going to put it here. That's it. Right? I just copied it. So I only selected up until the medals section. I think until here. Yeah, up until here, the medal summary. I copied everything up until here and I simply put it back there. That's it. So that information is now available here as a part of the prompt. So this is now the article itself. Plain text, as you can see. And all of this is here. And then let's keep going. This is the article. So now I'm going to say use the below article on 2022 Winter Olympics to answer a subsequent question. Answer a question as truthfully as possible. Answer the question as truthfully as possible. And if you're unsure of the answer, say sorry, I don't know. Right. So now here you're getting it to ask something very, very specific. You're asking something very, very specific, and you're saying, and look, here's the query, here's the question, and then you get it to answer that particular query. So if you look at the query, this is the query, blah, blah, blah. Actually, I don't need this because it's already there in the system prompt. Let me see if it's there in the system prompt. Okay, I didn't add it in the system prompt. I can add it in the system prompt. Let's go here. Okay, cool. So this is a system prompt. Answer as truthfully as possible. And if you don't know, just simply say, I'm sorry. And the query, by the way, is just this whole article now. Right? Now I ask the same question. Right? And the question here is, which teams won the gold medal in curling and at the 2022 Winter Olympics? So when I ask this question right now, it generates the response. The men that won the gold medal at curling in 2020 Olympics were men's curling Sweden, women's curling Great Britain, mixed doubles curling Italy. If you actually fact check that, let's go back here. Men's curling Sweden, women's curling Great Britain, and mixed doubles curling Italy. So what does that tell you? If you provide the right kind of context, and if you tell it explicitly what to do, these models will kick ass. They'll do a good job of this. They'll do a fantastic job. However, question is somewhat related to this problem where the model is being taught the new context. Please read my question. Can you repost your question? Okay. How can we make ChatGPT learn a certain context and what we can trust the accuracy of the questions based on the context? So you are not, okay, here's the thing. Here's the thing that I want you to understand. That look, you are not training the model here. I need you to understand that. You are not teaching the model, you are not training the model. You are just saying, look at this and answer. That's it. So the model is not learning anything. By just because you passed this additional piece of information, the model did not learn about 2022 Winter Olympics curling. The model did not learn anything there. The model's learning is what it was trained on before. You have just tapped into its ability to do reading comprehension, and you simply said, look at this article and answer this question. All it did is just that much. It did not become intelligent. It did not. Now, when you ask that model, no, you're not fine tuning. You're not doing anything, sir. Right now, you're not doing any fine tuning. If you want to do that, if you want to really get it to train, if you really wanted to train it on new pieces of data, that's where you will have to do something called as fine tuning, like what Devashish was saying. Here, I'm not doing anything. Here, it is just simply inferencing, not referencing, inferencing. That's the right word. If he asks the same question without this context, will it still say yes? Absolutely yes. You ask the same question again without this context, it will say I don't know. The response over here is strictly because of the context that you provided it, not because of the not because the model has learned something. If you take out that context and if you re-ask that question again, it will simply say I don't know. Now, what is the word limit for this context? Can I just add as many as I want? Well, no. So the context window for a GPT 3.5 model is 16,000 tokens. Now, the way to infer a token for a GPT 3.5 model is 16,000 tokens. The token is, you all must have learned about tokens. You all must have learned about tokenization when you learned your PyTorch or Hugging Face models. What is tokenization? Now, tokenization is not embedding. Tokenization is just the phase where a particular word is broken down into subparts. Right? So these models, they infer language very differently. So if you take the complete sentence, they basically break that sentence down into individual words. Right? In certain cases, right? Like for example, if you take the word higher, the word higher can be broken down into two parts, like high and the suffix er, right? The word high and the word er. So a good way to kind of assume this is, right? If you take, for example, 10 tokens or 100 tokens is around 75 words. 100 tokens is approximately around 75 words. 3/4. One token is sort of 3/4 of a word. Okay, that's essentially what your token really is. So when you talk about 16,385 tokens, you're approximately talking about around 12,000 words of sorts. That's like a good estimate. You can think of that as 12,000 words. 10,000 to 12,000 words. So that's the max that you can have as far as GPT 3.5 is concerned. However, the GPT-4 family of models, especially the GPT-4 Turbo and even the GPT-4o Turbo 4o models, they all can have much larger number of words, 128,000 tokens. Right? So they can have much larger context size. Right? But even otherwise, right? And as you can see, they had the training data that they have. But the point that I want you to know is that GPT 3.0, 4.0 models can carry a much larger token size. That's one thing you need to understand. So that's the maximum amount of context that you can shove into it. So if you just look at you can actually, when you make a call here, there is a way for us to actually look at the number of tokens. Dot. There is a way to get the token size. Let me just find it. Yeah, that's what they say. So approximately one token is like 4 characters, 3/4 of the word. Just trying to see if there's a way to compute the number of tokens. So now let's go one step further. Now let's ask a slightly more complex question here. Like for example, here I'm going to use the same Wikipedia article, use the below article on the 2022 Winter Olympics to answer the subsequent question. Same thing again. Did any athlete win multiple medals? So if you actually look here, right, in this, so there is actually this guy who's actually won multiple articles, right? This guy Oscar Ericsson, he's actually won like multiple medals here. In this particular thing, right? He's also won like a team medal and that as well. So you can say as he won more than one medal, everything else remains the same. You ask the same question, right? So this guy has actually won like multiple medals at curling. He won a gold medal in the men's event and a bronze medal in the mixed doubles event. So if you look here, the mixed doubles event, this guy has actually won like a bronze medal. You probably find it actually here itself. Yeah. So if you see here, in the mixed double event, this guy's actually won a bronze medal and also like a gold medal here. Again, point is that once you have the right context, it'll do a good job, right? So if you actually, so interestingly, if you actually just Google this question, you will not get the response for this. Somebody had asked me, right? Like, did any athlete win multiple medals? So you actually go ahead and Google this. Interestingly enough, you will not find it. You don't have it. It'll just point you to this and ask you to come back with a response, but actually will never be able to get you the right response here. But on the other hand, if you're able to provide the right kind of context, you can build agents that can specifically answer questions for you. So this is all great. But what you need to understand is here, this particular model has a bit of a privilege. What is it? It's able to answer this particular question well because I provided this complete article to it. But then how do I know which article to provide? If I were to really build like a scalable agent, an assistant, then how do I know which article to provide? From where will I know that? If I just manually try to provide this article every time I ask a question, then what's the whole point of having an assistant? Right? If this were to be truly capable, then what I would ideally expect is for this to be able to automatically find the right kind of article and on any given, at any given point in time. So how do I automatically enrich a prompt with the data that I've passed right now? Basically the context. How do I dynamically provide that additional context? Right? That's exactly what we're saying. We're saying manually adding extra information to the prompt obviously is not scalable. So we will now show how to automatically enrich this. And that is exactly where we are going to spend the next few minutes. Right? How will we do this? So here's where things are going to be a little interesting. So as I said, the prompt for every, so first thing to note is you just cannot add all the custom data as a part of the prompt. We spoke about it. You need to find relevant chunks, relevant portions of the custom data or of your data set as a part of the prompt. Why? Because there is a limit on the tokens on the context window. In the case of GPT 3.5 model, it's 16,000. In the case of GPT 4, it is much bigger. It's almost like 10 times that. Even otherwise, even if it is 10 times that, it's still not large enough. It's large, but it's still not large enough, right? So, as I said, if you take, for example, the average size of a book, right? So the average words in a book, right? So a book on an average has around, an adult fiction books on an average has around 70,000 to 100,000 words, right? A book on an average has around 70,000 to 100,000 words. That's one book that I'm talking about. So this 128K is like one adult fiction book, is one fiction book that we're talking about. That's nothing in the context of the internet. That's literally nothing, right? So my point that I'm trying to come up with is, if you're trying to summarize information, just summarizing or trying to find a response of a particular question from like one book is very limiting. So how can you like tap into much larger portions of data, right? That's where we are going to be talking about this idea of retrieval augmented generation. How does retrieval augmented generation work? Here's the thing. This is like a good representation of it. Let me zoom out. So here's a good view of how the retrieval augmented generation high level works. So how does it work? So first things first, what's going to happen is you take a document or a corpus, right? I'm using the word document here very loosely, but you can think of this as a corpus. The term document, remember, is this can be a corpus of, as I said, it can be Wikipedia, it can be 10,000 PDF documents, it can be one PDF document, it can be anything, doesn't matter. So what you would do is you would take this particular document and you would break that document into chunks. What do you mean by a chunk? This chunk generally is a sort of, you can think of this chunk as typically something that has around 1,000 tokens or something, right? It's like a couple of paragraphs. Think of it like a couple of paragraphs, right? So that's a chunk typically. I mean, that size changes, but typically you take that complete document, you break that document into chunks. So this is one chunk, this is one chunk, this is one chunk, this is another chunk. So you basically chunk it down into different portions. You break it down into different chunks. Then what you do is you convert that piece of chunk into embeddings. Do you remember sentence embeddings? Long ago, so long ago. Once upon a time, we learned about embeddings and sentence embeddings. Yeah. So you convert those into sentence embeddings. Now, how do you convert them into embeddings? What models can you use to convert them into embeddings? How do you convert them into embeddings? Spot on. You can use the encoder model. You can use the encoder models. You can use any of the encoder models. You can use BERT. You can use word2vec. You can use whatever encoder models. GPT also has their own encoder model. Right? The GPT-4 has an encoder model called as the text embedding model. So if you actually go to the the GPT-4 model suite, which is here, if you actually look at embeddings, if you look at these are the embedding models that they have. Embeddings are numeric representations. So you can actually use these embedding models, right? And they can create, so there are three versions of these models. This is the most capable model for English and non-English tasks. Most capable second generation embedding model, replacing 16 first generation models. There was like a model actually before this was kicked out. This is like an improvement on top of this. So for all good reasons, generally what you would observe is most people would be using this model. This model is pretty decent. So we will also probably be using a version of this. If walk you through an example, you'll see that we'll be using this particular model. Point is, that is the model that we're going to be using. But the point is that we will be creating those chunks from these models. So you take a document, you break the document into smaller parts, and each part is essentially created as an embedding. Now, these embeddings are stored in a vector DB, vector database. We can come to the concept of a vector database later on. And the reason why we use something like a vector database is because You need faster retrievals, faster comparisons, and stuff like that. But I'll come to the concept of vector database in the next example. But broadly speaking, this is like a small array or a collection of all of these embeddings. So what this vector database will have is it will have the chunk ID, right? It'll have the embedding and the actual data itself. So chunk ID 1, whatever is the actual data, all of that data will be available here, and the embedding. So the embedding array will be present over here. Similarly, chunk ID 2, data and the embedding. Chunk ID 3, data and the embedding. So it's essentially going to have all of that information nicely stored in here. So this is sort of the first task that you perform. You take all of your custom data and then you create this embedding space. Now what? Now once you do this, every time a new question is asked, now it's very simple. Every time a new question is asked. So we take all the data. How do we make chunks? Chunks is simply breaking it down. Take 2 paragraphs, take the complete data set and break it down by 2 paragraphs. That's it. A chunk is as simple as that. Just take a piece of text and break it down into equal parts. How does ChatGPT still work if we pass it embeddings with different dimensions? Embeddings are never with different dimensions. Embeddings are always with the same number of dimensions. The whole point of an embedding is to make sure that the output is always of the same standard dimensions. How does an embedding look like? How does an embedding look like? A number. Now, once you have that, now every time a new question is asked, here's the thing. So every time a particular question is asked. So let's say somebody says, who is the president of the United States? The question is asked. What do? You take this question and you create an embedding out of this particular question. You use the same model that you've used to create the embeddings here. Whatever model was used, the embedding model, the same encoder you use, and then you create an embedding of the question. This is the query embedding, right? Now you take the query embedding and in the vector database, so the vector database, as I said, has 3 columns, the chunk ID, the data, and the embedding, right? So now in the vector database, look for all those chunks which are similar to your query embedding, which are similar to the query embedding. How do you find similarity between any 2 embeddings? How do you find similarity between any 2 embeddings? Cosine similarity, not attention and all. Simple. Cosine similarity. Attention is already done. Attention is done, hence the embedding has been created. Now that you have 2 vectors, how do you know if these 2 vectors are similar or not? Just look at cosine similarity. So once you compute cosine similarity, you will know the top 10 embeddings, right? Top 10 or top K embeddings. So you might know, okay, this embedding, and this embedding are the closest. So then what do? So now what you do is you take the data from these 3 embeddings. So now you know the top 10 or top K embeddings. From those top K embeddings, you extract the data from there. That data, you append them together. You append that data together. So this is chunk 1. This is chunk 200. This is chunk 350. So you get, let's say, the top 3 chunks. You get the raw data. You append them together. And then what do? You pass that as an input, as context into your model now, rather into your prompt. This becomes your new context. This becomes your new context. So this context plus the original question will be sent to the model, and then you will be able to generate the response. So what is the rationale here? What is the rationale here? The rationale here is when you are trying to find the best set of embeddings over here that are closest to the question, you are assuming that these questions, you're assuming that, or these chunks could possibly have the answer to this question somewhere in them. They could possibly have the answer to
to it is somewhere in them. Then what you do, you pick the top 10 or the top K, extract the raw data from it, combine all of them together. That becomes your new context. That context plus the original question, you pass it as a part of the prompt into the LLM, and that LLM will generate the response for you. Where will it generate the response from? It will only generate the response from the context that you provided. It is not just going to ramp, it is not going to make up anything. So the point is, here we were able to automatically come up with this piece of information. This piece of information that you're seeing over here, we were able to automatically come up with it by finding the nearest chunks or that are related to this particular question, and thereby we were able to generate the response. Why chunk embedding represented as vector than as a subspace? Yeah, embedding is a vector only, no? Embedding is essentially a vector in a high dimensional space. As I said, the chunk sizes is a bit of a parameter that you will have to tune given your problem. In certain cases it's like two paragraphs or one paragraph length. So you can sort of decide how big a chunk you want. As you can imagine, larger the chunks, greater the chances of finding better responses, right? If the chunk size is big, then you'll find better responses. But if the chunk size is big, you might also overshoot the prompt limitations at times. So you just have to be careful about that. We learned in LSTM a limitation that large sequence context vectors are inaccurate. Absolutely, yes. That's because they're LSTMs. LSTMs struggle with large context sizes. LSTMs struggle with large sequences. But these are attention-based models. And that's the whole reason why these do phenomenally well, even if they're large context size. So LSTMs struggle with large context sizes, but attention models do very, very well. Transformers do very, very well with large context size. They don't struggle with it. Actually, the Gemini model, the latest Gemini model, has a context size of 1.5 million tokens. So, and that's what's happening. That's what they've been trained on right now. You can pack an entire book in a single context vector. Yes. That's what I'm saying, right? So if you have a context width of 128K, 128K is as big as a book. Is one book. So you can kind of put the entire book in a context window. This is sending partial data. Can we send full data for fine tuning? So the whole reason that we've gone down this path is because you cannot fit the complete data in a prompt. Remember, the prompt has a limiting constraint of only being able to put like 128K tokens in it. The whole reason why you have a framework like this is to find relevant pieces of your data which can help you answer the question better. Thereby, you're only identifying parts of the data which are relevant and then combining that and passing it into the query. But if your data is very small, then you don't need this framework at all. If your data is just small, simply shove it into this prompt and then just send it, ask it to generate the response. If your data is small. If your data is very large, you have a lot of documents, if you have hundreds and hundreds of documents, then you need something like this. Components onto this, like for example, examples for vector databases are your popular models like, your popular frameworks like Redis, or you also have Postgre Vector DB, you have Azure Vector DB, and so on and so forth. There are like multiple vector databases that are available out there for people to use, and there are also some open source vector databases that are available as well. I'll talk about some of these components when we actually discuss vector databases. For our example right now, what I'm going to do is something fun. So what I'm going to do is I'm going to actually take, for the same example, we are going to create chunks, right? Or for this example, I'm going to like try and quickly show you how the complete architecture looks like. And then I'm going to use I'm not going to be using a vector database for this example. For the next one, which is slightly more sophisticated, I'll use the vector database. For this, I'll just use a pandas data frame. I'll just use a simple pandas DB. data frame for now. Okay. All right. Let's go. So the first thing is, of course, the data set itself. Okay. So the first thing is, I'm of course going to try and like use a. So the good thing is for this particular data set, OpenAI has actually already created some of these embeddings and provided it to us. But I'm still going to show you how you can create these embeddings. This is the same Winter Olympics data set that I was talking about. It's almost like a 200 MB large data set. So we can actually download it and we can access that particular Winter Olympics data set. Let me just show it to you once it downloads. But anyways, let me go back here. So they've hosted this data set already, but I'll still show you how you can create it yourself. I'll show it to you. So this is the data frame. And let me show you how the data frame looks like. So here's the data frame. So you see the text. This is the text, and this is the embedding. So remember, this is the same page, the Winter Olympics page that I was referring to. Same exact page. OpenAI has already kind of provided those embeddings for us. But anyway, I'm just going to like, and this is, as you can see, this is the raw HTML. So you don't really have to do any pre-processing to the raw text. This is, if you see, this is the HTML. You see HTML tags and everything over here. So the beauty of this is that you really don't have to do any kind of pre-processing. You just keep the text as raw as possible. You just take it and then you simply create this embedding out of this. How do you create the embedding? Let me actually show you how you can create the embedding. So there is this simple function. So I'm going to be using the text embedding ADA002 model. As I said, it's the same model that was published in actually 2022. So we are going to be using the same model over here. So what you can do is when you pass a piece of text into it, into the embedding model, it will simply generate a piece of numbers, text as vectors over here. How do you do it? You simply say OpenAI.embedding of create, pass the text, pass the model, and it will simply generate the output for you. As simple as that. So that's exactly what I'm doing. OpenAI.embeddings.create or client.embeddings.create, embedding model, and a piece of text. And it will simply generate the response embedding for me. I don't need to do literally anything else. So if I'm going to say, I'm going to get a vector, I'm simply going to say Gen AI is amazing, right? That's like a vector for me. If you look at the vector itself, here's the vector. How long do you expect this particular vector to be? How long do you expect this particular vector to be? Let's look at the embeddings. Text embedding ADA002. The output size should be 1536. Right? You remember something from the glove embeddings that we used in the sentiment analysis session that we did? How big was that? We loaded the model from GenSim, if you remember. How big were the embeddings for that? How big were the embeddings on that? 300. It was 300 dimensions long. The output dimensions was 300 on that. And this is 1536. So you can imagine how much more complex the model is. But anyways, 1536. And then you can sort of come back here and let's go back to the, yeah. So if you look at this is the vector E. Now I'm going to get the embedding for generative AI is incredible. So I have two sentences here. Gen AI is amazing, and the other is generative AI is incredible. I got the embedding for this as well. So, in your opinion, what do you think? By the way, you can check the length of this. Length of F, comma length of E. Both of them are 1536 long. So, in your opinion, if I look for the similarity between both of these sentences, generative AI is incredible and Gen AI is amazing, what do you think the similarity score should be between both of these? Should be high, close to. So I'm going to use the cosine similarity, look at this, 0.91. Pretty high, right? Generative AI is incredible. Generative AI is amazing. Gen AI is amazing. I was able to get a score that is almost as high as 0.91. So do you agree that the embedding models here work? Like they can kind of come up with like some numeric representations of these sentences? Narendra Modi is addressing the media, and if you remember, there was one more sentence which was the prime minister is speaking to the press or something. Right? So two sentences. The prime minister is speaking to the press. Narendra Modi is addressing the media. Both sort of mean the same, but they have nothing in common. But if you look at the similarity, look at that. See the similarity here? That is the beauty of these models, right? So that is amazing as far as I think the quality of these models is concerned. So now you have the embedding model. So you know, given a particular sentence, how to extract the embeddings. Now tell me something. Can I just simply pass this piece of text and can I extract embeddings? Can I just pass this piece of text? And do you think I can extract embeddings? Yes, perfect. So that is all that I need to do. So compute document embedding. All that I have to do is I just need to get embedding of that piece of text for individual ID in here. I just have to iterate across rows and I just have to get the embedding. So I'm not going to run this right now because the beauty of this, if I want, I can. I'm not running it for the moment because the beauty is it's going to take some time for it to get executed. The beauty is somebody has already done it for us. They have already created these embeddings for us. So I don't need to worry about creating it myself. So these guys have already comfortably created it for us and made it available. So we can just use these embeddings as is. So you know how to create the embeddings. I'm not creating it right now, just in the interest of time. But if you want, you can actually create it yourself as well. It's going to take it some time. So now that we have the embeddings, what's the next? So each time we receive a question, what do we need to do? We calculate the embedding vector for the question with the get embedding function. So we have the get embedding function. So we're going to compute the embeddings for the get embedding for every question. We create the embedding. For each chunk in our custom dataset, we calculate the cosine similarity between the chunks embedding vector, these vectors, and the questions embedding vector. We compute the similarity. We rank the sections from the most cosine similar to the question to the least cosine similar. So you then rank them. That's it. So I'm just going to run this function for the moment. And so, for example, if you take this string curling gold medal, right? I'm passing the data frame and I'm saying get me the top 5 get me the top 5 strings associated with this. And I'm going to simply print this just to see how it looks like. So if I run this, it's going to find the embedding of this particular question and it's going to return. So 87.9 is the similarity score. Curling at the 2025 Winter Olympics medal summary is providing the chunk with the medal summary. Here, curling at the result summary. Again, result summary, women's tournament. This is mixed doubles tournament. Medalists. So if you see, if I say curling gold medal, it found like stuff that is associated with medalists, mixed doubles tournament, women's tournament, and stuff like that. So it's giving me something that's related to the question that I've asked with the top 4 chunks or top 5 chunks is what it has returned. Now what do I do? Now what I'm going to do is I'm going to combine these chunks, right? And I'm going to pass them into the model. I'm going to try and shove them into the context window of the model and then I'm going to pass it, right? So that's it. So I'm going to say use the below articles to answer the subsequent question, answer the question as truthfully as possible. And if you're unsure of the answer, say, sorry, I don't know. I'm still going to stick with this. And since I don't want it to exceed the context window, we're using this package called tick token. And it is simply going to help me count the number of tokens. It is going to help me count the number of tokens. Number of tokens, string, model, GPT model, and it'll help me count the number of tokens, tick token dot encoding for model, and it'll help me compute the size. Like for example, I can simply say this model curling gold medal, and model is the GPT model. Sorry, num tokens. So it will tell me how many tokens it will take to, how many of these tokens will get basically created over here. It says, so curling gold medal has essentially 5 tokens. See, because I cannot exceed the 16,000 token limit, right? Because if it again exceeds the 16,000 token limit, it's not going to be using it. So that's it. So that's all that I'm going to do. I'm going to say, so relatedness, I'm going to find the strings here that are related to the question that I'm going to ask. So I'm basically reusing that function here. That's it. And I'm simply going to, for string and strings, for whatever strings I'm going to get, I'm just going to like append all of that Wikipedia article section, and I'm going to like chunk all of it, and I'm going to like simply merge all of them, basically adding everything together. That's what this is simply going to do. I'm just appending them. You see here, if the number of tokens is greater than the token budget, the token budget is 16,000, or here it is 3,700, but honestly it's like 16,000 or something. If it is greater than the token budget, then it will break, else it will append the next article, right? So that's it. And then the message and the question are going to be merged together, and it will simply return that. You can of course go through the code, guys. You can go into the detail of the code, but I want you to understand what's exactly happening here. So this, we are tokenizing our document as context and passing it. We are not tokenizing the document. We are essentially just okay. So here's the line of codes. So here, what's going to happen is this piece of code is going to return all of the strings that we saw here. The raw text, how many ever we ask for, top 5 or how many ever we ask for, it will simply return that over here. Okay. Once that is done, in this for loop, all that I'm going to do in this for loop is I'm going to go string by string. This is a piece of string, by the way. I'm going to go string by string, and all that I'm going to do is if the number of tokens in the message so far, message is an empty message, by the way, right? If the message plus the next article plus the question, whatever question that I have, if it is greater than 3,500 or 3,700, I think that's the limit that they put up, but 16,000 to be honest. If it is greater than 16,000, then if it is greater than 16,000, then I simply break. I don't append the next one. If it is less than 16,000, then I actually go ahead and append this one as well to it, thereby creating a larger prompt. This is all prompt creation. Nothing else is happening here. The simple for loop. There's no tokenization or anything that's happening yet. I'm just counting the number of tokens so that I stay within the total limit of the number of tokens that are required. So in a sense, what's happening here is just this prompt creation is happening. Let's go back here. Let's go. Yes, this prompt creation is all that's happening here. That's it. This prompt creation is happening, nothing else. Exactly. That's it. That's all that's happening there. And nothing beyond that. Clear? That's it. So now, once this is executed, so then I'm going to pass. Which athletes won the gold medal at curling in 2022 Winter Olympics? And I'm going to make this, yeah, fine. That's okay. Doesn't matter. I'm going to execute. Which athletes won the gold medal? What happened? Header is not defined. Header. This is the header. Okay. Cute. So now it's actually going to, perfect. There you go. So this is the article, or this is the prompt now. use the below articles. If you don't know, simply say, sorry, I don't know. Wikipedia article selection. This is everything to do with curling. First one. So it's actually, so if you look at this, this is the next article section. Where did it go? So it basically separated by this part called Wikipedia article section. So this is the first one. Okay. Second chunk. Third chunk. Fourth chunk. Fifth chunk. Sixth. Seventh. Eighth. I think 8 chunks here. I don't know what was the limit that was passed as the total number of chunks. But yeah, I think it found 8 chunks. And then it found the response to the question. Which athletes won the gold medal at curling? That was the question. And of course, we have the prompt now, which is fully prepared. So now I have the prompt. What do I do once I have the prompt? What's the next thing that I need to do? Ask the question once I have the prompt. Right? So now fire. So you see, there's something called as ask. So pass it to the LLM. So answer the query using GPT-4, whatever. This is the role, this is the message. The message is simply nothing but the message that I have here. And simply fire it. So once you fire, so print ask. And that's going to fire the question. But see, this is going to basically do everything. This is going to do the retrieval. This is going to combine everything. This is going to pass it to the LLM and generate the response. And the answer to that is the athletes who won the gold medal in curling in 2022 Winter Olympics were Stefania Constantini, Amos Mossener, and in Italy in mixed doubles tournament, the team consisting of Bruce Mouth and whatever. So these folks in men's tournament and mixed doubles, and I think somewhere women was also there. Yeah, whatever. So as you see, which athletes won the gold medal, that is all present here. Mixed doubles, it has given you mixed doubles. And this is men's tournament. I don't know why it didn't give the women's tournament. We can also ask for the women's tournament as well. But you get the idea, right? So you get how kind of clubbed everything together. Let's ask a question for an Olympics event that never happened. So 2016 Winter Olympics. Honestly, 2016 there was no Winter Olympics, technically speaking. So it says 2016 had no Winter Olympics. So it says sorry, I don't know, right? And then if you want it to lie, all that you have to do is just change the header, right? If you just change this part, instead of saying answer the questions as truthfully as possible, instead of that, if you just remove that, look what happens. I just remove it and then I ask it for this question. Now it bloody makes up any random thing on the planet. See, the athletes who won the gold medal in curling in 2022 are these. So I asked it for 2016, but it's making up an answer for 2022, first of all, and it gave some names over here from men's tournament and women's tournament. But I asked it for 2016, so it's kind of making up some stuff here right now. So you get the point, right? It's answering an irrelevant question, and it's kind of, yeah, exactly. That's the annoying part. That's the part where you need to be very, very clear. So again, the important thing that you need to understand is you need to be very, very clear, very explicit about what you want it to do. They are super sensitive to these guardrails. So if you don't provide the right kind of guardrail, LLMs can go all over the place. So you have to be very clear about what you want them to do. Else they can go all over the place. First question, say I ask for 128K context tokens. Second question is ask for 128K. Does ChatGPT now remember that the entire 256? No, it's stateless. Each question is only for, so the context size is only for that question, for that call. So when I'm making a call here, there is one call that's being one call that's happening here, and thereby it's only for that particular part. So it doesn't care about the next one or the previous one for that matter. As truthfully as possible is not. It's normal language, normal human understandable language. You can say, instead of saying as truthfully as possible, you can simply say be as truthful as you can, or try not lying, or try not making up answers. You can come up with other things. So in this case, it did not find any 2016 Olympics in the top context chunks. Yeah, which is why it did not answer for 2016. 2016 in the previous case, there was nothing. So it did not create anything. But here, it did not find anything, but it still made up an answer basis what it saw in 2022. That's the annoying part. Okay. Bunny's point is, and I think she's only posted to hosts and panelists, so I don't think everybody else can see it. So she's saying, I'm guessing that there are some better techniques of chunk retrieval, or is it going to be this simple always? Is vector similarity check part of the vector DB? I'll answer the first question. Yes, chunking is a bit of art than science. There are some interesting ways to handle it. So for example, if you go back here, this is just one article, but generally what you do with chunking, there are two parameters with chunking. So when you talk about chunking, there are two parameters generally. There is something called as chunk size and chunk overlap. What do you mean by chunk size and chunk overlap? So imagine you have a document. You create one chunk and then you create another chunk. So the question is, should these two chunks completely be mutually exclusive? What has been found is having them mutually exclusive is counterproductive. Why? It's important that these chunks kind of have some shared context. Else what happens is the piece of information that is available here and the piece of information that is available here, they might be loss of continuity. Like there might be some sentence over here that is probably talking about some kind of a behavior. And here, if you just abruptly start from another place, there is loss of continuity between the two. So it's always good to have some kind of an overlap. So you can define how many tokens overlap do you want between the two chunks. And chunk size, as I said, is generally around one paragraph or two paragraphs. But that's also a bit of an art because it depends on the type of document you are operating with. So yeah, chunk size and chunk overlaps are generally a little tricky, to find. They significantly determine the quality of the responses. The second one to your question, which is vector similarity. So yes, the vector similarity part is generally the responsibility of the vector databases. We manually computed the vector similarities, right? But as you can imagine, this can be very expensive. Meaning, when I say expensive, meaning in terms of time. See, imagine you have 20,000 or 100,000 entities. Every question is asked. You cannot compute the similarity for 10, 20,000, vectors. It's very, very, computationally intensive. So there are some nearest neighbor algorithms. There are some techniques that can help you compute similarity of one particular vector with the other vectors in a fastest fashion. There are algorithms that help you do that. That is where vector DBs are very good at. Vector DBs have some specific inbuilt algorithms that will help you perform this similarity check very, very fast. That is why instead of doing the vector similarity within your system, it is often preferred to kind of go to these vector databases. Like what we just did here is we simply ran like a for loop, right? To find the similarity, what did we do here? We basically executed a for loop here. Where did that go? Yeah, this one. For strings ranked by relatedness. So if you look at this function, all that we did was basically ran a for loop across each row and we computed the similarity, which is very, very, I mean, this is not very sophisticated. So you would ideally want to do something that's a little more robust. and that is less computationally intensive. That's where vector databases come in. What vector databases do is all that you have to do is just pass them a query and pass them a similarity threshold. You say this is the query embedding, and this is the I want to find all the vectors that are 0.85 or below. So this everything that's happening inside this function basically happens in there. Basically everything that happens, yes, everything that happens in that function basically happens in the this function. Sorry, everything that happens in this function basically happens as a part of the vector DB. Basically happens as a part of the vector databases itself. So I will show you a vector database. We will try a Chroma DB or something, an inbuilt Chroma DB or something. Exactly. So spot on, right? We jinxed it. So yes, I'll be showing you a Chroma DB in the next example that I walk you through with LangChain, and that will help.
We went down the route of retrieval-augmented generation, right? So retrieval-augmented generation, as you can imagine, has two aspects with it. One is the retrieval part, and the other is generation. The retrieval part is more about trying to extract the relevant context from the massive corpus that you have given any given and given a particular question. Now, retrieving this context, of course, has to be dynamic, and for that to be dynamic, you require some kind of a very smart logic that only retrieves the relevant piece of information. And then once that is done, then what you're trying to do is you're essentially taking all of those relevant pieces of information and the question that you have and put that together to be able to generate a response and thereby summarize that particular response as well. So retrieval augmented generation is essentially that. Is in what kind of a scenario, right? Do you think, right? I'll repeat the question. What kind of a scenario do you think retrieval augmented generation will not be required? What I mean by that is, to be able to do question answering, do you always believe that retrieval augmented generation is needed? Or is there a scenario where RAG is probably not going to be useful or not required, so to say? That's a question for all of you. Basically, small corpus, okay? For general purpose question answering, RAG is not required. Fair point, okay? What else? My question is, in what scenarios do you think retrieval augmented generation is not needed? Where I don't know the context, okay? When the context is not available, sure. Something we know the model is already trained on. Answering recent questions. If we have an understanding of the topic where details are not required. Model is not trained. Yeah, I think you all are there to some extent. The small data set part is absolutely true. Because if the data set is small, then you don't need basically you don't need RAG. You can just stuff that complete data set into or information into your prompt itself, right? So that's straightforward. Yeah, great point. For a creative task, you don't need RAG. Absolutely agreed. Where the learning is minimalistic, Sallapi says where the learning is minimalistic. Sure, okay. For tasks with low risk, yeah, I think we're there and thereabouts, everyone. Some of your answers are right. Some of your answers are, I think, there. I think there's still that last mile understanding that is still missing. I'll spend a couple of minutes on that because I want to really cement this understanding in your head before we move on, right? So the reason why you would want to do RAG, right, is if and only if, right? So you would do RAG if and only if your data set is large. Right? See, the best way to do question answering, so the best way to do question answering is through putting the content, the regular question answering, the question into the prompt itself. Or so as I said, a prompt is simply nothing but a combination of a question or a query plus context. Now, when I refer to context here basically means data or simply corpus, right? Regular documents. That's what we mean by context here. A question plus context is what we refer to as a prompt. Now, if the prompt is not necessarily large, if this particular prompt is not necessarily large, meaning now the definition of large also changes from model to model. So if you are using the GPT 3.5 class of models, then you are talking about if this combination does not go more than 16,000 tokens, right? 16,000 tokens is approximately how many words? 16,000 tokens is how many words? Very good. 12,000 words approximately. Approximately 12,000 words, right? So approximately around 12,000 words. If both of these put together is less than or equal to less than 12,000 words, then you don't need RAG. Then you just send it directly to the LLM. Then you don't need a RAG. However, in certain cases, what may happen is this question may have to be answered from a piece of corpus that is very, very, very large, right? Like, for example, I may be building a bot, right? I might be building a bot which tries to do question answering on top of, let's say, the whole of Wikipedia. Now, I cannot put the complete Wikipedia over here as context. Ideally, if I can, I would have loved to do it, right? If I am able to put the complete Wikipedia here, I would love to do it. But what restricts me from putting the complete Wikipedia in this particular prompt? What is the limiting constraint here? What is the limiting constraint from putting the complete Wikipedia in this? The number of tokens. Fantastic. It's the size of the model. So you can then decide, you know what? Let me do one thing. Let me start using the GPT-4 category of models, right? Or I might choose to say I might use Gemini in this case, because Gemini might allow for like almost 2 million tokens. GPT-4 would allow 128,000 tokens. Even this, my friends, is not very large. Even this is not very large, right? This is probably as big as one book, right? 128K is as big as one book. 2 million tokens probably is yeah, as you can imagine, it can just be probably 5 books or something. My point being, even in that case, to do question answering, this is not going to be enough. Hence, if, by the way, in a scenario where you're able to stuff the complete corpus into the prompt itself, then you don't need RAG again. Then you can simply just switch the model from a 3.5 sort of a model to a GPT-4 or a Gemini sort of a model, and then parse it to the LLM and do question answering. However, if you don't think that is possible, that is where the alternative is RAG. If you are unable to stuff it into the corpus, stuff it into the prompt, then you go for RAG. So simply, if I were to put a condition, if the if the number of tokens of your prompt, if it is less than the number of allowed tokens by a model, by an LLM, then you don't need RAG. You just combine the two of them, directly send it to the LLM. Otherwise, you're going to go for a RAG, because then you have a context length which is much, much larger. Then in that case, you go for RAG. Now let's talk about slightly more modern day retrieval augmented generation architectures. Okay. So I'm going to talk about a little more advanced RAG. I wouldn't say advanced RAG, but basically different architectures use of RAG. Now, what are the architectures of RAG? How do you set up RAG? Now, there are so many different ways to set up RAG. Let me just go back here. There are so many different ways to set up RAG. One of the most simplest ways was discussed here, right? So, okay. Now, one of the most, as I said, this is one of the most simplest RAG frameworks. However, now here's where the complexity starts coming in, everyone. Right? So how do you now build on top of this kind of an architecture? What kind of components would you require? Because when you're building an enterprise grade component, right? When you're building an enterprise grade retrieval augmented generation framework, that is where you will you will require more and more components, cloud components, right? So that will help you build something like this. What do I mean by this? Let me show you something. Give me a second. I'm just trying to pull up an architecture diagram. I don't want it to be too complex either to start with. Let's go back here. So imagine for a moment that you are actually building an enterprise grade retrieval augmented generation bot, right? Imagine for a moment that you are actually building an enterprise grade retrieval augmented generation bot. Now, what do I mean by that? So this is a bot that you're trying to build, a sort of a chat bot, right? Which can essentially answer questions from structured and unstructured data, maybe unstructured data to start with. Let's forget about structured data. Structured data will require a different architecture. We'll talk about that. So imagine you have, let's say, a lot of marketing, right, content in your organization, or you have a lot of information about suppliers, or you have a lot of information about your competitors, right? And all of that information is, let's say, stored in the form of PDF documents. It's stored in the form of, let's say, PowerPoint presentations, PPTs. It's stored in the form of, let's say, Word documents, right? It can also be, in certain cases, maybe some form of SharePoint sites, and so on and so forth, right? Any form of unstructured content, right? That we are referring to, right? All of that information is sort of available for us right now. Now, the question is, and mind you, right? So this is a lot of websites, a lot of content that we are referring to here. In such a scenario, your ask, or somebody from, let's say, your marketing team has asked you, hey, if I were to access all of this information, all that I have is I have it, let's say, on a SharePoint site or a Teams site, or I probably have it on a Google Drive. And my folks are having to actually just go into one of those files and they're actually having to search across those. It's super inefficient, as you can imagine, right? If I were to simply say, if I were to simply ask a question like, what has, so let's say, imagine you are Airtel, and you would want to understand more about Vodafone, or let's say you're more interested in learning about Geo. So you may ask, what are the key investments made by Geo in 2023? So you ask a question like this, or specifically on improving network coverage. So let's say you were to ask a question like this, or for somebody in your organization to be able to answer a question like this, he or she would have to go through all of these PDF documents, your PPTs. These PDF documents could sort of be earnings reports. These could be investor, IR, or broker reports. They could be transcripts. They could also be some kind of information that's available on the internet. People would have to specifically go through all of this. Now the point is, and for you to be able to extract all of that information and to be able to answer, that's going to be very, very complex. And just to let you know, right, there are teams that do competitor intel. There are teams in your strategy organizations that do competitor intelligence at scale, right? For example, my company makes beer, right? So I work for a company that makes Budweiser, Corona, Stella Artois, Hoegaarden. These are all our brands, right? So we've got a lot of brands. Now, Our direct competitor is Heineken. Our direct competitor is um, our direct competitor is Heineken. Our direct competitor is, we also consider Coca-Cola as our competitor, PepsiCo as our competitor as well. Any CPG is our competitor. Now, one of the things that we actively look for is our folks in our strategy team, who report into the chief strategy officer. They spend a lot of time doing competitor intel. Their job is just about comp intel. And competitor intelligence is about understanding how their financials have improved since last year or since last quarter. So quarter over quarter, how has their EBITDA improved? How has their earnings per share improved? How has their organic profitability? How has it improved? And so on and so on. They look at all the different line items on a P&L statement, and they summarize this information, create massive decks, and they send it out to the C-suite. Right? They send it out to the CEO, they send it out to the CTO, the CFO, and they spend a lot of time then discussing how should they respond back to all of this. This is very, very common. A lot of companies do this. The point is that this is, as you can imagine, a very, very time-taking aspect, very time-taking task, and this happens in every company, right? So, any kind of CPG industry, any kind of industry for that matter, this is a very common affair. In such a case, how can technology help, right? How can you contribute to this? So, one way that people have tried in the past is by trying to create chat interfaces. But the problem is these chat interfaces have been extremely suboptimal. Right? These chat interfaces were not great. Thanks to large language models, now these chat interfaces have significantly become better. Right? You can actually chat with them. You can actually ask questions. So how do you build something like this? How do you build a capability like this within your ecosystem, specifically on your own data? Right? That is essentially where an architecture like this would probably come up. Now, I am giving you an example on Azure, right? So this is Azure components, but you could sort of extend this for any cloud component. Any cloud component, you can sort of extend it. So I'm going to actually show you the same thing, but more from like a, I'll abstract this out, not necessarily using the Azure components, but I'll abstract this out for all of you to, to adapt this to any kind of a cloud framework. It could be for AWS, it could be for Azure, it could be for anything. You could just basically, the structure of the architecture more or less remains the same. The components can change. Right? What are the key investments made by Jio in 2023, specifically on improving network coverage? Now, how do you answer a question like this? As I said, the first thing is you would want to have access to all of this information. So that's what you have here, right? So the first piece here is some kind of a storage container, which is basically like, think of it like a drive, right? So think of it like a Google Drive or a OneDrive sort of a thing. Basically a file storage, right? It can be your C drive or your D drive on your local machine as well. It can be a hard disk as well on your own personal machine. But basically, you have a file system where all of your files are available. Now, these are all the different documents that are available here. Right? All of these documents are available here for you. Now, what do you do when somebody asks a question? So remember, if you remember, what did we do first? In the case of the curling example, we took the Wikipedia document. What did we do? We converted that document we broke that document down into smaller chunks, and we converted that into embeddings. Remember? Yes or no, everyone? Remember that? We converted that into embeddings, right? Now, that converting that into embeddings part is what happens here, right? This is, forget about cognitive search and everything. But basically just a small, piece of component that helps you break that particular document down into embeddings. And those embeddings are, just to let you know also, to be able to do this, there is a small error here in this picture. You will also need access to this. This is the embedding creation. This is the embedding creation. So to create the embeddings, you first create the embeddings here by accessing the OpenAI service. And then after that, you store them. Remember in our example, what did we do? We put it in a pandas data frame. But the problem is pandas data frame is probably not always the best choice, right? So you would have to put it in like some kind of a database, which is very, very easy for us to access. So that is essentially your index, search index over here, or very popularly known as a vector DB, a vector database. Right? There are many, many types of vector databases that are available. This is a very commonly used vector database. This is Azure's vector database, but technically there are many vector databases that are available out there. Some on-prem, some in-memory, some on cloud. There are a lot of options. But those vector DBs are something that you could use to store this information. I'll actually walk you through an example. We will be using something like a Chroma DB. We'll solve a problem, and I'll actually show you how you can store that, vector DB. There is absolutely no logical way to read this vector, to read the vector. But can you access a vector DB? Yes, of course. Just like any other database, you will connect to it and you will read information from it. It's basically like any other database that you will be accessing this information from. That is a one-time background activity that you will have to perform. That's the background activity. Then, now there is a user. Now there is a user. And this user wants to answer questions. This user that you have here wants to answer questions. So this user is now asking a particular question. This user is asking a particular question. Now that question is whatever question that you have over here. So this user is asking this particular question. How will the user ask the question? The user will of course require a web application, right? Through the browser, through your Chrome browser or through your Edge browser, you need a web application. When I say web application, basically the chat interface. This is not a data scientist's responsibility. In most cases, the data scientist doesn't have to worry about this part. Right? This is something that an engineer or a front-end engineer, a back-end engineer, a software engineer in your team will be able to help you with. Even for example, all of this components. Simply put, this is essentially building the chat app, right? The chat application. That front end is sort of built by someone. Once that question is asked on the front end of or on the app, that question is sent into that particular question. So all of this piece that you see, this piece is now going to be present as a part of your core backend application. So this part, once you ask a question, what's going to happen is that question is going to get converted into that particular question is essentially going to be passed into the vector database. The vector database will return a set of 3 or 4 nearest neighbors, right? Remember, when you ask a question, that question is converted into an embedding, right? And then we try to extract the 3 or 4 nearest neighbors. Those 3 or 4 nearest neighbors, along with the question, we pass it into the OpenAI service, and that generates the response and it returns back into the web application. So that is the whole flow, as you can imagine here. Now, if I were to sort of abstract it from here and sort of create a very, very simple diagram for all of you, let's actually create a very simple architecture diagram right now. We'll simply create a simple architecture diagram for architecture or a data flow diagram. I would use the word data flow, but with some architectural components using PowerPoint just to quickly land the idea here. And then I'll actually walk you through some of these examples, right? So we build on top of it. Now, so this is essentially your database. Sorry, this is essentially your, think of this as your OpenAI service, right? So this OpenAI service is essentially going to be available here for you to access. Then Somewhere you have a web application, like a chat application. I am just putting this as a chat application here. You don't have to worry about how that chat application is being built. As a data scientist, you don't need to worry about it. That is something for generally your developers to figure, like your engineering teams to figure. But a chat application would typically have components like a web app, right? So they will have to build a web app. And this web app is typically built in a React or a again, if it is a mobile application, then it would probably be like a cloud, a platform native development, basically like a actual out and out web application or a mobile application that they will have to build. A React based front end. I'm just giving you React as an example. It can be built in Node or any of the other technologies as well. And then this chat application would also have sort of a backend, right? So what's going to happen is a user is going to interact, right? A user here in this particular case is simply going to interact through the web application, right? So a user in this particular case is going to interact through the web application. That is essentially what you had seen in the previous case, right? And that becomes extremely important because the web application will then act as like a entry point for this particular user. Now, it's important for me to call out a couple of things here that do not expect the user to be, in most cases, do not expect the user to always access this through a chat interface. It could also be outside of a chat interface as well, right? So we can talk about that as well. Now, I'm taking OpenAI as an example here, the OpenAI service. When I say OpenAI service, I'm essentially referring to the OpenAI API that you and I are accessing. This is sort of generally something that sits outside of your complete ecosystem, right? Which is why I'm going to put it somewhere out here. Now, when a person asks a question, right? So when a user asks a question, so now that question, Control C. I'm just going to put Q as a question. This particular user is asking a question. And now this question typically should go and hit a backend service over here. What does that do? This backend service is sort of think of it like a Python engine, right? This is a Python. It could be Python, it could be anything. I'm just taking this as an example, Python as an example. Right, so this is a Python, sort of a backend service. What does this backend do? This backend has 2 or 3 responsibilities. The first responsibility is to convert, I'm talking about key functionalities here, convert query to embeddings, right? So what this is going to do is this backend service is going to fire a query from here to the OpenAI service. This will fire a query to the OpenAI service. And what it will get back as a return is essentially a set of embeddings. So it's going to send the query typically, and it'll get back an embedding. I'm going to put an E over here. Right? It's going to get back an embedding. It's going to send a query as an input. It's going to get back an embedding as an output. And typically, what kind of a model will be used over here? Anyone? What model is being accessed to be able to generate this response? An embedding model. Remember what was the model that we had used in the example? Not a word to it, guys. It's an LLM, but you remember there was a model called ADA. The OpenAI had a model called exactly an encoder model, some kind of an encoder model or an embedding model. In this case, something like OpenAI has a model called ADA, which is essentially the embedding model. If you remember from where did that go? Let me show this to you. If you go to docs, you go to models, and under the models you can see embeddings. If you see the embeddings, this is the model. You remember text embedding ADA002. This is generally the model that we would be using for generating any kind of an embedding. This is also the same model that we had used in this example. Let me show you that. See, look at this. This is the embedding model. Text embedding ADA002. We use the same model over here to be able to generate that particular response. And you would have, in the case of some of the other examples, you would have a bunch of other models that are available like this as well. Let me just okay, cool, awesome. So now the backend has been created. This backend has converted, Python backend has been created, and it has converted the question into embeddings. Then what is the second task of the backend? The backend is also responsible for sending request to the or extracting context from vector DB. That is what this is also going to do. So once a function is completed to convert the embeddings, the second is it is going to run another function where it is going to extract context from the vector DB. So how will it do that? So for that, firstly, you would require a vector DB to be available, right? So this is your Python backend, right? And this is your chat application. This is your vector DB. Now this vector DB, you might remember, is essentially just a collection of multiple vectors, of your context. So this vector DB would have already should have already been populated with a lot of this information that we see here. This vector DB should have already have been populated with all the information that you have here. From where? So this vector DB has to be very close here. And this vector DB has access to unstructured data, whatever this unstructured data is that we're referring to, right? So it could be PDF files, it could be whatever, right? So PDF, Word documents, text files, images, whatever, right? So call it, you name it, and so on and so forth. Now, this vector DB has access to all of this information, and what would have happened and what should have happened rather is all of this information should have ideally been already ingested into this vector DB through a batch process, right? So this is not a live process. This is a batch process. So all the embeddings, right? So, E1, E2, all the way up until En, they should have all been ingested into this vector DB. Now, how will this happen? It's not going to just automatically happen. I cannot simply point a vector DB to unstructured data and say, you know what, go ahead and put everything in the vector DB. That's not how it works. So what I would need is I would need some kind of a Python job, or again, I'm considering Python as loosely here. So there should be some kind of a Python job that converts data to embeddings, to E1, E2, E3, all the way up until En, right? This is super, super critical This is a batch job, remember. This is not a real-time activity. This is a batch job, which is why I'm referring to that as a batch activity. Now, why am I saying that this is batch? Because, see, this data is probably never going to be always the same. This data might continuously keep increasing. So in that scenario, what do you need to do? You need to continuously update this vector DB. But how frequently will you have to convert that? How frequently will you have to keep updating it? Not very frequently. Whenever the data gets updated. So whenever, and that this job can be triggered through a some kind of a trigger, right? Like for example, if the data here changes, then you trigger this job. Else you don't run it. So this is sort of a batch activity. This doesn't have to happen regularly. This can happen once in a while. But this can be triggered only when there is some kind of a change in your original data itself. Otherwise, you don't need to do it. Only incremental will have to be done here. So now let's ask the question. So now there is a question that has come. There's a question that was raised, right? That question went into this Python backend. This Python job has converted the question into embeddings. There is a, and it has also sort of extracted, it has also nicely extracted the embedding, and it has also extracted the content from the vector DB. But for that to extract the content from the vector DB, it of course will have to fire a request to the vector DB, isn't it? So here is where there is a request made to the vector DB. What will have to be passed to the vector DB and what will be generated out of this particular vector DB? I'm seeing questions here. Perfect. The input has to be the embeddings and the output will not necessarily be chunks. It will be, you're right in a way, right? So it's sort of a combination of both. So it's a two-way query that's essentially going to get fired here. And the input is going to be, as you all rightly said, the input's going to be the query. And the output here is going to be the relevant embeddings or the nearest embeddings. So actually, it's going to be two things that are going to come out of this. It's not just the embeddings. It's going to return multiple things for you. So it's going to return embedding one, the embedding itself, and it will also return the chunk one, right? So which is essentially going to be a string. Similarly, and this will essentially be the first output. This will be the first one. Similarly, it would return another one like this, another one, and another one. And this is probably going to be chunk 5, the embedding 5. You probably actually don't need the embedding if you think of it. It just needs the similarity score if you actually think about it. The embedding value itself doesn't make sense, right? So the similarity score is all that matters here, and the chunk. Do you all agree with that? Right, something like 0.95, right? 0.95, 0.93, and so on and so forth. So this is similarity 1, similarity of the 5th, similarity of 100th, and similarity of maybe nth. That's essentially what's going to come back. So this is what's going to go in, and this is what's going to come out. We'll talk about images in some time. Like this architecture will change depending upon scenario to scenario. This architecture will change. But now that this is going to come out, then the next question is, now that you have the response is coming out, the next step is this Python backend will then have to fire one more query. What does it have to do? So that you've got the top 5 as a return. right? So it has returned, let's say, the top 5 or top K embeddings. Top K have been returned. Then what do? Exactly. So you will have to fire one more to then summarize, right? So for you to then summarize, so you'll have to make the second call here, which is going to be again a query that goes from here all the way up until your OpenAI service. You'll make another call over here. What's going to be the input and what's going to be the output? So the input is going to be this piece. It's going to go as an input to this, and then it'll return back the final summary response. I'm going to put it as R. I'm going to call it as R over here, or rather response, I would say raw. Right? Sort of a raw response is what you're going to get. And this raw response can be further fine-tuned to get your final response, which will then sort of be sent back through this. But broadly, do you all agree that this is essentially how it's going to work? This whole thing? Exactly. It'll compare not the score, not the embedding values, but the chunks. The OpenAI servers will essentially take the chunks. Actually, doesn't care about the similarity scores, honestly. All that it cares about is the chunks. So you pass the chunks, not just the chunks. You will also pass the question here. Remember, along with this, you will also be passing the question. So actually, it's not going to look as simple as this. Actually, that's a good point. So you're essentially going to pass one string here. So you're going to pass the question plus, right? C1 plus C2 and so on as one large string. You're essentially going to pass this as one large string over here. That's going to go in here as an input, right? And then you will come up with a response as the output here in this case. The backend service should make two calls. Yes, two calls. Yes, one to the vector DB to fetch the right information, and then one. If you think of it, it has to make. Technically speaking, if you consider this backend as a service, as a microservice, I'll talk about all the different interactions. But I think I made a small mistake here. This has to be a two-way query. It's a post query. Yeah. So if you think of it, there is one API call that's being made to the Python backend. And this Python backend first step calls the OpenAI service, that's the first call. Then it calls the vector DB, that's the second call. Then it takes both of these and then it makes a call to the OpenAI service. It takes both of these and then makes a call to the OpenAI service, which is the third call, and then sends a call back to your chat application. So that's the fourth call. So your backend application actually has 4 interactions. So this is essentially sort of the most important part of your for all good purposes, this is sort of your most important part of your this is sort of the heart of your complete application, the Python job that you see here, Python application that you see here. Python backend gets embeddings from, so if you were to sort of put let me put the sequence over here of how this works. This is step 1. This is your step 1. This is your step 2, right? This call is your step 2. Then this is your step 3. This is your step 4. This is your step 5. And this part is batch. This is a batch operation. So this piece that you're seeing here is a batch operation. So you could sort of forget about that in some sense. That is not a part of your querying process. This can sort of sit out of the whole thing. Batch, that's a very good point. Yes, the batch would also use the OpenAI service, which is an absolute reality, and I have completely missed that. So I'm going to just make it simpler. Then in that case, just change these interactions. That's it. So this is essentially the, I hope this does justice in some sense. So yes. So you're essentially passing this into this. This will essentially get this will essentially get the whole thing from OpenAI. That's another call, and then I'll pass it to the vector DB, and this vector DB will then help you generate the results as expected. What saves in vector DB is all embeddings of the corpus, right? What is the difference between vector DB and regular DB? Is vector DB a kind of tables, or what sort of data is stored in a vector DB? I'll show that to you in an actual example. But the short answer to that question is yes. A vector DB is simply nothing but, a vector DB, in all honesty, is just a regular table, nothing else. The only difference is also sort of a collection, regular collection of data. The only difference is it doesn't store data. I mean, it is a structured representation only. So you would have indexes, right? And then you have chunk one, or rather some kind of an ID identifier. You would have the raw, text. Generally, the raw text is not stored. You store it in some form of an encrypted fashion. You just binarize it and store it as a binary string. And then you have the embedding. Now, embedding is generally a vector, an array of numbers over here. That's essentially what you have. And this is indexable. This embedding that you see over here. Now, the beauty of this is that, and you would have one more array, and so on and so forth. So when you have the question array that's coming in, right? So this is essentially your embedding E. So when you have a question coming in, ideally, that's where things are generally very tricky, because what you would have to do is you will need to find the similarity of that question with this embedding, find the similarity with this embedding, find the similarity with this embedding, and so on and so forth. If you have 1 million embeddings, you'll have to find the similarity. Now, as you can imagine, this is going to be a very, very time-taking task. So what these vector DBs have is, instead of you going sequentially from top to bottom, they have an extremely fast way of retrieving the best neighbors of this particular question. So they have something called as approximate nearest neighbors algorithm built into them. What do they do? So what they do is, their responsibility is they look at all of the embeddings and the given question embedding, right? So when I say question, this is essentially the question embedding, remember. It takes the question embedding and then it tries to find the similarity across everything. But the problem is, if you were to do it normally, it would take you very, very long, because you will have to essentially write, like, I mean, if you think of it writing in Python, you'll have to write it like a for loop. It's very expensive. For loop is essentially an order of n magnitude. And if databases take an order of n time, then the problem is that they're very, very expensive, very, very slow. On the other hand, you could use some of these approximate nearest neighbors algorithms. Some examples of these algorithms are HNSW. There is something called as locality sensitive hashing, LSH. Then you have NMS lib. There are algorithms like Annoy and stuff like that. There are a lot of algorithms which find, given any array, they can compute cosine similarity of that particular array with a list of bunch of other arrays in a very, very quick fashion. But these are essentially those algorithms. That is, these algorithms that make, and by the way, these algorithms that make these vector indexes or vector DBs very, very good. It's what separates these vector DBs from your regular SQL sort of a DB. In a regular SQL database, you will just have data sitting over there. You can write an SQL query and you can retrieve the data. Here, you don't retrieve it like that. Here, the way you retrieve it is you ask a query. Once you ask a question, through an embedding, you can pass a vector as an input, and then it will try to find the nearest set of vectors against that particular vector in the shortest possible fashion. That's how these vector DBs have become very, very popular. Does that make sense? And the way they do it is because of some of these algorithms, and these algorithms are baked into these vector DBs. That's what makes these vector DBs very fast. The retrieval is extremely fast. Now let me quickly show you. I wanted to pull up the right architecture diagram, but anyways, doesn't matter. Let me show you this. Right. So I'm going to walk you through like a very simple example, but using LangChain, of course, in this case. Quickly show you how you could use LangChain to do some of these quick examples. So let me just execute this. Do we create vector tables manually or is it automatic? We'll have to create it ourselves. You and I will have to create it ourselves. Okay. So I'm gonna import like a couple of things here. I have the OpenAI key available with me, which is the one that we just used a while earlier. So the task that I'm going to be using is very simple. So I'm going to be taking like some kind of a GitHub page. So this is like an LLM powered autonomous agent. There's like a GitHub page on agents on LLMs itself, like some kind of a architecture page that is available. So I'm going to like try and build something on top of it, right? So first step, what that I'm doing is I'm using this library called Beautiful Soup. I don't know if you're aware. Beautiful Soup is essentially like a library for scraping. It's for web scraping. So you could kind of scrape any page that you wish to. So as I'm showing you here, you could just use this to scrape it. You can also pick any Wikipedia article you're interested in, right? Any article you wish to. I don't know. I extracted it about Galena. Let's maybe look for, I don't know, the 2024 Olympics or something. You can take anything you want. Where's the Wikipedia page? There you go. 2024 Summer Olympics page. Now I'm just doing one page, but you could technically park any set of pages you want or how many ever pages you want. I'm just going to extract this. That's going to simply load it. So if you actually look at the docs, there you go. So the complete page is here for us. Right, it's a complete page with the whole thing. Let me show the prints here. I can also print the content. So if you see, there is like total 85,000 lines of content. This is not complete Wikipedia. This is just one page in Wikipedia. One article in Wikipedia that I'm currently loaded, not the complete Wikipedia. So if I look at the top 5,000 lines, here's how it is. Text editor. So here's how it looks like. This is the complete first 5,000 lines of content. And I'm sure there must be some, yeah, there you go. There's some lines over here that are available. What links are related, blah, blah, blah. Yeah, there you go. This article summarizes sporting event. A lot of information that's available. This is the raw content that's available, by the way. Okay, cool. So anyways, so now going in. So now what I'm going to do is the first step, right? If you go back here, let's go to our architecture diagram. The first step. So I have, let's say, one of the PDF. So in this particular case, it's like a HTML file. It doesn't matter. You don't need to do any cleansing, Aniruddha. You can just use it as it is. Any website you want can be scraped. You just have to be a little careful about the structure of some of these pages. At times, some pages can be a little tricky, but you just have to be. You can scrape any page you want. Just letting you know, scraping is not always legal. Huh? So just be careful. So I'm essentially using a simple text splitter over here. There's a functionality that's available on LangChain that can help you basically chunk your data set into chunks of 500 words with an overlap of 100 words, right? And I'm simply going to chunk them. So if you look at now, there are a total of 239 chunks that have been created out of my complete data set, 239 chunks have sort of been created right now. Now, what can I do? Right. By the way, you can take any of the splits and you can look at the page content actually. So look at this. If you just look at the first split, and if you look at the size of the content, 481 words are there. Of course, it will not create exactly the same number of chunks. It will approximately try and break it like that. Right. So 481 pieces of information is available over here. And then if you keep going, now what I'm doing is I'm essentially loading a vector database called as Chroma. Now, see, what I want you to understand is these vector DBs, there are many, many vector databases that are available. What are all the different types of vector DBs? Let's go here. Let's quickly spend a little bit of time on this. So when you talk about vector DBs, they are broadly in memory and cloud, or rather in memory and SaaS managed instances. Let's go that way. What do you mean by in memory? And a good example of in memory are something called Chroma. Chroma also has I think that Chroma also has a managed instance, but I'm just giving you some examples. So if Chroma DB is a good example. You have something called as Face, which is also an in-memory vector DB, which basically what do you mean by in-memory? In-memory mean by in-memory as this is a vector database that is created inside your machine. Right? It's not a separate database. Are you aware of SQLite, SQLite? Have any of you all worked with SQLite? This is like SQLite. Right? SQLite is not necessarily a separate database. It's an in-memory DB that is created in your machine temporarily for you to work with. Right? It's not like a database that's created elsewhere for all of us to access. It's essentially a database that is created in your database in your machine for now, for the moment, temporarily. But there are very similar managed instances that are also available. What examples are? So Redis is a good example. Pinecone has a managed instances. Postgre, has something like this. Azure Search has a search vector DB. Similarly, you have AWS has something very similar, and so on and so forth. So you have like a bunch of such managed instances that are available that you can sort of access. Now I am creating something in memory in this case, right? So I'm using the Chroma DB. And all that I'm saying is that I'm going to be using the OpenAI embeddings, which essentially uses the text text embedding ADA model by default. I can pass the model as well over here. So the model equal to, and I can pass the model as well. But the default model is anyways the text embedding ADA 002. So what I'm doing here is I'm saying, hey, look, I'm creating a Chroma DB, but how do I create a Chroma DB? Chroma from documents. I'm passing the data as well over here. As you see, I'm essentially passing the data also over here, and I'm asking it to simply create this. Right, so when I execute this, this will now create a Chroma database, Chroma vector DB in my system right now. So it's essentially storing all of this into a vector DB as we speak. So now my vector store has been created. My vector DB has been created. So if you look at vector DB, that is a in-memory vector DB, the memory location that's been created. So now I can simply say web page broken down into 481 chunks. I'm also defining a retriever here. I'm saying, hey, look, vector store, and I'm creating a retriever. Search type is similarity, and I'm saying, hey, retrieve the top 5 documents. Whenever I call this retriever, retrieve the top 5. And I can ask, where is the Summer Olympics 2024 happening? I mean, you can pick as many as you want. I picked top 5 here, just as an example. Chroma is not a cloud vector store. It is an in-memory vector store. In-memory as in inside my personal machine right now. It's running in my memory. Yeah. So retrieved. So now I have extracted. So if you actually look at the retrieved information, see, look at this. I've asked for this question, where is the Summer Olympics 2024 happening? It has says Paris 2024, 2024 Olympics and Paris Olympics redirected here. So it's essentially pulling out all of the information for the 0th one, similarly for the first one, similarly for the second one, third chunk, fourth chunk, and if I type fifth, it's going to return an error, of course, because there are only 4 totally. I mean 0 to 4, which is essentially like the 5 thing. So it has retrieved all the necessary information. Now I'm going to use the generation part of it. So retrieval is done. Right? I stored the vectors. I retrieved it from the vector DB. Now I'm essentially going to generate it, do the generation. So, and I'm going to say, hey, chat OpenAI models. Same thing. I can use the same piece of code that we had done earlier as well. Take whatever you want. And I'm going to say, use the following pieces of context to answer the question. If you don't know the answer, just say you don't know. Don't try to make up an answer. Use 3 sentences maximum to keep the answer as concise as possible. Always say thanks for asking at the end of the answer. Context and the question. So now, this is the template that I've created. The error. Let's execute this. And okay. So if you look at this, my prompt has been created. All that I'm going to do is I'm going to say, yeah, it doesn't matter. I'm just going to delete this. That's it. Now all that I'm going to do is I'm just going to ask that particular question. Against that particular template, I'm going to say, where is the Paris Olympics? Where is the Olympics happening in 2024? Now it's going to start generating. The Summer Olympics in 2024 are happening in France, with Paris as the host city, and the events are held in 16 additional cities across metropolitan France, and 1 substitute in Tahiti, French Polynesia. Thanks for asking. And what are the top? Sure, let's search 2022. Where did Olympics happen in 2022? It made up. Should have been Tokyo. So I should, we should probably 2020 Olympics. It should say Tokyo, hopefully. Did not happen in 2020 due to the COVID pandemic. The Summer Games were postponed to 2021. Thanks for asking. Yeah, we'll have to force it to be as true as possible and not make up anything. Ensure that you are extremely truthful. Let's force it. Let's try again. Perfect. There you go. Thing. And yeah, see, if you ask this one question, who is the Prime Minister of India? Of course, as I don't know. Yeah, of course, you can force it to give you a wrong answer as well. You can definitely do that. You can say, if you don't know the answer, and we can say, come up with an answer that is extremely, that sounds super realistic. Provide some evidences to make it sound real. Okay. Now there you go. Let's go. Let's try. I don't know. It made. Yeah, it knew the answer, so it made up. So let's answer. Let's ask this question. Probably will have to change the prompt a little more. I don't know if I removed anything here. Looks like it did not retrieve anything at all from the who is the, I don't know. Yeah, looks like it couldn't find anything. By the way, also just to let you know right here, that reminded me of something. So what might be happening in this case is it's probably not fetching anything from the content itself. The reason is, so when you're looking for, vector store retriever, right? The keyword arguments that we're passing here, you can actually get it to get it to fetch information from you can pass like a you can sort of pass like a threshold. So you see here like a score threshold as well. Instead of just passing the top 5, you could also pass a score threshold. You can say, hey, look for at least something that is 50% similar. So what may also be happening? So either you could do this or you could do that too. So that is totally your choice. So if you want to go like a slightly different, you could try something like that. So you could do something like this. And so it couldn't find actually anything that's similar. It's score threshold. Yeah, with that score threshold, it couldn't find anything. Kind of bad. So let's go back to this one. Yeah, but that's like another option that you have. See, the point is the only difference that we've done here from the previous case is we've introduced this vector DB, right? We've introduced the vector DB, and the other thing that I also want you to understand is look how simple the code is right now, right? Look at how simple. I mean, forget about all. Actually, this is all not even code. Right, so I could just forget about this. This is super simple now. The code is extremely lean. Storing into a vector DB is like one line code, right? I know it's in memory, which is why it's one line. But otherwise, splitting is just a couple of lines of code, right? And storing it is like one line code. Retrieval is 2 lines of code. And then last but not the least, generation is a couple of lines of code again. Generation, we have done it in the past as well using LangChain. So that's what LangChain does. LangChain abstracts the whole damn thing. So remember in the previous case, if we were to do that, we had to write like functions over functions over functions over functions. Now all of that is abstracted. So you remember this function, the search function to find the similarity. We don't need any of this anymore because we are using LangChain, and LangChain takes care of all of this for you to retrieve the right. ChromaDB takes care of some of this for you. So especially this part is taken care of by ChromaDB. LangChain takes care of ensuring that all of the splitting and creating embeddings and everything is taken care of. LangChain takes care of all of this. So that's the beauty of using something like a LangChain, using some of these components on top of your existing solution. And once you have something like this, once you are able to build a setup like this, of course you can very comfortably build like an API layer where then you can start chatting, right? So where you can start asking questions back and forth. So my point is, you will have to start leveraging some of these components. Only then you will be able to build a scalable capability. Else, what's going to happen is we'll end up writing code that might not scale. So for that reason, it's very, very important that we need to do this. So in order to make an enterprise level application, the core piece is very, very simple. It is not going to be very complex. The core AI part is very simple. It's the engineering around it which is going to make it very complex, right? So you will have to, exactly like somebody saying, so you'll have to you can host it on Streamlit. So if you're hosting it on Streamlit, right, Anil, what's going to happen is you will not have two separate services. This web application and the Python backend will essentially be the same app then in that case. Then you will just have multiple endpoints within the same service, and then you're essentially going to go back and forth, which is again not enterprise grade. Streamlit, nobody uses Streamlit as an enterprise grade solution. It's a good thing to do demos. Streamlit is useless otherwise. It's great for demos. It's useless otherwise. Should we always use LangChain? Yeah. So you will have to build, build a proper web app, right? Build a proper web application, a native React application, or a or a JS. Use JavaScript, any of the scripting languages, and then build a front end app, and then a proper back end using either Node or Python or whatever. The good part is all of these interactions are just API calls. So you could have a nice backend over here that's taking care of all of it. Generally, what happens in our in our architecture, right? What we have done is we have one more backend over here, and then the actual core engine. The other backend will then take care of doing all the Active Directory authentications, role-based access control, all of that then comes in. So you will have like one more layer over here that is managing all of that before the application. So you'll sort of have two layers between before it actually hits the core engine itself. So all of that will come in. Is LangChain is what we will use for embedding since it's an orchestrator layer on. You could use LangChain. There are other alternatives as well. You could use either LangChain. You could also use something called as Llama Index. Right. So you could also use something called as Llama Index. This is also a very, very similar one. I'll just show you a simple example. Yeah, you see the documentation. I'll give you something very interesting. Okay. So this is LangChain, right? LangChain actually has their own chat application where you can actually query on top of their own document. So it's like, give me the code for running a simple RAG application using PDF documents in, I don't know, Google Drive. Let's go. And perfect, there you go. So it's given me the whole thing here. So it has answered the RAG application. So it has given me few things. One is it has of course given me a Google Drive here that I can use to search. And on top of this, I can say, give me the rest of the RAG code. Perfect. This is the remaining of it. Done. That's it. So they've built it on top of their own solution here. They've built this on top of their own. This is using RAG to retrieve the result. Yes. This is built on top of their own documentation. They have provided all of their documentation to this. Make sense? And by the way, if you look at it, this is exactly the piece of code that we've used. Exactly the same piece of code that we've used. Retriever, tag.run, and you could do the same in Llama Index as well. Llama Index also has their own. It's not loading. Yeah, there you go. You could do the same here as well. You could query the same here as well. Let's talk about the prompting techniques. Okay, so when we talk about the prompting techniques, right? So there are, as by now you must have realized that prompting is sort of an art than sort of a science. But interestingly enough, when we talk about prompting, there are some aspects that you can definitely control, right? So when you take up a course on prompt engineering, or when you discuss about prompt engineering in general, there are certain design patterns through how people generally ask questions, right? What are they? So the first one, more often than not referred to as, when we talk about prompting and design patterns around prompting, the first one is your regular zero-shot prompting, right? What do you mean by a zero-shot prompting? Zero-shot prompting is essentially essentially simply like asking it a question and answer to resolve a particular query within that particular question itself, right? What do we mean by, so like for example, you simply ask it a question. You simply say, hey, there are 20 people, 5 of them have gone to do a certain task. How many are left? So you're essentially asking it to resolve that particular question within that particular sentence itself. Or you're saying, hey, here's a tweet. Can you classify this tweet into one of these 3 categories, positive, negative, or neutral? And what it is going to do, it is going to try and classify that particular prompt for you immediately at that very point in time. So that is essentially referred to as zero-shot prompting. It is trying to act on something immediately, right? So without really any kind of a background, so to say, right? So that is referred to as zero-shot prompting. The second kind of prompting is referred to as your few-shot prompting, or few-shot learning, referred to as FSL generally. What do you mean by few-shot learning? A few-shot learning is where you're asking it a question, but you're also telling it how it could be answered with some examples. So for example, if you say classify, an example prompt can be classify the following tweet into positive, negative, or neutral. Use the following examples as a guardrail, right? And then you can provide the 3 examples. You can provide sentence 1 or tweet 1. You can say tweet 1. You can provide the tweet and then classification. You can say this is positive. Similarly, example 2, tweet 2, the tweet and the classification negative. And then tweet 3, the tweet itself and the classification neutral. So by this, what you're telling your large language model is you're saying, look, if it was a regular few-shot prompt, it would have simply just been this part, right? And you would have simply passed the query to it. But by doing this, you're also telling it, you're giving it an example of how to go about doing it. You're telling it exactly how it was done in the past with some examples. So that is also a very, very good way of going about prompting your large language model. Your large language models generally do very, very well when you provide such kind of approaches. When you provide them few-shot prompting, they generally do a very, very good job with few-shot prompts. So zero-shot prompting or few-shot prompting is a very common approach that you would perform. With few-shot prompting, you're sort of setting expectations. That's the right way of doing it. So this is essentially your few-shot prompting. Zero-shot prompting and few-shot prompting are essentially very, very popular techniques that are often used. Now, within these, right, using the zero-shot prompting and few-shot prompting approaches, I'll show you a couple of examples in a minute. By the way, just actually, let's look at a quick example, right, and then we can come back to it. Cool. So we can take any of the examples from our previous, from the stuff that we've done in the past. Like for example, we can take pull up the LangChain 101 example. We can actually build on top of this. Okay, cool. So if you look at any of these examples, right? So let's take, for example, one of these examples. Let me just load the .env into this, and let me go in here, the LLM, the chat model, and then we can either use the chat template or, okay, let's use the chat template. Drag, photo. Awesome. So here, right? So this, by the way, is the GPT-4o. We can use 3.5 as well if you wish to. By the way, this is the previous example. Now, what I would want to do is, let's say, when I'm providing the system prompts, here is where, so if you look at this example, right, this is a simple zero-shot prompt, right? I am asking it to get to the final answer in one go. All right, I am not giving it any slack. I'm simply saying, you're a very cordial translator. Please read before you respond. You're proficient in English as well as in Hindi. After you respond, share a small piece, and I'm simply asking it to translate this sentence into Hindi. One go. I'm not giving it any other. I'm not giving it any more context. So this is like a good example of a zero-shot prompt. Now, if I were to create something very similar for a few-shot prompt, this is how it would look like. I would say, you are I'll probably go a little multi-line. You are a very useful assistant. You are good at classifying tweet into positive, negative, or neutral. Here are some examples of how that classification could be done. Neutral or sarcastic. And then you could go something like, let's remove this actually to start with, and we can come back to this. Sarcasm is not a sentiment. So you could say, example one, tweet. You ideally should try and, whenever you're providing this information, try to follow some kind of a pattern so that it's so much more easier for it to understand, right? So example one, and here, because it's the first example, you can provide that again as, so in this case, I'm following the pattern of a JSON. So the tweet here can be, this is an amazing studio that you have, and this is the sentiment is positive, right? That's the first example. And similarly, you could provide another example. This is the second example. Tweet. This is less, and here I say this is negative. And then I can, of course, provide one more example. So this, as you can see, this process of trying to create multiple examples is super, super important. Now, you can imagine where this could be very useful, right? So, for example, if you're trying to translate some code, that's another example. And that's another place where this could be very useful as well. Right. So that's it. So that's essentially like 3 examples that I'm providing here. And then I can pass whatever input I want, and I can ask it to simply, classify it. I can pass the tweet itself. And the tweet here can be, classify the following tweet So something like that. And then you simply ask it to execute this. Something went wrong. I think, did I miss a parenthesis somewhere? Let me just simplify this. I just want to follow one structure that is easy. I think it's reading this differently. I don't know why. Okay, let's try this. Okay, so there you go. That's it. Done. So as you can see, it has returned the response, and it has returned the response exactly the way I want it to. And that seems to work. Right, yeah, that should not matter. I think there is one. Yeah, I think I removed that. Cool. Okay, but you get the idea, right, everyone? So I think I'm assuming this is clear. At least you know that when you ask a question, you don't simply just ask the question, but you ask the question, but in the prompt, you also pass some examples of how it could go about answering that particular question as well. And that's a very, very common, sort of a template that people tend to follow. It's called as few-shot learning. Now, you could also extend this to larger kinds of examples as well, right? Like for examples, you could say, you could do this for code as well, right? For code, this is actually a very, very good example as well. Like for example, you could ask a question and like a SQL query. You could ask a question and like a Python query, it also depends on, like, for example, if you're doing SQL, or natural language to SQL, and if you want to build like a small template that converts natural language to SQL, you could simply use it to use the same kind of a prompt template. But in that particular case, you pass, here instead of a tweet, you pass the natural language question, and then here instead of sentiment, you simply say SQL and you pass the SQL query here. Same tweet, the natural language query, SQL query, natural language query, SQL query. And then every time you ask a question, it simply tries to find the SQL query associated with it. So it's like a very, very good approach. And as you can imagine, when you asked it to respond back, it exactly followed the same template of response that was created earlier. You see this, right? So tweet sentiment, tweet sentiment, tweet sentiment, it exactly follow the same template of a response. So that's the beauty of a few-shot learning. Few-shot learning will ensure that the same style of responses and the quality of the responses sort of transferred, not to this as well. So that's how FSL works. Okay. Now, it's not a very complex, task, but this is something that I just want to let you know. Now, why is this important? Now, the reason why I wanted to introduce this is because I want to talk a little bit about some more, techniques over here. I want to talk about a few more design patterns over here, right? Along with these two, zero-shot prompting and few-shot prompting, there are some more advanced prompting techniques as well. Like what? So one of the most popular prompting techniques is referred to as chain of thought. What do I mean by this? Chain of thought is essentially asking. So I think somebody just asked me about a math problem, right? So this is the exact kind of prompting that you would have to do to be able to answer math problems. So a chain of thought prompting is, you must have observed at times, right? So if you ask the LLMs like equation, and if you just ask them to solve it like a zero-shot prompt, they fail. But the same question you ask them by structurally having it to break down step by step, right? So if you tell it break down this particular problem step by step and then get to the final response, more often than not, they do a very, very good job of it. They do a fantastic job of it. So that process of breaking down a particular question step by step is essentially what we mean by a chain of thought prompting. So this is to force the prompt or have LLM break down a task into multiple subtasks or multiple sub steps, I would say, and answer it one by one. Right? That is what we mean by a chain of thought. Now you could also do chain of thought, right? When you're doing chain of thought, you could do chain of thought both ways. You can do chain of thought using zero shot as well as few shot. What do I mean by doing chain of thought through zero shot? When you say chain of thought through zero shot prompting, you are essentially going to simply add the sentence as a part of the prompt. You can simply say answer this question, but break down this particular question into sub steps and answer each of the sub steps and then get to the final response. So you will write the prompt that way. When you do it like through a few shot, you are actually going to tell it how those sub steps are going to look like. You will explicitly tell it what those sub steps should look like. A very good example is through chain of thought. A very, very good example is where you simply say, you can ask it a question like, okay, what are so the question could be, the query here could be something like, why did the sales of, let's say, Mumbai come down for our business? Right? So you're essentially asking a very specific question. And here, along with the question, you also say, break down the analysis into the following sub steps and answer one by one and summarize the final response. Now here you're going to provide an FSL. So the question is, why did the sales come down? And then you can provide multiple sub questions. And then like a final response of how you would summarize all of it. So by doing that, you are providing some kind of a guardrail, again, some kind of a example, a precedent as to how your LLM should go about answering that particular question. Again, it's the same thing. It's few shot learning, but few shot learning with a little more structure. So you're asking it to break down a question into step by step. So it has often been observed that specifically for math problems, this kind of works very, very well. So let me give you an example here. By the way, you could also like change how the way you're writing the prompt here, but that's up to you. So you could use LangChain's what was the system message? I think from .prompt template, if I'm not wrong, .schema. But anyways, so you could also say .schema, import system message, comma, human message. So this will essentially, instead of you passing it like this, you can simply say system message off and human message off. That will also take care of it. But anyways, doesn't matter. Okay. So let me just delete this. So in the system message, you can simply say you are an assistant that is very good at solving math problems, right? And you could say, and the input can simply be the question that you wanted to answer. So it could simply say, solve the following equation. And you can say 3x plus 5y is equal to 320 and 2x minus 3y is equal to 110. And I can ask it to simply solve both of these equations and then come back with a response. Now, while it is actually, so look at this. So it's actually tried to solve this particular problem. It has actually already tried to break this particular into step by step, and it has tried to solve the problem. We can use the method of elimination or substitution. Here we'll use the elimination method. So it's already tried to do it. That's probably also because I'm using a 4.0 model. Let me try to go for a 3.5 turbo or something. The 4.0 models are actually pretty good. Four models are actually very good at math. Yeah, so it's tried to answer this question. I don't know if this is actually true, but we can see 3x plus 5y is equal to 230, 2x minus 3y is equal to 110. To eliminate one of the variables, let's multiply equation 2 by 5 and equation 1 by 3. Seems all right so far. First one by 5. Yeah, it's actually messed up here. Right, so 230 multiplied by 5 is not 550. So it's sort of messed up. And this one, 110 multiplied by 3 is also not 690. That's clearly messed it up here. Again, a very, very confident answer, but clearly messed it up. Now what I can ask it to do is I can say specifically here, I can force it to break down the problem into multiple sub-steps. I'm going to be very explicit here. So this is essentially chain of thought, right? So I'm asking it to break it down into multiple sub-steps and ensure every step is perfectly validated and the response is appropriate. Only proceed to the next step. Thank you. Okay. So, I'm sorry. Now let's try this. Okay, now let's take a look at this. What is it saying? We'll solve the second equation for x in terms of y. 2x minus 3y is equal to 110. So 2x is equal to 3y plus 110. X is equal to this. So far, okay. Let's go to step 4. Substitute the expression for x into the first equation. So it's taking x value of x and substituting this into the first equation. So 3 times 110 plus 3y by 2 plus 5y is equal to 230. So 3 times, that's not bad. So 10y is equal to 460. It's essentially taken the LCM and it's taken the 2 onto the other side. So 460, so far so good. 330 plus 9y is equal to 10y, plus 10y is equal to 460. Perfect. 19y is 1310. Sorry, 130, which is also perfect. Y is equal to 130 by 19, 6.8. Perfect. This is good, right? See, that's the difference. So when you prompt it and when you ask it to go step by step and validate every step, it does a much better job than in the previous case. It just screwed up earlier, right? So I'll actually leave the previous one also here. So that is chain of thought. So actually here in the previous case, it was able to come back with the right response here as well, but it made some mistakes otherwise. With the 4.0 model, it messed up. With the 3.5 model, it got to the right answer. But you get the idea, right? You understand how these prompts really matter, right? So you're essentially structuring how it should operate. You're getting it to operate a certain specific fashion. And that becomes extremely important for these models to perform. What you could also do, right? You can follow. Now this is taking it one step further, right? So you can take it one step further. You can follow the following approach to solve a simultaneous equation. So what is it? Problem is, I don't know, x plus y is equal to 10. And x minus y, x minus 2y is equal to pi. And then you can ask it to solve it a certain way, right? Subtracting step 1. Multiply the, I'm just taking a slightly longer route. The first equation by 2 on both sides. And it's, so this is going to make it 2x plus 2y is equal to 20, and x minus 2y equal to 5. And equation 2. Step 2, subtracting. So essentially, both the adding both the equations, you would get 3x is equal to 25. X is equal to 8.33. Step 3, substitute x in one of the previous equations. So you got to essentially solve it for it and show it how you would ideally solve it. And then maybe provide like a couple of examples of this. And then you can hope for it to follow the same approach. And 8.33 multiplied by whatever. So x is 8.33. So what would be y? Y is equal to 10 minus 8.33. So y is equal to 1.67. Final answer. I just went the longer route just to add a few more so just to kind of add some content here, because I ended up picking slightly simpler examples, which is why. Yeah, and you can ask it to follow the same approach. And I don't know if this makes sense. So this is what it did. This is why it messes it up, because I asked it to add step 2. I asked it to add both the equations, because the first one it did an okay job, right? Multiplied by 3 to get a common multiple for one of the variables. Did it get a common multiple here? Well, unfortunately, no. So it messed it up. So it messed it up here. So clearly, this one example didn't really help it. And second, it ended up adding both of them. And I don't know how it ended up with just 25x, because it did get 25x here. But then it completely missed out the 10y from this, because it just assumed that this 10y here will simply get subtracted. So which is why the other thing that you have to bear in mind is you have to be very explicit why you did what you did here. I have a common multiple for y. Now look at this. Now I just changed one letter here, common multiple for y, because that made it a lot more easier for it. Equation 1, 9x plus 15y is 690, 10x minus 15y is 550. It's subtracted to do 19x is equal to 1250, x is 65.26. Substituting that back here, y is 6.84. So spot on. We got the answers right now. Make sense? And it exactly followed the same structure as to how I wanted it to work. You follow the same exact structure. But remember, this should be few shot. I just gave it one example here. This should ideally be like 5 to 10 examples. You can provide 5 to 10 examples here, and that would typically help the quality of the responses. That would typically improve the quality of the response. Okay. All right, let's keep going. Now I'm going to talk about one more prompting technique. Another popular prompting technique called as React. Another prompting technique, React, which is essentially a short for reason and action. So the React template or the React design pattern is again a very, very, very effective one. It's actually more effective than a chain of thought one, where you are asking the model itself to reason at every step. Instead of just breaking the problem down into multiple steps, you're asking why it needs to do a few things, right? For example, let me actually pull up the paper that published this. There was actually a paper that was published on React. I'm trying to see if I can bring it up for you. So this is the paper that was published. This was a paper that was published in March 2023. So last year, again, Google, for some folks from Google had published this. Very interesting, where they talk about synergizing reasoning and acting in language models. So they talk about how language models have demonstrated impressive performance across tasks in language understanding, and interactive decision making, their abilities for reasoning, chain of thought prompting, which is what we saw, and acting. There's something called as action plan, which we can also, wherein it actually generates like a complete plan of action, and then, or it's also referred to as plan and execute, which is like the other kind of approach. There is chain of thought and there is plan and execute. Plan and execute is like when you ask it a question, it completely generates the complete plan and then executes it, which is also another way to prompt your LLMs to operate, right? In this paper, we explore the use of LLMs to generate both reasoning traces and task-specific actions. So this is a very, very good example of what we mean by React. So if you look at this, let's actually go to the query itself. The question is, aside from Apple Remote, what other device can control the program Apple Remote was originally designed to interact with? Right? Aside from Apple Remote, what other device can control the program Apple Remote was originally designed to interact with? So it's saying, okay, what other remotes can we use can control the program. Apple Remote was originally designed to act, so like for example, Apple Remote was designed to act to probably design a few, to control a few things. The question is, what other remotes can be used to control the same thing? So I need to search Apple Remote and find the program it was originally designed to interact with. That's the first thought. The action is search. So it's going to search for everything about Apple Remote. The observation is the Apple Remote is a remote control introduced in October 2005. So it's basically got a lot of information about the Apple Remote. Then Apple Remote was originally designed to control, and I need to search, and it again tried to get more information about the same thing. Front row media center program, originally designed to control the front row media center program. But it couldn't find the front row media center program. And then it says front row is not found. I need to search front row software. So it went about again doing the same thing. So front row software is controlled by Apple Remote or keyboard function. So the answer is keyboard function keys. So the answer is keyboard function keys. So Apple Remote can also control keyboard function keys. That's how it went about answering this particular question. So it went one after the other, right? So it is essentially trying to ask itself what are all the different sub questions that you have to ask. So here's another example. You are in the middle of a room, looking quickly around. You can see a cabinet, a cabinet 6, a cabinet 1, a coffee machine, a countertop, a stove burner, and a toaster. Your task is put some pepper shaker on a drawer. Your task is to put some pepper shaker on a drawer. It's kind of a very weird question to start with. Think. First, I need to find a pepper shaker. So it's trying to find like where the pepper shaker is likely to appear in cabinets 1 to 6. Countertops 1 to 3. So go to cabinet 1. On the cabinet 1, you see a vase 2. Then it's going one after the other, as you can see here. So action, observation, action, observation, action, observation, action, observation, and finally you put the pepper shaker on the drawer 1. So what you ended up doing is to be able to get to the final response, you have performed multiple actions, and at the end of every action, you again had to reason. Okay, is this the right step or not? Okay, seems like it's the right step. So then let me go back. Let me redo this again. And you continuously do this time and time and time again until you get to a final response. It's a very, very, very effective approach to get to a specific kind of responses. And it's very good when you're dealing with it is extremely time taking. Absolutely, yes, and that's exactly what you see here. Chain of thought is fast, but React can be a lot more time taking. They've benchmarked this against multiple models, but the quality of the responses that you get and the quality of the outputs that you get is insanely high with this, right? So correct reasoning. So if you see, look at the quality of the responses. True positives, 94%. False positives. In a chain of thought, your false positives are 14%. Hallucinated reasoning, essentially. Your chain of thought tends to hallucinate a little more than the others. So, but when you do it through React, it tends to hallucinate much lesser. Reasoning error. In the case of chain of thought, it is, this is by the way, failures. In the case of React, the reasoning errors are much higher. That's also because you're going to be doing multiple steps one after the other, which is why the number of reasoning steps that would fail will be much higher in the case of React. Hallucination, of course, is almost 0%. Label ambiguity and stuff like that. So there are some other aspects which are being tracked over here. You can read through the paper. I'm not going to go into this into much more detail, but the idea here is to be able to take any piece of question and break that particular question down into 3 aspects: action, observation, and the thought, action, and observation, right? And let's actually, with that, right, let me actually go back to the OneNote and let me quickly show you some examples of this. So I'm going to show this to you through actually the agents examples. Okay. I'm going to show this to you through the whole idea of agents. I need to also introduce the idea of an agent to you, by the way, before we go that far. But basically, I'll introduce the idea of an agent before I go that far, because it's hard for me to explain that without explaining what an agent is. In a lot of ways, what your React is trying to do is sort of act like an agent. So let me actually go back in here itself. Let me first quickly touch upon what an agent is, and then we can go back to this. Okay. So what is an agent? So what we just saw with with React is essentially like an agent, right? This is React. If you think of it, reason and action. There are 3 steps when you talk about React. This is step 1, this is step 2, and this is step 3. Right? Step 1 is action, step 2 is observe, step 3 thought, and then go back. And then keep repeating this. Go one after the other until you get to the final response, right? So this is like a very, very good example of how you could go about, improving the quality of your response one after the other. Now, the thing about these agents is that these agents by themselves at times are not capable enough. These agents, right? They require some tools. What kind of tools are we talking about? For example, these agents will require access to internet, will require ability to execute some code, will probably require querying a database, will probably require looking at, so some of the more advanced agents might also require access to your camera to click a photograph, right? They might need access to a camera to click a photograph. They might need access to your mic to listen to what's happening out there, right? So these agents can now start leveraging all of the tools that are around them to gather more and more context. And then with the ability of React, you could then start going back and forth, right? You could get more information because now you're not solving the problem in one go. You're not just looking at context as a complete blob. You're answering one part of the question, then going back, observing what has happened, then coming back, gathering more information, then answering it again, then gathering more information, answering it again, and so on and so forth. So as a part of it, having access to a suite of tools will always be very, very helpful. For example, what are these tools? As I said, internet is a tool, right? So imagine you have access to Wikipedia. Imagine you have access to, imagine your code has access to, let's say, executing something on your Python shell, right? So let's say it has access to shell or REPL, Python REPL interpreter, right? Or it has access to, let's say, querying against a database. It has a SQL tool, SQL tool, where it can actually query this information against a SQL database, fetch the information, and then run it. So these kinds of tools can be game changing, right? So these agents, when they're performing a specific action, they have access to all of these tools, and these tools and agents put together, they then start making better decision making. They then start improving the quality of a response. Let me show you what I mean by this through an example. Okay. Let's start with a very, very simple example of a tool, right? So we can get to the advanced one a little later. But let me start with a very, very simple example. So here's the thing. I'll ask you a question. Do you think these LLMs have access to everything on my system right now? These LLMs right now, do they have access to everything on my system? They don't. Now what I'm going to do is I'm going to try and provide them getting access to some time, running some piece of code. I'm going to give them some of those capabilities, right? So I'm going to give it a tool that can execute some piece of code on my Python machine and then get a response. Let me show you what I mean by it. So this is regular straightforward stuff. So if you see, LangChain has something called as create React agent. So this React agent, as you can see, this tool is create an agent that uses React prompting. I'll show you exactly how the prompt looks like in a minute. So what I'm doing is I'm creating a simple Python function over here called get current time.
very simple tool. It's a function, right? This tool is currently local, but you can imagine this tool sort of being a remote function as well. It can be an API as well, right? The way you should think of tools is as APIs, is access to APIs. It can be access to interfaces, whatever those interfaces are. An interface can be a web interface, an interface can be a physical hardware interface through a camera or something. It is the ability to invoke a small capability. It is the ability to invoke a remote functionality somewhere that is outside of this ecosystem. That's essentially what you would mean by a tool here. So this one is a very, very simple tool, which returns the current time, right? I'm saying get current time, and I'm saying pass any arguments. This does not basically require any argument. Ideally, you don't need to pass any argument to it. And inside this, all that I'm doing is I'm importing date time, and I'm saying date time dot now, and I'm returning the time. So if you actually take this piece of code, and if you simply run it, it simply says 9:15 p.m. That's what it would say, right? This is hours, minutes, and AM, PM. That's essentially what it is going to say. 9:15 p.m. It is essentially, this is running on my current system. It is accessing my current operating system, and it is returning the response. So this is executing Python code on my subsystem right now. Now let's go back here. So what I've done is, this is the tool that I've defined, and I'm registering this as a Python tool, or sorry, a LangChain tool, right? I'm naming it something called as time, and I'm saying the function is this function. Get current time is the name of the function that it will have to execute. And what is this description for? What is it supposed to do? So I'm giving it some example over here. Useful when you need to know the current time. Whenever you need to know the current time, you can basically run this piece of code, is all that we are saying. This, you can use this tool when you need it for current time, right? Similarly, I can also I'm creating another simple function here. Now, this is, you can consider this as another tool. Every function can sort of become another tool, right? And I can register this as another tool. This is tool 1, another tool. I'm going to call this as path. The name of the tool is path. And I'm going to say get current path. Description. This description is very important. Useful for when you need to know the path for the current working directory. And that's another tool. Now, is this clear so far? Do you understand how these tools are? So this is a tool. Similarly, you can imagine, you can create functions over here that are interacting with Wikipedia, that is interacting with a camera, that is interacting with, let's say, a mic, that is capturing some information and gathering information. Tools are simply capabilities or small functions, utilities that can gather more information for you, right? They can connect to an API, they can get you some current status, current information, they can be anything, right? Weather is a good example, right? You need to know what the weather is, but I don't have a weather. Agent is the controller. Exactly. Agent will decide how to use all of these tools, and then decide how to, how to orchestrate, use these tools, and then answer larger questions. So now these tools are here. Now let's actually look at the prompt. So the beautiful part about this is this React reason and action, there's a very popular prompt template that's already available for people to use. So this man, right, his name is Harrison Chase. He's the guy who's written who has written LangChain. He actually runs LangChain himself. So the question. So this is essentially a prompt template to invoke a React agent. To invoke a React prompting methodology, you essentially will have to write a prompt that looks like this. The input question you must answer. You should always think about what to do. The action to take. Action is simply nothing but. So the question is nothing but the input question that you need to answer. The action is simply nothing but so it's saying answer the following questions as best as you can. You have access to the following tools. So you'll pass the list of tools. Use the following format. Question. The input question you must answer. Thought. You should always think about what to do. Action. The action to take should be one of these tool names. Action input. The input to the action. Observation. The result of the action. Then the thought. Right? This thought, action, input, observation can repeat n number of times. How many ever times? This thing can repeat multiple times. Thought. I now know the final answer. And then the final answer to the original input question. So if you see here, you're essentially running this multiple times, n times. I now know the final answer, and then you get the final answer to the question itself. And then the question, the thought, and the response. So I just executed, prompt is equal to hub.pull. You can essentially get this complete prompt for you to use. Does this make sense? Because I'm using LangChain. But if you want to use something else, feel free to use it. That's totally fine as well. Chat model, GPT-4o. And then this is the agent. So far, I've defined the tools. I have the prompt. But I need an agent that can run all of this, right? So here's the agent. So the LLM, tools, prompt. And I just have to execute this. So if you observe, I've defined all of this. Okay, all of this is defined. So I've passed the agent and the tools that it has access to, and I'm saying run. So now if I simply ask this question, what time is it now? And look what it is saying. I need to find the current time. Action. So this is the question. I need to find the current time. And then action is time. Action input is, so it got the input. I now know the final answer. Final answer, the current time is 9:22 p.m. Finish chain. Just return the final response for me. Right? So for example, if you say, how many directories are there So look at this question. How many directories do I need to hop from my C drive to get to the current path? Okay, let's go. Let's ask this question. Look what it has done. Action is path. It has now decided to use the path tool to answer this question by itself. To determine how many directories you need to jump to, I need to know the current working directory. So the action. So it got the current working directory. This is the current working directory. To the current path, I need to count the number of directories in the path. So the path can be broken down as follows: users, funny, OneDrive, trainings, IP training, AI, AP, TensorFlow, NLP, RAG. There are 8 directories to hop from C drive to reach the current path. Final answer, you need to hop to 8 directories from C drive to the current path. And then it has returned the final response for me over here. Does this make sense? Do you understand how it's leveraging? So it has decided to use this all by itself. Now my question is, if it does not have access to this particular tool, do you think it would have been able to answer this question? Of course not. It doesn't. All right, let's look at another example.
Now this time, take a simple example. Okay, let's take a slightly simpler one, but this time I'm actually going to show you like another tool, which is I'll show you how to access a Wikipedia tool. Remember in the previous example, we tried to copy paste like a Wikipedia page ourselves. We used beautiful scoop to scrape it. Now I'll show you something more interesting. So let's go. So let's take a look at this. So now you have access to this. So I'm doing the same thing again. Okay. Are you aware of how to deploy, forget about large language models and all, like regular ML models? Do you know how ML model deployment works? Okay. So step number one is to understand how that works. So the way to make that work is there's a whole concept there. There are multiple ways of deploying it. You could deploy it on your personal machine. You can deploy it on a on-premise server. You can deploy it on cloud. You can deploy it on the edge. There are multiple ways. You can deploy it on phone. You can deploy it in multiple places. There is absolutely no limitation around how you could deploy a machine learning model. That space has been beaten to death, meaning there are some very, very good architectures on how you could deploy the most complex or the complex ML models. To your point, even on rockets if required, because a lot of the intelligence is determined by a lot of these intelligence systems that are embedded into the into the rockets as well, right? So not when I say rockets, I'm using the term very loosely, but the point is these any sort of a space mission, if you think of, they all have very, very intelligent systems. A lot of decision making happens by themselves. So short answer to your question is ML model deployment can happen at multiple levels. One of the most simplest ways to deploy a machine learning model is there are two steps in the process. There's the training step, and then there is the inferencing step. What do you mean by the two? Training is the process part of the model building, right? So this is model building. You are all aware of. You can do model building in batch, right? And then you have inferencing, which is nothing but to be able to generate predictions from that particular model. Generally, you need help with this step, not this. Training can be done on local machines. Training can be done on large, high performing computing machines. Training is not the problem more often than not, because training is sort of a batch exercise. Inferencing is the step where you need more support. Inferencing is where you would require more help because inferencing is simply nothing but generating prediction. A good example for that is, imagine there is a website, right? This is a banking website, right? There is a user that has come to this particular banking website. Now this website, and this is, let's say, on the internet, the person is trying to communicate through the internet through everyone. So this is, let's say, a web page for that matter. Now this person is trying to apply for a loan, right? This person is applying for a loan or inquiring about a loan. Now the thing is, the beautiful part is a lot of these banks these days have, real-time loan approval systems, real-time eligibility approval systems. What are they? They are ML models behind the scenes. All that they do is the moment when somebody comes in, they put in all of their details, right? So they put in all of the details, the age of the person, the location of the person, the the occupation of that particular person, salary of the person, so on and so forth. And then you have all of this information, and then you also put your Aadhaar or something, or your PAN number, right? You put your PAN number or something, most probably PAN. And then what happens is the moment you add all of that information onto the website, this website makes a call to a remote server. Now I'm using the word server very loosely here. This is a remote server. You're going to make an API call to this remote server with this details, right? And within this server, your machine learning model is sort of running in like a Python environment over here. So there's a Python environment that's created in this remote server. And inside this Python environment, there is a ML model that is waiting to generate predictions. So all that you have to do is you're expected to basically send all of this details into this ML model, right? And this ML model would generate a response. So you would have done this on your Python machine, right? So you would have done model.predict. So this is basically the same thing. This is also the same thing, model.predict, but that model.predict is wrapped under a web service. So you essentially build an API layer around it, right? And you can use some tools like Django, Flask, or Fast API. There are many frameworks that are available for you to build these web interfaces around it. Now, once you build that web interface, once you pass this information through an API, the ML model takes this information, generates the prediction, and then sends the response back. It sends probability of, let's say, default of this particular person is 0.8. There is an 80% chance that this person will fail to pay back. The moment that comes back, this website over here or the backend of this particular website will take look at this probability score and it will say, this probability is very high. It will execute some kind of a business logic and it will say, this probability is very high. So we are not going to process a loan for this particular person. We will come back and say, we are very sorry, you are not eligible for your loan given all of these information that you have passed. Now, this, my friend, this whole aspect of taking an ML model, hosting it on, wrapping it under Flask and then hosting it on a server is all referred to as ML ops. So it's important that you learn ML ops, which will teach you how to deploy a particular model on a particular machine. And by the way, this is a real-time call. In most cases, you probably don't need a real-time call. You just need a batch execution, right? For example, a lot of the information that you see here for existing people might already be available. So you don't need any kind of a real-time model. You just probably will require a batch model, meaning a model that generates predictions once every day, once every 10 days, once every 15 days. So in that case, you don't need any of such kind of a complex setup. All that you need is you need your Jupyter notebook to be scheduled, right? Your Jupyter IPYNB, your IPython notebook .IPYNB. This simply will have to be scheduled to run once every 20 days, once every 15 days, whatever. That is essentially like another way to deploy. So batch deployment versus real-time deployment. Yeah, so for example, a good example of a batch deployment is churn predictions, right? Likelihood that you will quit. So imagine you're working for a telecom company and basis your current behavior, we would want to evaluate how likely are you to churn. Churn meaning how likely are you to discontinue the services of, let's say, using Airtel or discontinue services of using Jio. Right? When you look at the typical behavior of a particular person, you can evaluate how likely is this person to churn. Now, this likelihood of churn, imagine if I know that a person is likely to quit, likely to discontinue my services. If I am a Geo, customer service representative, what I would probably do is at the beginning of every day, I get a list of people whose score is very high. Then basis that, I'm going to reach out to them and I'm going to specifically make a call and say, sir, you have been one of our very good customers. Hence, we have an offer for you. We are providing you with, I don't know, we are slashing down your monthly rentals from 300 rupees to 200 rupees, or whatever, right? So we will bump you up from 4G to 5G for free, for the next 5 days. For the next 5 months, you don't have to pay a penny, or we will give you a Geo subscription for the rest of the year for free, something like that. So the point is there will be some kind of an intervention that will be planned, there will be some kind of an intervention that will be planned over here, basis the fact that basis your churn score. It's called as a churn score, or a risk score. Now, this doesn't have to be a real-time exercise. At the end of every day, I will collect all of the activities that you have done as a customer,
right? I will take that information, I'll pass it into my ML model and generate predictions for all the customers at once. I don't need to do it one by one. I can do it for everybody together at once, right? And that can happen at midnight, once every at 12 o'clock in the morning, 2 a.m. in the morning, so that by the time this customer service representative logs in, then this would simply get updated. So for that to happen, all that I need to do is my ML model will have to generate predictions once a day. Now, how can I do that? All that I need to do is I need to essentially take my Jupyter notebook, right, or my Python file, and then I simply will have to schedule the execution of this particular file once every 1 day. And that is essentially how you do it, and that is a very simple. You don't do it on local systems, you do it again on remote server, but you just schedule it. You never do anything on local systems. In enterprise grades, in enterprise setups, you never run anything on your personal machine. Okay. Again, all of this, my friends, is a part of ML ops. All of this is machine learning ops. Okay. Right. So let's build on top of the understanding of of agents. Right. So I think we looked at a couple of examples earlier on agents. Basically, like you are using tools which are like more local, but this time I'm going to show you some more interesting tools that are available. And I'm going to show you, as I said, right, I just want to show you the Wikipedia tool and how you can access the Wikipedia tools. So the good part about LangChain is LangChain comes also. So while you can create your own tools, LangChain also comes with some inbuilt tools, right? So I'm going to show you how you can access one of those inbuilt tools right now, right, which is the Wikipedia tool. We'll also try using some other tools as well as we go along, but let's try. Let's go one at a time. So here you go. So .env, of course, this is essentially the simple loads. And let's say I ask a simple question. Hey, user will input. So this is, let's say I'm going to ask it about T20 Cricket World Cup. And I ask it a question. I say, who will win? User will input a year, and you will need to get the T20 World Cup details, and I say 2024, but there's no T20 World Cup scheduled for the year 2024, which I think is nonsensical, makes no sense. The next T20 World Cup is scheduled to be held in 2022 in Australia, which is again ridiculous. I don't know why that's the case. TP 3.5, which makes sense because it was trained only until, if I'm not wrong, until like 2021 September or something. But anyway, this is ridiculous, as you can imagine. But now let's build on top of it. Let's use React, and let's also use the Wikipedia wrapper, right? So let's give it more context here. It's the same thing, but this time I'm going to use tools and I'm going to use the React agent. So I'm going to use two things. The React prompting, I'm going to use both of them put together, and then we'll try and solve the same problem. So I'm using the same prompt that I had shown you all earlier. The React prompt. So if you look at the prompt, it's the same thing as I had shown you earlier, which is answer the following questions as the best as you can. You have access to all the following tools. We'll pass the list of tools that it has access to. Use the following format. Blah blah blah. Now, what else am I going to do? So I'm going to say, I'm going to define the API wrapper here, the Wikipedia API wrapper. So I'm saying extract the top 5 results. By the way, just to let you know, right, if you just use the API wrapper and I think .run, and you can pass any details, Olympics 2024, and it can actually return like all the articles from Wikipedia right now that match these keywords. So it actually queries against it specifically from Wikipedia, and it'll return the top 5 results for you from that 2024 Summer Olympics. But you remember this, right? This is what we did earlier. What did we do? We manually queried this information. We copy pasted it, if you remember, right? Instead, you could just use this to query it. That's one of the most beautiful things about the Wikipedia API wrapper. The beautiful things about open source. Wikipedia is open source. So the API is open source. You and I can query against it, and then you can kind of get that information for you. So that's how you can query, and you can execute it. You can also actually see this here. Bring this up, new window.
I hope you can see my screen. Okay, perfect. Wikipedia API. And if you actually look at the Wikipedia API, this is the main page to access the API. And here's how you can access all of the APIs, the English Wikipedia API. You can go to this page and you can see how to access all of it and everything. But the beauty is all of that is nicely wrapped into this tool over here for you. You don't need to worry about anything. It's nicely abstracted. LangChain has done a fantastic job of abstracting that for you. So now all that I need to do is I simply have to say, hey, look, agent, and there's only one tool that I have provided it for access right now. But if you want, you can provide as many tools as you want, like what we did in the previous example. Here, it has only access to one tool, but you can provide other tools as well if you wish to. Same LLM tools and prompts. The LLM is the 3.5 turbo, if I'm not wrong, the GPT 3.5 turbo. The prompt is the prompt from the previous step. The tool is a Wikipedia tool. So I'm creating the agent executor, and then I'm simply going to say agent.invoke. Who won the 2024 ICC Men's T20 World Cup? Now, if I ask it this question, look what it does. I should search for the winner of 2024 ICC Men's T20 World Cup. Okay. Action Wikipedia. So it's using the tool here. Action input is 2024 ICC Men's T20 World Cup, and it got these 5 pages as output. Right. So it has summarized each of these pages for you. 2024, 2026, 2024, 2025 ICC Men's T20 World Cup, Asia Qualifier, 26 Men's T20 World Cup. It has looked at all of it and it has responded back saying India won the 2024 ICC Men's T20 World Cup by defeating South Africa in the final. Do you think the LLM would have had access to this information otherwise? No. The LLM has not been trained on it. The LLM would have required access to Wikipedia. But then I would have had to put the information from Wikipedia myself. Or I would have had to extract all of it, put it in a RAG, and then run it. The beauty with this is because that interface has been exposed as a nice API for me, I was able to nicely weave that into this complete agent structure. So I didn't have to build a RAG to solve this problem. It did solve it in some sense because all that it did is kind of pulled up this information and it tried to summarize it. So in a way, if you think of it, it is RAG, but it is not actually RAG because it is querying against a API in this particular case. Does this make sense, everyone? Do you understand how this is sort of a slightly different design than that of your RAG? Now let's take it one step further. So there's Olympics going on right now. And of course, you want access to internet. So now let's look if there are tools that are available out there that provide you access to the internet, right? Imagine if there was like a Google API that was available, a Google tool that was available. The good thing is it is actually available. Let me show that to you. Let me pull this up. Let's go. Okay, let's go. Let's take a look at this. And this is all LangChain. I'm sure there are tools in Llama Index as well. I haven't personally explored Llama Index myself. I did very, very long ago, but I haven't really spent a lot of time on it. But let's take a look at this. Tools. There are built-in tools. So these are all the different tools that are currently available. So Alpha, Vantage, I think this is for, if I'm not wrong, for financial information. There you go. This is all for financial information, real-time financial information. So you can actually use this if you wish to. Some of them will require keys. Some of them are free. For example, you can use a Dolly image generator. You will need a key for that. DuckDuckGo search. You can access Google Drive, Google Jobs, Google Lens, of course, Google search. But for Google search, you need API and you need basic keys, right? So you need to set these keys. I don't have access to it, but there is this one which is free. DuckDuckGo search is free. This is anybody can access it, right? So let's try this. Let's actually try this. Let's look for if there's a YouTube. If it's not there, you'll probably have to write it yourself. There you go. There's a YouTube video access as well. YouTube's there as well. There's Yahoo Finance. Yeah, there's a bunch of these guys. So again, let's go back here, right? So let's take one example, right? Let's go with DuckDuckGo search. Now this is like a simple search. That the reason I'm going with this is because this is search, this is internet, and then yeah, is out here currently. Oh, sorry. Okay, let's go to the latest one. LangChain tools. Simple, built-in tools. I don't know why this is so hard, but anyways. Anyway, doesn't matter. So let's try this. Let's go DuckDuckGo. So I'm just going to try this out quickly. And what we're going to do is we're going to try and bake that into this, right? So we're going to create the same tool. I actually tried it, by the way. I don't know if it worked, but let's try. So same thing. So I have a Wikipedia tool here, but now I'm going to add one more tool, which is internet. Okay. Useful for accessing live information from the internet. Okay. And this is going to be, yeah, actually, I don't need to mention all of that. I just have to mention the name of the tool. That's it. From LangChain and dot tools import DuckDuckGo search results. I would assume that's the one. Let me just verify here. Search run. See, search run. And well, actually no, it's the search results only that I want. Okay, search results. And search is equal to DuckDuckGo search results. I'm just gonna go here and I don't need to mention any of this. I hope that works. Let me just go back here. Query run. Let's try. There you go. This is how I'll have to embed it. A wrapper, DuckDuckGo search API wrapper. From LangChain dot to dot which is okay. Okay, DuckDuckGo search API wrapper. And then all that I'm going to do is I'm going to define the wrapper. Like how, so it's basically the same way as how we've defined this. All right, so I'm going to define the same thing. I'm just going to remove this. And I'm going to remove this. Sorry for the back and forth, everyone, but API wrapper. But this time, the only difference is this has to be the DuckDuckGo API wrapper. I'm going to remove all of this just for simplicity. And I'm going to go API wrapper is equal to API wrapper. And where is the run? DuckDuckGo search run. All right. I think that should do the trick. Okay, so I have a get time tool, which I don't know is I don't know if it's useful, but anyways, I have the search Wikipedia tool, which is the Wikipedia one. By the way, I can actually define that as a Wikipedia one only. I don't know. Yeah, but doesn't matter. Then I have the DuckDuckGo DDG API wrapper, DuckDuckGo API wrapper. And I actually don't need this either. I can replace this with the Wikipedia wrapper as well. This to me honestly makes no sense. This is not required. I can define the Wikipedia wrapper here, just the way we had done this earlier. This is the Wikipedia wrapper. Okay, perfect. And then I have, cool. So I'm just going to get rid of this. And this is simply going to be Wikipedia API wrapper. There you go. Those are the three tools that I have. There's one custom tool, there's one Wikipedia tool, and then there's one DuckDuckGo search tool that I have over here. So we're all set. And this is sort of a chat agent that we have here using the GPT-4o model. The only difference between the previous one and the current one, honestly, is that this is more like a, we're kind of again building on top of it, right? So here we just were executing one question at a time. But imagine if you were to chat, if you want to like really chat, right? If you want to build an actual chatbot per se, then what you need is you need a memory buffer, right? So you need a conversation buffer which will help you sort of have the complete list of questions that have been asked so far queued up, right? So you need some kind of a mechanism where you have all the questions nicely in that conversation queued up. So why is that important? Because then you can ask follow-up questions, right? For example, if you say, what has happened in Olympics? And you get a response and you say, no, in 2024. So when you say no in 2024, you would want the Olympics 2024 to sort of be carried forward. Instead of simply saying no 2024, you say it's 2024, but with the context that you had previously. So Olympics and 2024 together. So which is why you have the conversation buffer memory. All that it does is basically creates a chat history and it stores messages around in that. That's it. So create structured chat agent, LLM tools, prompt. The only additional thing that I'm passing here is this memory object that you see here, just to maintain memory. Everything else is the same. You're an AI assistant that can provide helpful answers and you have available tools. Right. And then, cool, let's go. Let's ask a question. Let's see how that goes. So now you can actually ask a question here. Where is 2024 Olympics happening? And when I ask a question, Wikipedia, 2024 Summer Olympics. I'm hoping it fetches the right results from Wikipedia. There you go. Fetch something. The 2024 Summer Olympics will take place in Paris, France from 24 July to 11th August 2024. Fantastic. Cool, right? So it's fetched it from Wikipedia here. Now, let me ask you a question. What is the current medal tally? Now I'm asking it another question. It's gone to DuckDuckGo. And underway after competition early Saturday morning. Has not started yet. Looks like it's screwed up. Medal tally available games are scheduled to take place 24 July. It looks like it's screwed up. Get me the leader on the medal tally currently. This is for 2024. Look what I'm doing here. I'm conversing here now. Some 346 medal events were held across who is the leader on the medal tally. So now, because of the memory buffer that I have, I'm actually able to chat right now. Yeah, looks like it's unable to fetch that information from DuckDuckGo for some reason. Okay, let's ask. What is the Indian media talking about Olympics 2024? Indian media is currently reporting on the 2024 Paris Olympics, highlighting that Manu Bakar made history by winning a bronze medal in the women's 10-meter air pistol event, which is India's first medal at the Paris Games. This is fantastic because it kind of found that I queried it differently, but I was able to still fetch it. Now it's actually querying it live against the DuckDuckGo search engine, fetch that response, summarized it for you, and return the results. Additionally, other Indian athletes like Ramita Jindal and Arjun Babutha have reached the finals. Oh wow, that's crazy, fantastic. We can ask this. We can ask this. Tennis star Rohan Bopanna is the oldest athlete, while swimmers, I guess, wow, 14. That's crazy. Are participating in which events in Olympics 2024? DuckDuckGo search. Let's see what it's doing. It's still going back and forth. You see this here? It's still going sort of back and forth here, trying to find the actual response. I think it's unable to. It's got it actually. These are final the respective. No, this is not true actually. This is incorrect. So it's still going back and forth. This is still not the final response, as you can imagine. It's still trying. It's still trying very hard to find the right response. It's going in that circles back and forth. Yeah, it couldn't find the answer for some reason. But we can check. What event is Ramita Jindal participating in? There you go. That's not true. That's not true. That is not true. Ramita Jindal is not in 10-meter air rifle. Oh, is it? Is she in air rifle? I don't think so though, but we can verify. Oh, no, she is. 10-meter air rifle. That's actually correct. Not bad. Still fetched it. So it actually did have the right answer. 10-meter air rifle. So cool. You get the idea? Do you guys understand how this is sort of evolved one step after the other? We did simply prompt with stock information. We went to RAG, then we went to agents with tools, then we went to agents with tools that have access to the internet. So now then we went to agents with tools that have access to the internet and have a memory sort of baked into them. So now you're actually simply chatting in this case. And I'll just hit an escape. So it'll stop most likely. Okay, clear? Okay. So there are multiple ways of going about it. So you can basically use the same exact piece of code to do it. But let me firstly draw like a high level view of how this works. Okay. So let's start with, so when you want to build like an agent, right? Or an assistant. Let's use the word assistant. Right. So whenever you wish to build like an AI assistant or a co-pilot, so to say, these are all co-pilots or assistants, by the way. But anyway, what are the things that you need to do? So I'm going to talk about the core AI workflow. Okay. And then we can talk about the engineering and everything associated with it later on. But the core AI workflow, what are the steps that are required? Now, the first thing first, there are multiple components associated with this. One is the model that you wish to that you have access to. Second is the prompt or the prompt I'm going to use prompt or prompt template or design that you're following, right? So the third thing that you would need to have access to is a bunch of tools that you need access to. And then the fourth one is access to an agent. And if you wanted to have, you want to have it like a chat interface. If you want a chat interface, then you need to have a conversation buffer, basically like a memory, so to say, right? So, or a memory, simply put, memory. That's it. So these are the 5 high-level things that you would need access to. How do you go about it? So step 1, you of course define the model or the LLM, right? So that you would need that you would want to chat, that you would want to query against. Now, typically a 3.5, a GPT 3.5 generally does a good job. If you have access to 4.0, use the 4.0 as well. That's fine. If you wish to have any of the other models, then you can access them as well. I have shown you examples through GPTs, but if you wish to try some of the others, feel free to do so. LangChain will help you access all of those models very, very easily, right? So in this case, there is a GPT 4.0 or a 3.5 turbo is what we have tried. You could use others as well. Prompt template, generally for more complex ones, a React template works very, very well for complex flows. This is generally like the most preferred one right now. There are other approaches as well around the agentic architecture. So like, for example, there is something called LangChain has recently launched something called as LangGraph. Just the way you have React, you also have something called as tree of thoughts, which is also a very, very fun exercise, right? So it basically takes a particular question, breaks that particular question down into 5 possible, or it takes 5 different paths or n different paths to solve that particular problem. Path 1, path 2, path 3. And it tries to answer that particular question through each of these. If any of them, it faces a dead end, it simply kills it. It carries on with the others. So it's like a different way of solving the same problem. It's like almost like having 5 people solve the same problem, right? Instead of breaking the same question down into multiple things where one person is sort of breaking it down, here it's more like get 5 people to solve the same problem and see what works the best kind of an approach. So it's tree of thought. So you essentially have like multiple ways to break it down. So you have chain of thought, tree of thought, React. These are all different approaches. React is generally for more complex flows. Tree of thought is something that's coming up right now as well. Tools. Now, you can create custom tools or you can create built-in tools. You can use built-in tools, right? Both are possible. I think we discussed both. So for the built-in tools, you may need, for some of them, you might need to have access to their API keys. Some are free to use. For example, Wikipedia, DuckDuckGo, they are free to use. Some of the more complex ones, like some of the more expensive ones, are Google search, right? Bing. They are all expensive. Meaning they all require specific API keys and they are paid. So you'll have to procure their keys before you can do it. Now, tools are very, very important because for your agent to work, as we discussed here, right? So for your agent to really do a good job, the more tools it has access to, the more versatile it can become, right? The more versatile it can become, the better decision making it can come up with, right? So that becomes super, super important. The next one here is the agent itself, right? Agent is simply nothing but a orchestrator. There is nothing specifically about the agent by itself.
the agent is simply like using this prompt template and executing this piece of information multiple times. That's it. So if you actually look at the React agent, and if you look at the code for the React agent, let's actually go there, right? Where is the React? So if you look at the create React agent, function, this is the simple function that's available. It's an agent that uses React prompting. Close this. And if you look at the function itself, it's actually super simple. That's it. This is the only piece of code that it has. So all that it does is it takes the it's basically like a for loop, more like so this is like check if stop sequence, stop, don't do anything. Else all that it does is it basically takes the question that you have asked, sends it to the prompt, and generates the response. That's it. It's very simple. It's just a simple LLM call. That's what it is. And it uses a very specific template here, as you can imagine. Here's an example. Here's the prompt, examples, stuff like that. So this is, by the way, from LangChain. So this is, by the way, how you can access it as well. So this is the prompt. This is how you can write the prompt. This is the prompt that we're anyways using. So it's super, super simple. So the agent per se is just basically making a call. The agent itself is not doing anything here. It's the prompt that's the magic. It's the tools that do the magic, nothing else. Okay. And last but not the least is this memory. Now this is sort of an optional thing, right? If you are okay to just have like, I mean, if you don't want, if you're building it for your personal use, you don't need like a chat bot, the chat sort of interface. So you can just still live with this kind of a flow. It'll still get you the response like this. But if you really want like a chat flow, you want to go back and forth, you want to try, keep chatting and everything, then in that case you can really build something like this. You want to do a bit of back and forth sort of exercise, you can do this. It's just adding a few more additional lines of code. That's it. So broadly, these are the things, guys. This is what you need to do. Now, specifically for math, there is an important thing that you need to keep in mind. Now, math is there are some very specialized there are some tools that are available. There are also some specialized chains that are there as well. So what do I mean by that? Let me show this to you. So there is something called as an LLM math chain that is available, which is sort of a bit of an older implementation, but it works. The LLM math chain is basically about is to be able to, it essentially creates Python code to run math, right? So it interprets a prompt and executes Python code to do math. So you could sort of use this kind of a chain instead, right? You can sort of use this sort of a chain for performing anything very, very specifically on the math side of things. Right? It's actually pretty cool as well. Now these days they've actually upgraded the LangChain as well. If you actually go here, LLM, yeah. So if you see LangChain.chain, import LLM math chains. So you can either, if you're doing it through React, you generally don't need to do this. But otherwise, if you specifically want to do something for React, then essentially you can create a tool that uses this chain. So what you can do is you can actually create a function over here, a specific tool that uses that particular chain to execute some of the math related stuff. Right. So for example, what is 13 raised to 0.3432? It would execute that for you, 2.411. But under the hood, what it's doing is it is actually executing this piece of Python code. So it is doing, Python translation, code to Python translation is what's happening here under the hoods. Do you understand this flow here as to what are all the different components that you will need to have access to before you can build like a chat agent yourself? Cool. Okay. You can decide that there are some information
that is already available on the memory. The memory buffer can be defined. So if you actually go in here, the LangChain. So if you go to LangChain, and if you look at the memory, the conversation buffer, this is the conversation buffer window. So you can define how big this could be. You can actually define the length of your conversation buffer here. You can actually go here. See, keeps a list of interactions of the conversation. It only uses the last k interactions. The k can be defined here. Let me just, we can define. I think there's a keyword argument here. See, the default k is 5. So you can decide how many more you wish to. So when you are defining it here, where did the so if you see here, you can actually pass a keyword argument here. Return messages is false. Hang on, where did that go? Yeah, there's a keyword argument here. So you can pass the k here. You can simply pass the k and you can define how much that k could be, right? How many to use over here. When you are using tools like these, see, now here's the thing. Now, if I ask you a question, hey, tell me how many LLM calls have I made to be able to get to this response? And then we are screwed. Because here it would have made, I don't know how many LLM calls. So now I don't know how many LLM calls have been made. Now I don't know how many tokens have been consumed. I don't know what was asked in each LLM call. I don't know what came out of each LLM call. Hence, you need a slightly different tool to do logging, to manage observability and to manage logging. For a traditional software app, you would use some kind of a logger, right? You would use, I mean, it depends from again model to model, but sorry, from app to app. But some of them would use a Datadog. Some of them would use application insights, depending upon the interface that you're working with. But these are just simply loggers. These are simply just log management tools. But in the case of Gen AI based models, you cannot use those traditional loggers. You will have to use slightly different logging system, and those are generally your those are slightly more complex, to say the least. They would essentially have like, okay, you have asked one question. Under this question, there are like multiple sub questions and stuff like that. And that is basically what LangChain is providing. So if you go here, LangChain, one of the offerings by LangChain is also that. I'm not selling LangChain, by the way, just to let you know. I just use LangChain. This is why I'm explaining that. But I am by no means an advocate of this. Just full transparency here. I am just I'm just a user of it. So LangSmith is essentially sort of a tool that helps you manage logs, that helps you track how many LLM calls have been made. So as you can see here, right? So you have like a nice view where there is an agent executor. In that agent executor, this was the input. What was the expected output? What was the error rate? Blah blah blah. All of that can be very beautifully tracked in that. So that's the only difference. Other than that, everything else remains the same. Unless, of course, you are fine-tuning the model and stuff like that. Then things will be a slightly different. But generally, I'll be very honest, right? So then there is very little need for fine-tuning models. If you can write your prompts well, and if you can set up your RAG well, you don't need to fine-tune models at all. At least in the modern day, you don't need to fine-tune models. And also, it has been observed that with small data, fine-tuning is actually pretty bad. It actually deteriorates the model performance. The amount of benefit that you get is very, very, very little through fine-tuning. So if I were to visually represent it, so this is, let's say, your accuracy or quality. I'm not going to use the word quality here. And then there are things like zero shot prompting. Then you have few shot prompting. Then you have chain of thought, react sort of things, right? COT, react. And then you have, right, on the same page, you have on one extreme, you have, and probably here somewhere you have agentic. So from here, you're almost referring to like agentic systems and stuff like that, agents. And then last but not the least, you have, let's say, fine tuning. And what has been observed is you would see a significant improvement in performance as you go from here to here. But that quality doesn't necessarily take off after that. So from fine tuning, when you look at fine tuning, the amount of benefit that you would sort of get, right, through fine tuning is very, very, very minuscule, right? You would probably do something like that if and only if you have a very specific need. Otherwise, these will give you decent results, right? So your zero shot prompting, your few shot prompting, your chain of thought, react, thought, right? So I'm just going to put thought also here, tree of thoughts, or the agentic behavior, that will already give you very, very good results. Fine tuning is probably not required. Somewhere here, you can also add RAG, by the way, right? So somewhere here, you can also add RAG. So RAG is also probably going to be here, Retrieval-Augmented Generation, chain of thought. That would already give you a decent result. So a good 90 to 95% of work can be nicely accomplished just through this. You will very rarely require the need for fine tuning. That too, only if you have a very, very large volume of data. If you have small pieces of information, that's often not very useful. It's not very enough. It's not enough at times. So it actually is counterproductive, and it actually drops the quality of the performance. So people have observed that the quality of results dropping because of fine tuning, because their data was not good enough. So just be mindful of that particular part. Okay. Awesome. Okay. So folks, that brings us to sort of the very end of our sessions, especially on chatbots, on large language models and agents, agentic systems and stuff like that. Okay.
Just a quick info, guys. Intellipaat offers Generative AI certification course in collaboration with iHub IIT Roorkee. This course is specially designed for AI enthusiasts who want to prepare and excel in the field of generative AI. Through this course, you will master Gen AI skills like foundation model, large language models, transformers, prompt engineering, diffusion models, and much more from top industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step toward career growth in the field of generative AI.
Recently, from Reddit threads to Twitter storms, one phrase keeps echoing: MCP servers are changing everything. Or the next big thing in AI is MCP servers. Some call it the future of AI, others say it's the missing piece we have been waiting for. But what exactly are MCP servers, and why is the entire AI world suddenly obsessed with it? Are they really worth the hype? Let's see it in detail. Before getting started, let's consider a scenario here. Suppose you are building an AI app and the things are going smoothly until it needs to connect with Gmail, Notion, or some API and database. Now you're stuck reading docs and building yet another custom connector for every tool separately. Sounding familiar, right? And that's what most devs face when working with AI. Until now. Of course, AI has come a long way. Large language models like GPT-4, Claude, Gemini are incredibly smart. They can write emails, generate code, and explain quantum physics, right? But here's the thing, they still can't send the email via Gmail or edit your UI directly in the Figma. Why? Because these models don't directly talk to the external systems or tools. To make that possible, they will need a middle layer, something like a translator or a bridge, that can help them communicate with the external tools like web servers, APIs, code editors, platforms, etc. And that bridge is the MCP servers. MCP stands for Model Context Protocol, a game-changing innovation introduced by Anthropic, the company behind Claude, one of the most efficient and high-performing LLMs. It's already being hailed as the next big thing in AI. And when even Google adopted this new thing so quickly, it became crystal clear that this thing is the future. MCP solves a fundamental problem in AI automation and evolution. That is, how to connect smart models with real-world tools without writing endless custom and fragmented integration codes. It works like a universal adapter, letting any AI model connect to any tool or service in a standardized way. Think of MCP like a USB charger, but for an AI. Just like USB-C replaced all those old, confusing chargers with one simple plug that works with everything smoothly, like phones, laptops, and monitors. MCP does the same for AI models. Instead of building a custom connection every time your AI needs to talk to Gmail, Figma, or a database, MCP provides a universal way to plug into any tool like a plug-and-play system. One protocol supports endless connections in a simple, clean, and scalable way. But why MCP is needed? You might got an idea until now, but let's see in details. So yes, AI is smart, but in the fast-moving world, being smart isn't just enough. AI needs context tools and real-world awareness to truly become powerful. And that's where MCP becomes the hero, bridging the gap between what AI can say and what it can actually do. Now, before we jump into what MCP servers are, how they work, now let's see how MCP servers rose to fame and why it's making headlines and how it's quietly becoming the backbone of modern AI automation. Considering now we know that even the smartest LLMs can't act on your behalf. They can suggest, explain, even write the code, but they can't execute them, fetch the latest stock price, or move a Figma frame. And right there, Anthropic's MCP, that is Model Context Protocol, emerges as a pivotal solution to these challenges. MCP provides AI models the power to interact with the world beyond their own minds. It defines a set of standardized rules, specifically a protocol that external applications and tools can use to give context to an AI model. This context can be data, capabilities, or even actions that can be performed. And because the system is standard, any tool can plug in, any model can understand, and everything just works. Now that you already got an understanding of what MCPs are, so let's see how do they work. MCPs operate on a client-server model. Imagine it like a team working together with the three main players like the host, the MCP client, and the MCP server. First, let's talk about the host process. This is the heart of AI-powered application, whether it's an app like Claude or a plugin in an IDE. The host is the part you interact with directly, and it's where AI agents live. It's responsible for processing the requests, initiating their actions, and giving responses to the user. Think of the host as the brain of the operation. Next, we have the MCP client, which acts as a bridge or a middleman. The MCP client takes the request made by the AI, the host, and forwards it to the appropriate MCP server. It's kind of like a messenger, ensuring the request reaches the server directly, securely, and efficiently. Each MCP client is designed to handle one specific server at a time, which also helps maintain security and keep things isolated and simple. Finally, the MCP server, that's where your tasks are performed. The MCP server is usually external to the AI model. It's a plugin or a tool that implements the MCP standard, offering a set of specific capabilities. The server is responsible for processing the request it gets from the MCP client and then providing back the information or performing the actions that are needed. The server might interface with the databases, an API, a cloud service, or any other tool in the real world that you want to communicate with. So let's break it down with a simple real-life example to make it more clear. Let's say the AI, the host, wants to know today's weather in Bengaluru. The AI sends out the request, "Hey, what's the weather today in Bengaluru?" The MCP client steps in, takes the request, and forwards it to the MCP server. Then, the MCP server, let's say, connects and communicates to a weather API to get real-time data. After that, the server gets that data, formats it in a way that AI can understand, and sends it back to the MCP client. Lastly, the MCP client then passes that information to the host, and now the AI can respond with something like, "Hey, the weather in Bengaluru today is sunny with a high of 30 degrees Celsius temperature." And just like that, the AI has real-time external information and can give a detailed and interactive answers. And this is how all it works. Thanks to the client-server architecture of MCP Server, that it provides live external knowledge and capabilities, which makes the AI feel much more intelligent and responsive. So instead of the AI relying solely on the internal knowledge base, the server acts as an additional brain, providing external insights and executing actions on behalf of the AI. It's like adding a whole new layer of intelligence to the system, making it far more interactive and capable. Now let's see how does this all happen internally and behind the scenes. So the communication between MCP clients and MCP servers typically happens using the JSON RPC, which is a lightweight standard protocol for remote procedure calls. This allows messages to be passed back and forth in a clear and a structured way. Now MCP supports different ways of sending and receiving the messages. For local processes, it uses STDIO, that is standard input output, which is perfect for processes running on the same machine. For remote communication, it uses HTTP with server sent events, that is SSE, which is a way of sending real-time updates from the server to the cloud over the web. A big part of MCP design focuses on security and controlled access. The host is in charge of managing the clients and approving which servers they can connect to. This means users and organizations have full control over what their AI assistants are allowed to access, ensuring everything is tightly secured, which is really crucial when it comes to open source intelligence. Now let's see what is the real life impact of MCPs worldwide. The true power of MCP, Model Context Protocol, becomes clear when we look at how it's being applied across real world tools and platforms. MCP is already powering some pretty impressive tools across development, enterprise, and data analysis. In the dev world, tools like SourceGraph Cody and Z Editor uses MCP to give AI assistants access to large code bases and dev resources, making code suggestions smarter and more context-driven. While in enterprise settings, Block uses MCP to securely connect AI with internal data. Then comes Apollo, which links AI tools to CRM systems, improving the decision-making and client interactions. Even for the data querying, apps like AI to SQL let users generate SQL queries using natural language, all made possible through MCP. Cloud Desktop is another great example. It uses MCP to access local files and apps securely, so it can offer highly relevant real-time help on your machine. Beyond that, platforms like Replit, Codium, and Appifier integrating MCP to let AI agents automate web searches, extract data, and even review the GitHub PRs with full context. From coding to workflows, MCP is becoming the go-to standard for connecting AI with the real-world tools securely and at scale. But the potential doesn't just stop here. Imagine a personal AI assistant with the deep access to our local apps, files, workflows, or even complex workflows orchestrated across multiple systems. Thanks to the MCP standardized, secure, and scalable approach, all of this is possible now. The goal for MCP servers is to become a standardized method for integrating AI tools and services across the web. With this approach, as new AI models and tools are created, they will seamlessly connect through MCP servers, allowing a far more interconnected and efficient AI ecosystem. Keeping up with the AI advancements can be exhausting. One day it's a new chatbot that can write poetry, and the next it's a model predicting stock trends. According to a report from the World Economic Forum, 85 million jobs are going to be replaced by AI by 2025, but at the same time, 97 million new roles will be created in areas like AI development, data science, and human AI collaboration. So how do you stay ahead in this rapidly changing data-driven world? By building real hands-on AI projects. Working on projects not only helps you understand AI concepts better, but also prepares you for real-world challenges. It's the best way to learn, grow, and make your skills future-proof. In this video, I'm sharing 10 AI project ideas, 5 for beginners and 5 for advanced, designed to give you the practical experience you need. Whether you're just starting or ready to tackle the big stuff, these projects will help you build something meaningful while also making your resume stand out in this competitive field. So the very first project idea that we'll be discussing is the product recommendation system. This is a system used by companies like Amazon, Netflix, and Spotify to suggest products, movies, or songs based on what users like. A product recommendation system is an algorithm that analyzes user behavior to suggest products that they might like. For example, the system or the algorithm might recommend phone cases or screen protectors if someone buys a phone. This makes shopping more personalized and engaging. An interesting fact before you dive into this project: Amazon's 35% of sales come through product recommendation engine itself. This tells you how valuable this project would be if you were to make a career in any e-commerce company. The first step in this project is to gather and pre-process data such as user ratings, browser history, or product descriptions. You can find a sample data at Kaggle or UCR repository. You'll then use machine learning techniques to develop the recommendation model. Popular methods would include collaborative filtering, where you recommend items based on what similar users have liked, or content-based filtering, where you recommend items similar to what a user has shown interest in before. Now, the tech stack for this project would include Python as the main programming language, with libraries like Pandas for data handling, scikit-learn for building machine learning models, KNN for collaborative filtering, or decision trees for content-based filtering. You can also use Flask for building a simple web app to display the recommendations to users. Completing this project will give you hands-on experience in machine learning, data manipulation, and web development. From a resume perspective, this project is a great addition because product recommendation systems are widely used in many industries like e-commerce entertainment like Netflix or Spotify and online services. Now, the second AI project idea is cancer disease detection. This project uses artificial intelligence to help detect cancer at an early stage, which can be crucial for saving lives. Now, in order to get started, you will need a dataset that contains labeled medical images of cancerous and non-cancerous cells. There are several datasets available online like the Cancer Image Archive, TCIA, that can help you with this. Once you have your data, the next step is to pre-process it. For medical images, this might involve converting them into numerical arrays or normalizing them to ensure consistency. For the tech stack, you will be using a combination of Python and deep learning libraries. The most popular deep learning framework is TensorFlow or PyTorch. Now, these libraries are great for building and training machine learning models. You will also work with CNNs, which are specifically designed for image recognition tasks like this one. CNNs analyze patterns in the medical images and then classify them as either cancerous or not. Now, to handle the data, you can use Pandas and NumPy. You can also use Flask or Streamlit to create simple web app for your algorithm. This way, doctors can upload images and your AI system will analyze them and give predictions on whether the image shows signs of cancer or not. Now, what's the benefit of working on this project? By working with the real-world medical data and applying deep learning techniques, you'll develop technical skills in AI, machine learning, and data processing. Now, this can prove to be highly valuable for your resume. Completing this project will demonstrate that you can work with large data sets, develop models, and even deploy AI systems, which are skills in high demand. Now, moving ahead to the third project idea. Businesses and consumers rely heavily on online reviews to make decisions. However, reading through thousands of reviews to understand customer opinions can be time-consuming. This is where sentiment analysis comes in. It's a technique in artificial intelligence that can automatically determine whether a review is positive, negative, or neutral. Through this, businesses are able to quickly gain valuable insights into customer feedback. The project will begin with collecting product review data, which is publicly available from sources like Amazon or Yelp, and then pre-process it. For the model, we will use machine learning techniques, specifically natural language processing, to understand and analyze the text. Initially, a simple model using techniques like bag of words or TF-IDF combined with a classifier like logistic regression can be implemented. Later, you can enhance the model using deep learning with RNNs or LSTM, which is long short-term memory, for better accuracy, especially for complex sentences. On completing this project, you will not only boost your understanding of NLP and machine learning techniques, but also make your resume stand out. This project will demonstrate your ability to handle both data pre-processing and model building, skills that are highly sought after in AI and data science roles. Additionally, it's a great way to get hands-on experience with Python and machine learning frameworks, both of which are valuable in the tech industry. Moving on to the fourth project idea. Job seekers today face a major challenge: getting their resumes noted by recruiters. Many companies use an applicant tracking system or ATS to filter resumes before they even reach a human recruiter. These systems scan resumes with specific keywords, job titles, skills, and qualifications. If a resume doesn't match these criteria, it may never get seen by a hiring manager. Now, the goal of this project is to build a system that can automatically pass and extract important information from resumes. This makes it easier for ATS to process resumes and for recruiters to find the most qualified candidates. The resume parser should be able to extract details such as the candidate's name, contact information, skills, education, work experience, and certifications from various resume formats like PDF, docx, and plain text. It will also analyze and categorize this information, helping job seekers optimize their resumes for ATS. In order to get started with this project, we'll use natural language processing or NLP to extract and understand the content of resumes. For parsing different formats, you can go ahead and use libraries like PDF, Miner, or docx in Python. You can then employ machine learning models for keyword extraction, entity recognition, and classification to identify and organize this information. There are also libraries such as Spacey or NLTK that can be used for text processing. Once that is done, we might also want to integrate a simple scoring system that ranks resumes based on the match to a job description. Completing this project adds immense value to your resume and skill set. You'll gain hands-on experience in working with text data using libraries and tools commonly used in industry for NLP tasks. You'd also understand how ATS systems work and learn about their role in modern hiring processes. This project will strengthen your proficiency in Python, machine learning, and NLP, making you a more attractive candidate for roles in data science, AI, and software development. Plus, it will give you a practical project to showcase, demonstrating your ability to solve real-world problems and adding a highly relevant skill to your resume. Moving on to the fifth project idea. This project focuses on a world where machines can see and interpret the environment just like humans. Real-time object detection is all about teaching computers to identify and track objects in live video feeds, such as recognizing a car, a pedestrian, or even a stray animal crossing the road. The problem this project addresses is simple yet impactful. In many industries, from autonomous driving to security systems, there's a need for technology that can detect and respond to objects in real time. Without it, processes remain slow and manual, and in some cases, this delay could even lead to accidents or inefficiencies. This project allows you to bridge that gap by creating a system capable of detecting objects instantly, enhancing safety and efficiency. You'll begin by collecting a dataset of images with labeled objects such as COCO or Pascal VOC. These labels help train your model to recognize different items. Then you can go ahead and use a pre-trained deep learning model like YOLO, You Only Look Once, or SSD, Single Shot Detector, which are designed for speed and accuracy. With frameworks like TensorFlow or PyTorch, you will fine-tune the model, feeding it data and teaching it to detect objects in real-time video streams from a webcam or CCTV camera. Finally, you'll integrate OpenCV for video processing and visualization. The tech stack includes Python for coding, TensorFlow or PyTorch for building the AI model, and OpenCV for handling video feeds and a GPU to process the data quickly. You'll also use libraries like NumPy and Pandas to manage the data. For your resume, this project will showcase your expertise in computer vision, machine learning, and handling real-time data, which are sought-after skills in the AI job market. On the other hand, for organizations, the benefit is enormous, whether it's enhancing surveillance systems, improving vehicle automation, or optimizing industrial workflows. Moving on to the sixth project idea. For a business that receives customer queries day and night, hiring people to answer these questions 24/7 can prove to be expensive and sometimes inefficient. This is where chatbots can help. A chatbot is an AI-powered assistant that can understand customer questions and provide instant answers, saving time and money while improving customer satisfaction. To build this project, you'll start by defining the purpose of your chatbot. Will it assist with customer support, book appointments, or maybe help users navigate a website? Once you figure out the main category of support, you'll need to gather or create a dataset of common questions and answers related to your topic. Next, you'll use tools like Python and frameworks like Flask or Fast API to create a conversational interface. For the AI brain, you can use pre-trained models from libraries like Hugging Face, which help the chatbot understand and respond to text. The backend might use an NLP model like BERT or GPT. These models analyze the input text, understand its meaning, and generate appropriate replies. If you're making a more advanced chatbot, you could connect it to a database or APIs to retrieve specific information like product availability or order status. Once the chatbot is built, you can again deploy it on website or messaging platform using tools like Heroku or AWS. This project is a fantastic addition to your resume. It shows your ability to solve real-world problems using AI to automate processes and build systems that improve user experience. By completing this project, you'll demonstrate your skills in Python, NLP, and deploying AI systems, which are in high demand. Plus, it gives you a practical example to discuss during interviews and sets you apart from problem solvers ready to tackle real business challenges. Moving on to the 7th project idea. Now, if you're a developer working on a large project with multiple team members, understanding someone else's code is like solving a puzzle, especially when the code lacks clear documentation. Writing documentation is tedious and time consuming, which is why most of the coders neglect it. This is a common problem, often leading to miscommunication, bugs, and slower onboarding of new developers. Code Document Generator is an algorithm designed to bridge this gap. This project aims to automate the processing of creating detailed and accurate code documentation. You will build an algorithm that will analyze the structure, functions, and logic of the code base and generate human-readable explanations for each part. To build this project, you can use technologies like Python and Hugging Face transformers. A model like GPT-4 can be fine-tuned to understand code and generate meaningful descriptions. You'll also work with frameworks like LangChain for chaining tasks and Fast API to deploy the tool as a web service. You can also go ahead and add a front-end interface using Streamlit that will make the algorithm user-friendly and visually appealing. By completing this project, you'll gain hands-on experience with advanced AI concepts like working with large language models and deploying them in real-world applications, while also highlighting your understanding of generative AI. The next project idea that I'll be talking about has been inspired by Google's revolutionary Cotton-Ace project, pest monitoring application. This is basically an AI application that helps farmers protect their crops by guiding them on aspects like the best time to spray pesticides. Pests are a huge challenge for farmers. They damage crops, lower yields, and increase the cost of farming due to the needs of pesticides. Many farmers don't realize there's an infestation until it's too late, leading to significant financial losses. This is where technology, especially AI, that can step up and make a big difference. The application will use image recognition to identify and track pest infestations in real time. Farmers can upload photos of their crops, and the app will analyze the images to detect pests, classify them, and provide actionable recommendations such as whether to use pesticides or take other measures. To get started, you'll need a dataset of pest images and healthy crop photos. Then you will need to train a machine learning model like CNN using frameworks like TensorFlow or PyTorch. Then you can go ahead and add a user-friendly interface, perhaps a mobile app where farmers can upload their images and receive instant feedback. You can even incorporate weather data or other regional trends to make the app more accurate. For this project, you'll use tools like TensorFlow or PyTorch for the AI model, OpenCV for image processing, and a cloud platform like AWS or Google Cloud for deployment. The mobile app can be built using Flutter or React Native to ensure it works on multiple devices. You could also add APIs for weather forecasting to give farmers extra insights. This project is a great addition to your resume. Employers value candidates who can demonstrate technical skills with practical applications, something that brings a change in the everyday lives of the people. Now moving on to the 9th project idea. Consider a situation where a marketing manager needs to come up with engaging content for products in an organization. Every campaign is going to require hours of brainstorming, research, and editing to create creative emails, blog posts, or social media captions. This is where an AI-powered marketing content generator can make life easier. Repetitive content creation takes up time and resources that could be better spent on creative ideas and connecting with customers. By building an AI marketing content creator, you can automate the task, making it faster and more efficient while still maintaining quality and personalization. To develop this project, you would start by training a generative language model like OpenAI's GPT or Hugging Face transformers to create different types of marketing content. You can feed it examples of blogs, email campaigns, or social media posts to fine-tune the model for specific industries. Adding features like customizable tone, keywords, or target audience will make the tool more versatile. You can also integrate a user-friendly interface using tools like Streamlit or Fast APIs so marketers can simply input a prompt and get ready to use content instantly. The tech stack will include Python as the primary programming language, libraries like TensorFlow or PyTorch for deep learning, and LangChain for chaining tasks like summarization and editing. Hugging Face can provide pre-trained models, while Pinecone or a similar vector database can store embeddings for fetching quick text. To deploy the app, you can use cloud platforms like AWS or Google Cloud. Completing this project will add immense value to your resume. It showcases your expertise in generative AI, NLP, and creating end-to-end solutions for real-world problems. By building a marketing content generator, you will not just be solving a technical problem, but you will be creating something that directly drives business growth, improves efficiency, and demonstrates the power of AI in everyday tasks. Here comes the last project idea for this particular video. Managing finances today can be complex and overwhelming for many people. Financial advice are often expensive, and individuals with limited resources may not have access to professional guidance. This is where a generative AI powered chatbot can bridge the gap by offering personalized, real time financial advice. To build this project, you would create a conversational AI model capable of understanding user inputs such as financial goals or challenges and provide tailored recommendations. The chatbot would use natural language processing to understand queries, retrieve the relevant data, and then generate meaningful responses. For example, if someone asks, "How can I save for retirement?" the chatbot could analyze the user's income, expense, and investment options to provide advice. The tech stack for this project includes Hugging Face transformers to build and fine-tune the conversational model, then LangChain for integrating multiple knowledge sources, and Pinecone or Waviate for storing and retrieving user data efficiently. Tools like Fast API can be used to deploy the chatbot, and a user-friendly interface can be created using Streamlit or React. Security protocols like OAuth can be added to ensure user data privacy. Completing this project will be a big win for both the individual and the organization. For you, it would demonstrate your ability to work on real-world AI problems using advanced tools and showcase your skills in generative AI and multimodal data integration. It's a standout addition to your resume, especially for fintech. So this is all for this video. I hope you guys were able to get some insight out of it. If you guys liked it, hit the like button and subscribe to Intellipaat's YouTube channel. Thank you and see you in the next video.